Section 0 of the 4th National Climate Assessment, Volume 2, Impacts, Risks, and Adaptation in the United States. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Warren Kati, Gurnee, Illinois. 4th National Climate Assessment, Volume 2, Impacts, Risks, and Adaptation in the United States by the U.S. Global Change Research Program. Section 0, Front Matter. About this report. The National Climate Assessment. The Global Change Research Act of 1990 mandates that the U.S. Global Change Research Program, USGCRP, deliver a report to Congress and the President no less than every 4 years that, quote, 1. Integrates, evaluates, and interprets the findings of the program, 2. Analyzes the effects of global change on the natural environment, agriculture, energy production and use, land and water resources, transportation, human health and welfare, human social systems, and biological diversity. And 3. Analyzes current trends in global change, both human-induced and natural, and projects major trends for the subsequent 25 to 100 years. End quote. The 4th National Climate Assessment, NCA4, fulfills that mandate in 2 volumes. This report, Volume 2, draws on the foundational science described in Volume 1, the Climate Science Special Report, CSSR. Volume 2 focuses on the human welfare, societal, and environmental elements of climate change and variability for 10 regions and 18 national topics, with particular attention paid to observed and projected risks, impacts, consideration of risk reduction, and implications under different mitigation pathways. Where possible, NCA4 Volume 2 provides examples of actions underway in communities across the United States to reduce the risks associated with climate change, increase resilience, and improve livelihoods. This assessment was written to help inform decision-makers, utility and natural resource managers, public health officials, emergency planners, and other stakeholders by providing a thorough examination of the effects of climate change on the United States. Climate Science Special Report, NCA4, Volume 1. The Climate Science Special Report, CSSR, published in 2017, serves as the first volume of NCA4. It provides a detailed analysis of how climate change is affecting the physical Earth system across the United States and provides the foundational physical science upon which much of the assessment of impacts in this report is based. The CSSR integrates and evaluates current findings on climate science and discusses the uncertainties associated with these findings. It analyzes trends in climate change, both human-induced and natural, and projects major trends to the end of this century. Projected changes in temperature, precipitation patterns, sea level rise, and other climate outcomes are based on a range of scenarios widely used in the climate research community, referred to as representative concentration pathways, RCPs. As an assessment and analysis of the physical science, the CSSR provides important input to the development of other parts of NCA4 and their primary focus on the human welfare, societal, economic, and environmental elements of climate change. A summary of the CSSR is provided in Chapter 2, Our Changing Climate, of this report. The full report can be accessed at science2017.globalchange.gov. Report Development, Review, and Approval Process. The National Oceanic and Atmospheric Administration, NOAA, served as the administrative lead agency for the preparation of this report. A federal steering committee, composed of representatives from USGCRP agencies, oversaw the report's development. A team of more than 300 federal and non-federal experts, including individuals from federal, state, and local governments, tribes and indigenous communities, national laboratories, universities, and the private sector, volunteered their time to produce the assessment, with input from external stakeholders at each stage of the process. A series of regional engagement workshops reached more than 1,000 individuals in over 40 cities, while listening sessions, webinars, and public comment periods provided valuable input to the authors. Participants included decision-makers from the public and private sectors, resource and environmental managers, scientists, educators, representatives from businesses and non-governmental organizations, and the interested public. NCA 4 Volume 2 was thoroughly reviewed by external experts and the general public, as well as the federal government, that is, the NCA 4 Federal Steering Committee, and several rounds of technical and policy review by the 13 federal agencies of the USGCRP. An expert external peer review of the whole report was performed by an ad hoc committee of the National Academies of Sciences, Engineering, and Medicine, NASEM. Additional information on the development of this assessment can be found in Appendix 1, Report Development Process. Sources used in this report. The findings in this report are based on an assessment of the peer-reviewed scientific literature, complemented by other sources, such as gray literature, where appropriate. In addition, authors used well-established and carefully evaluated observational and modeling datasets, technical input reports, USGCRP's sustained assessment products, and a suite of scenario products. Each source was determined to meet the standards of the Information Quality Act, see Appendix 2, Information in the Fourth National Climate Assessment. Sustained Assessment Products. The USGCRP's Sustained Assessment process facilitates and draws upon the ongoing participation of scientists and stakeholders, enabling the assessment of new information and insights as they emerge. The USGCRP led the development of two major sustained assessment products as inputs to NCA 4. The Impacts of Climate Change on Human Health in the United States, a Scientific Assessment, and the Second State of the Carbon Cycle Report. In addition, USGCRP agencies contributed products that improve the thoroughness of this assessment, including the U.S. Department of Agriculture's Scientific Assessment, Climate Change, Global Food Security, and the U.S. Food System. NOAA's Climate Resilience Toolkit, Climate Explorer, and State Climate Summaries. The U.S. Environmental Protection Agency's updated Economic Impacts of Climate Change report, and a variety of USGCRP indicators and scenario products that support the evaluation of climate-related risks. See Appendix 3, Data Tools and Scenario Products. USGCRP Scenario Products. As part of the sustained assessment process, federal interagency groups developed a suite of high-resolution scenario products that span a range of plausible future changes through at least 2100 in key environmental parameters. This new generation of USGCRP scenario products, hosted at https://scenarios.globalchange.gov, includes changes in average and extreme statistics of key climate variables, for example, temperature and precipitation, changes in local sea level rise along the entire U.S. coastline, changes in population as a function of demographic shifts and migration, and changes in land use driven by population changes. USGCRP scenario products help ensure consistency in underlying assumptions across the report and, therefore, improve the ability to compare and synthesize results across chapters. Where possible, authors have used the range of these scenario products to frame uncertainty in future climate and associated effects as it relates to the risks that are the focus of their chapters. As discussed briefly elsewhere in this front matter, and in more detail in Appendix 3, Data Tools and Scenario Products, future scenarios referred to as RCPs provide the global framing for NCA4 Volumes 1 and 2. RCPs focus on outputs, such as emissions and concentrations of greenhouse gases and particulate matter, that are in turn fed into climate models. As such, a wide range of future socioeconomic assumptions at the global and national scale, such as population growth, technological innovation, and carbon intensity of energy mix, could be consistent with the RCPs used throughout NCA4. For this reason, further guidance on U.S. population and land use assumptions was provided to authors. See Appendix 3, Data Tools and Scenario Products, including Table A3.1, for additional detail on these scenario products. Guide to the report. Summary findings. The 12 summary findings represent a very high-level synthesis of the material in the underlying report. They consolidate key messages and supporting evidence from 16 underlying national-level topic chapters, 10 regional chapters, and 2 response chapters. Overview. The overview presents the major findings alongside selected highlights from NCA4 Volume 2, providing a synthesis of material from the underlying report chapters. Chapter Text. Key messages and traceable accounts. Chapters are centered around key messages, which are based on the author's expert judgment of the synthesis of the assessed literature, with a view to presenting technical information in a manner more accessible to a broad audience. This report aims to present findings in the context of risks to natural and/or human systems. Assessing the risks to the nation posed by climate change and the measures that can be taken to minimize those risks helps users weigh the consequences of complex decisions. Since risk can most meaningfully be defined in relation to objectives or societal values, key messages in each chapter of this report aim to provide answers to specific questions about what is at risk in a particular region or sector, and in what way. The text supporting each key message provides evidence, discusses implications, identifies intersections between systems or cascading hazards, and points out paths to greater resilience. Where a key message focuses on managing risk, authors considered the following questions. What do we value? What is at risk? What outcomes do we wish to avoid with respect to these valued things? What do we expect to happen in the absence of adaptive action and/or mitigation? How bad could things plausibly get? Are there important thresholds or tipping points in the unique context of a given region, sector, and so on? These considerations are encapsulated in a single question. What keeps you up at night? Importantly, climate is only one of many drivers of change and risk. Where possible, chapters provide information about the dominant sources of uncertainty, such as scientific uncertainty or socioeconomic factors, as well as information regarding other relevant non-climate stressors. Each key message is accompanied by a traceable account that restates the key message found in the chapter text with calibrated confidence and likelihood language. See Table 1. These traceable accounts also document the supporting evidence and rationale the authors used in reaching their conclusions, while also providing information on sources of uncertainty. More information on traceable accounts is provided below. Our changing climate. USGCRP oversaw the production of the Climate Science Special Report, CSSR, NCA4 Volume 1, which assesses the current state of science related to climate change and its physical impacts. The CSSR is a detailed analysis of how climate change affects the physical Earth system across the United States. It presents foundational information and projections for climate change that improve consistency across analyses in NCA4 Volume 2. The CSSR is the basis for the Physical Climate Science Summary presented in Chapter 2, Our Changing Climate, of this report. National Topic Chapters. The National Topic Chapters summarize current and future climate change-related risks and what can be done to reduce those risks. These national chapters also synthesize relevant content from the regional chapters. New national topic chapters for NCA4 include Chapter 13, Air Quality, Chapter 16, Climate Effects on U.S. International Interests, and Chapter 17, Sector Interactions, Multiple Stressors, and Complex Systems. Regional chapters. Responding to public demand for more localized information, and because impacts and adaptation tend to be realized at a more local level, NCA4 provides greater detail in the regional chapters compared to the national topic chapters. The regional chapters assess current and future risks posed by climate change to each of NCA4's 10 regions. See Figure 1. And what can be done to minimize risk. Challenges, opportunities, and success stories for managing risk are illustrated through case studies. The regions defined in NCA4 are similar to those used in the third National Climate Assessment, NCA3, with these exceptions. The Great Plains region, formerly stretching from the border of Canada to the border of Mexico, is now divided into the Northern Great Plains and Southern Great Plains, along the Nebraska-Kansas border, and content related to the U.S. Caribbean islands is now found in its own chapter, distinct from the Southeast region. Response chapters. The response chapters assess the science of adaptation and mitigation, including benefits, trade-offs, and best practices of ongoing adaptation measures, and quantification of economic damages that can be avoided by reducing greenhouse gas emissions. The National Climate Assessment does not evaluate or recommend specific policies. Economic estimates. To the extent possible, economic estimates in this report have been converted to 2015 dollars using the U.S. Bureau of Economic Affairs Implicit Price Deflators for Gross Domestic Product, Table 1.1.9. For more information, please visit https:// bea.gov/national/index.htm. Where documented in the underlying literature, discount rates in specific estimates in this assessment are noted next to those projections. Use of scenarios. Climate modeling experts develop climate projections for a range of plausible futures. These projections capture variables such as the relationship between human choices, greenhouse gas (GHG), and particulate matter emissions, GHG concentrations in our atmosphere, and the resulting impacts, including temperature change and sea level rise. Some projections are consistent with continued dependence on fossil fuels, while others are achieved by reducing GHG emissions. The resulting range of projections reflects, in part, the uncertainty that comes with quantifying future human activities and their influence on climate. The most recent set of climate projections developed by the international scientific community is classified under 4 representative concentration pathways, or RCPs. A wide range of future socioeconomic assumptions could be consistent with the RCPs used throughout NCA4. NCA4 focuses on RCP 8.5 as a higher scenario associated with more warming, and RCP 4.5 as a lower scenario with less warming. Other RCP scenarios, e.g. RCP 2.6, a very low scenario, are used where instructive, such as in analyses of mitigation science issues. To promote understanding while capturing the context of the RCPs, authors use the phrases a higher scenario, RCP 8.5, and a lower scenario, RCP 4.5. RCP 8.5 is generally associated with higher population growth, less technological innovation, and higher carbon intensity of the global energy mix. RCP 4.5 is generally associated with lower population growth, more technological innovation, and lower carbon intensity of the global energy mix. NCA4 does not evaluate the feasibility of the socioeconomic assumptions within the RCPs. Future socioeconomic conditions, and especially the relationship between economic growth, population growth, and innovation, will have a significant impact on which climate change scenario is realized. The use of RCP 8.5 and RCP 4.5 as core scenarios is broadly consistent with the range used in NCA 3. For additional detail on these scenarios and what they represent, please see Appendix 3, Data Tools and Scenario Products, as well as Chapter 4 of the Climate Science Special Report. Treatment of uncertainties, risk framing, confidence, and likelihood. Risk framing. In March 2016, NASEM convened a workshop characterizing risk in climate change assessments to assist NCA4 authors in their analyses of climate-related risks across the United States. To help ensure consistency and readability across chapters, USGCRP developed guidance on communicating the risks and opportunities that climate change presents, including the treatment of scientific uncertainties. Where supported by the underlying literature, authors were encouraged to describe the full scope of potential climate change impacts, both negative and positive, including more extreme impacts that are less likely but would have severe consequences, and communicate the range of potential impacts and their probabilities of occurrence. describe the likelihood of the consequences associated with the range of potential impacts, the character and quality of the consequences, both negative and positive, and the strength of available evidence. Communicate cascading effects among and within complex systems, and quantify risks that could be avoided by taking action. Additional detail on how risk is defined for this report, as well as how risk-based framing was used, is available in Chapter 1, Overview. See Box 1.2, Evaluating Risks to Inform Decisions. Traceable accounts, confidence, and likelihood. Throughout NCA4's assessment of climate-related risks and impacts, authors evaluated the range of information in the scientific literature to the fullest extent possible, arriving at a series of key messages for each chapter. Drawing on guidance developed by the Intergovernmental Panel on Climate Change, IPCC, chapter authors further described the overall reliability in their conclusions using these metrics in their chapter's traceable accounts. Confidence in the validity of a finding based on the type, amount, quality, strength, and consistency of evidence, such as mechanistic understanding, theory, data, models, and expert judgment. The skill, range, and consistency of model projections, and the degree of agreement within the body of literature. Likelihood, which is based on measures of uncertainty expressed probabilistically, in other words, based on statistical analysis of observations or model results, or on the author's expert judgment. The author team's expert assessment of confidence for each key message is presented in the chapter's traceable accounts. Where the authors consider it is scientifically justified to report the likelihood of a particular impact within the range of possible outcomes, key messages in the traceable accounts also include a likelihood designation. Traceable accounts describe the process and rationale the authors used in reaching their conclusions, as well as their confidence in these conclusions. They provide additional information about the quality of information used and allow traceability to data and resources. Table 1. This table describes the meaning of the various categories of confidence level and likelihood assessment used in NCA4. The levels of confidence are the same as they appear in the CSSR, NCA4 Volume 1. And while the likelihood scale is consistent with the CSSR, there are fewer categories, as that report relies more heavily on quantitative methods and statistics. This binning of likelihood is consistent with other USG-CRP sustained assessment products, such as the Climate and Health Assessment and NCA3. Confidence level. Confidence level very high. Strong evidence, established theory, multiple sources, confident results, well-documented and accepted methods, etc. High consensus. Confidence level high. Moderate evidence, several sources, some consistency, methods vary and/or documentation limited, etc. Medium consensus. Confidence level medium. Suggestive evidence, a few sources, limited consistency, models incomplete, methods emerging, etc. Competing schools of thought. Confidence level low. Inconclusive evidence, limited sources, extrapolations, inconsistent findings, poor documentation and/or methods not tested, etc. Disagreement or lack of opinions among experts. Likelihood. Likelihood very likely, greater than or equal to 9 in 10. Likelihood likely, greater than or equal to 2 in 3. Likelihood as likely as not equals 1 in 2. Likelihood unlikely less than or equal to 1 in 3. Likelihood very unlikely less than or equal to 1 in 10. End of section 0. Section 1 of the 4th National Climate Assessment, Volume 2, Impacts, Risks, and Adaptation in the United States. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Warren Kati, Gurnee, Illinois. 4th National Climate Assessment, Volume 2, Impacts, Risks, and Adaptation in the United States by the U.S. Global Change Research Program. Chapter 1, Overview, Part 1. Introduction. Earth's climate is now changing faster than at any point in the history of modern civilization, primarily as a result of human activities. The impacts of global climate change are already being felt in the United States and are projected to intensify in the future. But the severity of future impacts will depend largely on actions taken to reduce greenhouse gas emissions and to adapt to the changes that will occur. Americans increasingly recognize the risks climate change poses to their everyday lives and livelihoods and are beginning to respond. Figure 1.1. Water managers in the Colorado River Basin have mobilized users to conserve water in response to ongoing drought intensified by higher temperatures. And an extension program in Nebraska is helping ranchers reduce drought and heat risks to their operations. The state of Hawaii is developing management options to promote coral reef recovery from widespread bleaching events caused by warmer waters that threaten tourism, fisheries, and coastal protection from wind and waves. To address higher risks of flooding from heavy rainfall, local governments in southern Louisiana are pooling hazard reduction funds, and cities and states in the Northeast are investing in more resilient water, energy, and transportation infrastructure. In Alaska, a tribal health organization is developing adaptation strategies to address physical and mental health challenges driven by climate change and other environmental changes. As Midwestern farmers adopt new management strategies to reduce erosion and nutrient losses caused by heavier rains, forest managers in the Northwest are developing adaptation strategies in response to wildfire increases that affect human health, water resources, timber production, fish and wildlife, and recreation. After extensive hurricane damage, fueled in part by a warmer atmosphere and warmer, higher seas, communities in Texas are considering ways to rebuild more resilient infrastructure. In the U.S. Caribbean, governments are developing new frameworks for storm recovery based on lessons learned from the 2017 hurricane season. Climate-related risks will continue to grow without additional action. Decisions made today determine risk exposure for current and future generations, and will either broaden or limit options to reduce the negative consequences of climate change. While Americans are responding in ways that can bolster resilience and improve livelihoods, neither global efforts to mitigate the causes of climate change nor regional efforts to adapt to the impacts currently approach the scales needed to avoid substantial damages to the U.S. economy, environment, and human health and well-being over the coming decades. Climate shapes where and how we live and the environment around us. Natural ecosystems, agricultural systems, water resources, and the benefits they provide to society are adapted to past climate conditions and their natural range of variability. A water manager may use past or current stream flow records to design a dam. A city could issue permits for coastal development based on current flood maps, and an electric utility or a farmer may invest in equipment suited to the current climate, all with the expectation that their investments and management practices will meet future needs. However, the assumption that current and future climate conditions will resemble the recent past is no longer valid. Chapter 28, Adaptation, Key Message 2. Observations collected around the world provide significant, clear, and compelling evidence that global average temperature is much higher and is rising more rapidly than anything modern civilization has experienced, with widespread and growing impacts. Figure 1.2. Climate Science Special Report, Chapter 1.9. The warming trend observed over the past century can only be explained by the effects that human activities, especially emissions of greenhouse gases, have had on the climate. Chapter 2, Climate, Key Message 1, and Figure 2.1. Climate change is transforming where and how we live, and presents growing challenges to human health and quality of life, the economy, and the natural systems that support us. Risks posed by climate variability and change vary by region and sector, and by the vulnerability of people experiencing impacts. Social, economic, and geographic factors shape the exposure of people and communities to climate-related impacts and their capacity to respond. Risks are often highest for those that are already vulnerable, including low-income communities, some communities of color, children, and the elderly. Chapter 14, Human Health, Key Message 2. Chapter 15, Tribes, Key Messages 1 through 3. Chapter 28, Adaptation, Introduction. Climate change threatens to exacerbate existing social and economic inequalities that result in higher exposure and sensitivity to extreme weather and climate-related events and other changes. Chapter 11, Urban, Key Message 1. Marginalized populations may also be affected disproportionately by actions to address the underlying causes and impacts of climate change, if they are not implemented under policies that consider existing inequalities. Chapter 11, Urban, Key Message 4. Chapter 28, Adaptation, Key Message 4. This report draws a direct connection between the warming atmosphere and the resulting changes that affect Americans' lives, communities, and livelihoods, now and in the future. It documents vulnerabilities, risks, and impacts associated with natural climate variability and human-caused climate change across the United States, and provides examples of response actions underway in many communities. It concludes that the evidence of human-caused climate change is overwhelming and continues to strengthen, that the impacts of climate change are intensifying across the country, and that climate-related threats to Americans' physical, social, and economic well-being are rising. These impacts are projected to intensify, but how much they intensify will depend on actions taken to reduce global greenhouse gas emissions and to adapt to the risks from climate change now and in the coming decades. Chapter 28, Adaptation, Introduction. Chapter 29, Mitigation, Key Messages 3 and 4. Our Changing Climate, Observations, Causes, and Future Change. Observed Change. Observations from around the world show the widespread effects of increasing greenhouse gas concentrations on Earth's climate. High temperature extremes and heavy precipitation events are increasing, glaciers and snow cover are shrinking, and sea ice is retreating. Seas are warming, rising, and becoming more acidic, and marine species are moving to new locations toward cooler waters. Flooding is becoming more frequent along the U.S. coastline. Growing seasons are lengthening, and wildfires are increasing. These and many other changes are clear signs of a warming world. Figure 1.2. Chapter 2, Climate, Box 2.2. Appendix 3, Data and Scenarios. See also the USG CRP Indicators and EPA Indicators websites. Causes of change. Scientists have understood the fundamental physics of climate change for almost 200 years. In the 1850s, researchers demonstrated that carbon dioxide and other naturally occurring greenhouse gases in the atmosphere prevent some of the heat radiating from Earth's surface from escaping to space. This is known as the greenhouse effect. This natural greenhouse effect warms the planet's surface about 60 degrees Fahrenheit above what it would be otherwise, creating a habitat suitable for life. Since the late 19th century, however, humans have released an increasing amount of greenhouse gases into the atmosphere through burning fossil fuels and, to a lesser extent, deforestation and land use change. As a result, the atmospheric concentration of carbon dioxide, the largest contributor to human-caused warming, has increased by about 40% over the industrial era. This change has intensified the natural greenhouse effect, driving an increase in global surface temperatures and other widespread changes in Earth's climate that are unprecedented in the history of modern civilization. Global climate is also influenced by natural factors that determine how much of the sun's energy enters and leaves Earth's atmosphere, and by natural climate cycles that affect temperatures and weather patterns in the short term, especially regionally. See Chapter 2, Climate, Box 2.1. However, the unambiguous long-term warming trend in global average temperature over the last century cannot be explained by natural factors alone. Greenhouse gas emissions from human activities are the only factors that can account for the observed warming over the last century. There are no credible alternative human or natural explanations supported by the observational evidence. Without human activities, the influence of natural factors alone would actually have had a slight cooling effect on global climate over the last 50 years. Chapter 2, Climate, Key Message 1, Figure 2.1. Future change. Greenhouse gas emissions from human activities will continue to affect Earth's climate for decades and even centuries. Humans are adding carbon dioxide to the atmosphere at a rate far greater than it is removed by natural processes, creating a long-lived reservoir of the gas in the atmosphere and oceans that is driving the climate to a warmer and warmer state. Some of the other greenhouse gases released by human activities, such as methane, are removed from the atmosphere by natural processes more quickly than carbon dioxide. As a result, efforts to cut emissions of these gases could help reduce the rate of global temperature increases over the next few decades. However, longer-term changes in climate will largely be determined by emissions and atmospheric concentrations of carbon dioxide and other longer-lived greenhouse gases. Chapter 2, Climate, Key Message 2. Climate models representing our understanding of historical and current climate conditions are often used to project how our world will change under future conditions. See Chapter 2, Climate, Box 2.7. Climate is defined as weather conditions over multiple decades, and climate model projections are generally not designed to capture annual or even decadal variation in climate conditions. Instead, projections are typically used to capture long-term changes, such as how the climate system will respond to changes in greenhouse gas levels over this century. Scientists test climate models by comparing them to current observations and historical changes. Confidence in these models is based, in part, on how well they reproduce these observed changes. Climate models have proven remarkably accurate in simulating the climate change we have experienced to date, particularly in the past 60 years or so, when we have greater confidence in observations. See Climate Science Special Report, Chapter 4.3.1. The observed signals of a changing climate continue to become stronger and clearer over time, giving scientists increased confidence in their findings even since the third National Climate Assessment was released in 2014. Today, the largest uncertainty in projecting future climate conditions is the level of greenhouse gas emissions going forward. Future global greenhouse gas emissions levels and resulting impacts depend on economic, political, and demographic factors that can be difficult to predict with confidence far into the future. Like previous climate assessments, NCA4 relies on a suite of possible scenarios to evaluate the implications of different climate outcomes and associated impacts throughout the 21st century. These representative concentration pathways, RCPs, capture a range of potential greenhouse gas emissions pathways and associated atmospheric concentration levels through 2100. RCPs drive climate model projections for temperature, precipitation, sea level, and other variables under futures that have either lower or higher greenhouse gas emissions. RCPs are numbered according to changes in radiative forcing by 2100 relative to pre-industrial conditions, plus 2.6, plus 4.5, plus 6.0, or plus 8.5 watts per square meter. Each RCP leads to a different level of projected global temperature change. Higher numbers indicate greater projected temperature change and associated impacts. The higher scenario, RCP 8.5, represents a future where annual greenhouse gas emissions increase significantly throughout the 21st century before leveling off by 2100, whereas the other RCPs represent more rapid and substantial mitigation by mid-century, with greater reductions thereafter. Current trends in annual greenhouse gas emissions globally are consistent with RCP 8.5. Of the two RCPs predominantly referenced throughout this report, the lower scenario, RCP 4.5, envisions about 85% lower greenhouse gas emissions than the higher scenario, RCP 8.5, by the end of the 21st century. See Chapter 2, Climate, Figure 2.2. In some cases, throughout this report, a very low scenario, RCP 2.6, that represents more immediate, substantial, and sustained emissions reductions is considered. Each RCP could be consistent with a range of underlying socioeconomic conditions or policy choices. See the Scenario Products section of Appendix 3 in this report, as well as Climate Science Special Report Chapters 4.2.1 and 10.2.1 for more detail. The effects of different future greenhouse gas emissions levels on global climate become most evident around 2050, when temperature, Figure 1.3, Chapter 2, Climate, Figure 2.2, precipitation and sea level rise, Figure 1.4, Chapter 2, Climate, Figure 2.3, projections based on each scenario begin to diverge significantly. with substantial and sustained reductions in greenhouse gas emissions, e.g., consistent with the very low scenario RCP 2.6, the increase in global annual average temperature relative to pre-industrial times could be limited to less than 3.6 degrees Fahrenheit, 2 degrees Celsius. Chapter 2, Climate, Box 2.4, Climate Science Special Report, Chapter 4.2.1. Without significant greenhouse gas mitigation, the increase in global annual average temperature could reach 9 degrees Fahrenheit or more by the end of this century. Chapter 2, Climate, Key Message 2. For some aspects of Earth's climate system that take longer to respond to changes in atmospheric greenhouse gas concentrations, such as global sea level, some degree of long-term change will be locked in for centuries to come, regardless of the future scenario. See Climate Science Special Report, Chapter 12.5.3. Early greenhouse gas emissions mitigation can reduce climate impacts in the nearer term, such as reducing the loss of Arctic sea ice and the effects on species that use it, and in the longer term by avoiding critical thresholds, such as marine ice sheet instability and the resulting consequences for global sea level and coastal development. Chapter 29, Mitigation, Timing and Magnitude of Action. Annual average temperatures in the United States are projected to continue to increase in the coming decades. Regardless of future scenario, additional increases in temperatures across the contiguous United States of at least 2.3 degrees Fahrenheit relative to 1986 to 2015 are expected by the middle of this century. As a result, recent record-setting hot years are expected to become common in the near future. By late this century, increases of 2.3 to 6.7 degrees Fahrenheit are expected under a lower scenario, RCP 4.5, and 5.4 degrees to 11 degrees Fahrenheit under a higher scenario, RCP 8.5, relative to 1986 to 2015. Figure 1.3. Chapter 2, Climate, Key Message 5, Figure 2.4. Alaska has warmed twice as fast as the global average since the mid-20th century. This trend is expected to continue. Chapter 26, Alaska, Background. High temperature extremes, heavy precipitation events, high tide flooding events along the U.S. coastline, ocean acidification and warming, and forest fires in the western United States and Alaska are all projected to continue to increase, while land and sea ice cover, snowpack, and surface soil moisture are expected to continue to decline in the coming decades. These and other changes are expected to increasingly impact water resources, air quality, human health, agriculture, natural ecosystems, energy and transportation infrastructure, and many other natural and human systems that support communities across the country. The severity of these projected impacts and the risks they present to society is greater under futures with higher greenhouse gas emissions, especially if limited or no adaptation occurs. Chapter 29, Mitigation, Key Message 2. Box 1.1, Confidence and Uncertainty in Climate Science. Many of the decisions we make every day are based on less than perfect knowledge. For example, while GPS-based applications on smartphones can provide a travel time estimate for our daily drive to work, an unexpected factor like a sudden downpour or fender bender might mean a ride originally estimated to be 20 minutes could actually take longer. Fortunately, even with this uncertainty, we are confident that our trip is unlikely to take less than 20 minutes or more than half an hour, and we know where we are headed. We have enough information to plan our commute. Uncertainty is also a part of science. A key goal of scientific research is to increase our confidence and reduce the uncertainty in our understanding of the world around us. Even so, there is no expectation that uncertainty can be fully eliminated, just as we do not expect a perfectly accurate estimate for our drive time each day. Studying Earth's climate system is particularly challenging because it integrates many aspects of a complex natural system as well as many human-made systems. Climate scientists find varying ranges of uncertainty in many areas, including observations of climate variables, the analysis and interpretation of those measurements, the development of new observational instruments, and the use of computer-based models of the processes governing Earth's climate system. While there is inherent uncertainty in climate science, there is high confidence in our understanding of the greenhouse effect and the knowledge that human activities are changing the climate in unprecedented ways. There is enough information to make decisions based on that understanding. Where important uncertainties do exist, efforts to quantify and report those uncertainties can help decision-makers plan for a range of possible future outcomes. These efforts also help scientists advance understanding and ultimately increase confidence in and the usefulness of model projections. Assessments like this one explicitly address scientific uncertainty associated with findings and use specific language to express it, to improve relevance to risk analysis and decision-making. See Front Matter and Box 1.2. End of Box 1.1. Box 1.2 Evaluating Risks to Inform Decisions. In this report, risks are often defined in a qualitative sense as threats to life, health, and safety, the environment, economic well-being, and other things of value to society. Chapter 28, Adaptation, Introduction. In some cases, risks are described in quantitative terms, estimates of how likely a given threat is to occur, probability, and the damages that would result if it did happen, consequences. Climate change is a risk management challenge for society. It presents uncertain and potentially severe consequences for natural and human systems across generations. It is characterized by multiple intersecting and uncertain future hazards and, therefore, acts as a risk multiplier that interacts with other stressors to create new risks or to alter existing ones. See Chapter 17, Complex Systems, Key Message 1. Current and future greenhouse gas emissions, and thus mitigation actions to reduce emissions, will largely determine future climate change impacts and risks to society. Mitigation and adaptation activities can be considered complementary strategies. Mitigation efforts can reduce future risks, while adaptation can minimize the consequences of changes that are already happening as a result of past and present greenhouse gas emissions. Adaptation entails proactive decision-making and investments by individuals, businesses, and governments to counter specific risks from climate change that vary from place to place. Climate risk management includes some familiar attributes and tactics for most businesses and local governments, which often manage or design for a variety of weather-related risks, including coastal and inland storms, heat waves, threats to water availability, droughts, and floods. Measuring risk encompasses both likelihoods and consequences of specific outcomes and involves judgments about what is of value, ranking of priorities, and cost-benefit analyses that incorporate the trade-offs among climate and non-climate related options. This report characterizes specific risks across regions and sectors in an effort to help people assess the risks they face create and implement a response plan, and monitor and evaluate the efficacy of a given action. See Chapter 28, Adaptation, Key Message 1, Figure 28.1. End of Box 1.2. End of Chapter 1, Part 1. Section 2 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 1, Overview, Part 2. Climate Change in the United States, Current and Future Risks. Some climate-related impacts, such as increasing health risks from extreme heat, are common to many regions of the United States. Chapter 14, Human Health, Key Message 1. Others represent more localized risks, such as infrastructure damage caused by thawing of permafrost, long frozen ground, in Alaska, or threats to coral reef ecosystems from warmer and more acidic seas in the U.S. Caribbean, as well as Hawaii and the U.S.-affiliated Pacific Islands. Chapter 26, Alaska, Key Message 2. Chapter 20, U.S. Caribbean, Key Message 2. Chapter 27, Hawaii and Pacific Islands, Key Message 4. Risks vary by both a community's exposure to physical climate impacts and by factors that influence its ability to respond to changing conditions and to recover from adverse weather and climate-related events, such as extreme storms or wildfires. Chapter 14, Human Health, Key Message 2. Chapter 15, Tribes, State of the Sector, Key Message 1 and 2. Chapter 28, Adaptation, Key Message 4. Many places are subject to more than one climate-related impact, such as extreme rainfall combined with coastal flooding, or drought coupled with extreme heat, wildfire, and flooding. The compounding effects of these impacts result in increased risks to people, infrastructure, and interconnected economic sectors. Chapter 11, Urban, Key Message 1. Impacts affecting interconnected systems can cascade across sectors and regions, creating complex risks and management challenges. For example, changes in the frequency, intensity, extent, and duration of wildfires can result in a higher instance of landslides that disrupt transportation systems and the flow of goods and services within or across regions. Box 1.3. Many observed impacts reveal vulnerabilities in these interconnected systems that are expected to be exacerbated as climate-related risks intensify. Under a higher scenario, RCP 8.5, it is very likely that some impacts, such as the effects of ice sheet disintegration on sea level rise and coastal development, will be irreversible for many thousands of years, and others, such as species extinction, will be permanent. Chapter 7, Ecosystems, Key Message 1. Chapter 9, Oceans, Key Message 1. Chapter 29, Mitigation, Key Message 2. Economy and Infrastructure. Without more significant global greenhouse gas mitigation and regional adaptation efforts, climate change is expected to cause substantial losses to infrastructure and property and impede the rate of economic growth over this century. Chapter 4, Energy, Key Message 1. Chapter 8, Coastal, Key Message 1. Chapter 11, Urban, Key Message 2. Chapter 12, Transportation, Key Message 1. Regional Chapters 18 through 27. Regional economies and industries that depend on natural resources and favorable climate conditions, such as agriculture, tourism, and fisheries, are increasingly vulnerable to impacts driven by climate change. Chapter 7, Ecosystems, Key Message 3. Chapter 10, Agriculture, Key Message 1. Reliable and affordable energy supplies, which underpin virtually every sector of the economy, are increasingly at risk from climate change and weather extremes. Chapter 4, Energy, Key Message 1. The impacts of climate change beyond our borders are expected to increasingly affect our trade and economy, including import and export prices and U.S. businesses with overseas operation and supply chains. Box 1.4. Chapter 16, International, Key Message 1. Chapter 17, Complex Systems, Key Message 1. Some aspects of our economy may see slight improvements in a modestly warmer world. However, the continued warming that is projected to occur without significant reductions in global greenhouse gas emissions is expected to cause substantial net damage to the U.S. economy, especially in the absence of increased adaptation efforts. The potential for losses in some sectors could reach hundreds of billions of dollars per year by the end of this century. Chapter 29, Mitigation, Key Message 2. Existing water, transportation, and energy infrastructure already face challenges from heavy rainfall, inland and coastal flooding, landslides, drought, wildfire, heat waves, and other weather and climate events. Figures 1.5 through 1.9. Chapter 11, Urban, Key Message 2. Chapter 12, Transportation, Key Message 1. Many extreme weather and climate-related events are expected to become more frequent and more intense in a warmer world, creating greater risks of infrastructure disruption and failure that can cascade across economic sectors. Chapter 3, Water, Key Message 2. Chapter 4, Energy, Key Message 1. Chapter 11, Urban, Key Message 3. Chapter 12, Transportation, Key Message 2. For example, more frequent and severe heat waves and other extreme events in many parts of the United States are expected to increase stresses on the energy system, amplifying the risk of more frequent and longer-lasting power outages and fuel shortages that could affect other critical sectors and systems, such as access to medical care. Chapter 17, Complex Systems, Box 17.5. Chapter 4, Energy, Key Message 1. Chapter 8, Coastal, Key Message 1. Chapter 11, Urban, Key Message 3. Chapter 12, Transportation, Key Message 3. Current infrastructure is typically designed for historical climate conditions. Chapter 12, Transportation, Key Message 1. And development patterns. For instance, coastal land use generally do not account for a changing climate. Chapter 5, Land Changes, State of the Sector, resulting in increasing vulnerability to future risks from weather extremes and climate change. Chapter 11, Urban, Key Message 2. Infrastructure age and deterioration make failure or interrupted service from extreme weather even more likely. Chapter 11, Urban, Key Message 2. Climate change is expected to increase the costs of maintaining, repairing, and replacing infrastructure, with differences across regions. Chapter 12, Transportation, Regional Summary. Recent extreme events demonstrate the vulnerabilities of interconnected economic sectors to increasing risks from climate change. See Box 1.3. In 2017, Hurricane Harvey dumped an unprecedented amount of rainfall over the greater Houston area, some of which has been attributed to human-induced climate change. Chapter 2, Climate, Box 2.5. Resulting power outages had cascading effects on critical infrastructure facilities, such as hospitals and water and wastewater treatment plants. Reduced oil production and refining capacity in the Gulf of Mexico caused price spikes regionally and nationally from actual and anticipated gasoline shortages. Figure 1.6. Chapter 17, Complex Systems, Key Message 1. In the U.S. Caribbean, Hurricanes Irma and Maria caused catastrophic damage to infrastructure, including the complete failure of Puerto Rico's power grid and the loss of power throughout the U.S. Virgin Islands, as well as extensive damage to the region's agricultural industry. The death toll in Puerto Rico grew in the 3 months following Maria's landfall on the island, due in part to the lack of electricity and potable water, as well as access to medical facilities and medical care. Chapter 20, U.S. Caribbean, Box 20.1, Key Message 5. Climate-related risks to infrastructure, property, and the economy vary across regions. Along the U.S. coastline, public infrastructure and $1 trillion in national wealth held in coastal real estate are threatened by rising sea levels, higher storm surges, and the ongoing increase in high tide flooding. Figures 1.4 and 1.8. Chapter 8, Coastal, Key Message 1. Coastal infrastructure provides critical lifelines to the rest of the country, including energy supplies and access to goods and services from overseas trade. Increased damage to coastal facilities is expected to result in cascading costs and national impacts. Chapter 8, Coastal, Key Message 1. Chapter 4, Energy, State of the Sector, Key Message 1. High tide flooding is projected to become more disruptive and costlier as its frequency, depth, and inland extent grow in the coming decades. Without significant adaptation measures, many coastal cities in the Southeast are expected to experience daily high tide flooding by the end of the century. Chapter 8, Coastal, Key Message 1. Chapter 19, Southeast, Key Message 2. Higher sea levels will also cause storm surge from tropical storms to travel farther inland than in the past, impacting more coastal properties and infrastructure. Chapter 8, Coastal, Key Message 1. Chapter 19, Southeast, Key Message 2. Oil, natural gas, and electrical infrastructure located along the coasts of the Atlantic Ocean and Gulf of Mexico are at increased risk of damage from rising sea levels and stronger hurricanes. Regional disruptions are expected to have national implications. Chapter 4, Energy, State of the Sector, Key Message 1. Chapter 18, Northeast, Key Message 3. Chapter 19, Southeast, Key Message 2. Hawaii and the U.S.-affiliated Pacific Islands and the U.S. Caribbean also face high risks to critical infrastructure from coastal flooding, erosion, and storm surge. Chapter 4, Energy, State of the Sector, Chapter 20, U.S. Caribbean, Key Message 3, Chapter 27, Hawaii and Pacific Islands, Key Message 3. In the western United States, increasing wildfire is damaging ranches and rangelands, as well as property in cities near the wildland-urban interface. Drier conditions are projected to increase the risk of wildfires and damage to property and infrastructure, including energy production and generation assets, and the power grid. Chapter 4, Energy, Key Message 1. Chapter 11, Urban, Regional Summary. Chapter 24, Northwest, Key Message 3. In Alaska, thawing of permafrost is responsible for severe damage to roads, buildings, and pipelines that will be costly to replace, especially in remote parts of Alaska. Alaska oil and gas operations are vulnerable to thawing permafrost, sea level rise, and increased coastal exposure due to declining sea ice. However, a longer ice-free season may enhance offshore energy operations and transport. Chapter 4, Energy, State of the Sector. Chapter 26, Alaska, Key Message 2 and 5. These impacts are expected to grow with continued warming. U.S. agriculture and the communities it supports are threatened by increases in temperatures, drought, heavy precipitation events, and wildfire on rangelands. Figure 1.10, Chapter 10, Ag and Rural, Key Messages 1 and 2. Case Study, Groundwater Depletion in the Ogallala Aquifer Region. Chapter 23, South Great Plains, Key Message 1. Case Study, the Edwards Aquifer. Yields of major U.S. crops, such as corn, soybeans, wheat, rice, sorghum, and cotton, are expected to decline over this century as a consequence of increases in temperatures and possibly changes in water availability and disease and pest outbreaks. Chapter 10, Ag and Rural, Key Message 1. Increases in growing season temperatures in the Midwest are projected to be the largest contributing factor to declines in U.S. agricultural productivity. Chapter 21, Midwest, Key Message 1. Climate change is also expected to lead to large-scale shifts in the availability and prices of many agricultural products across the world, with corresponding impacts on U.S. agricultural producers and the U.S. economy. Chapter 16, International, Key Message 1. Extreme heat poses a significant risk to human health and labor productivity in the agricultural, construction, and other outdoor sectors. Chapter 10, Ag and Rural, Key Message 3. Under a higher scenario, RCP 8.5, almost 2 billion labor hours are projected to be lost annually by 2090 from the impacts of temperature extremes, costing an estimated $160 billion in lost wages. Chapter 14, Human Health, Key Message 4. States within the Southeast, Chapter 19, Southeast, Key Message 4, and Southern Great Plains, Chapter 23, Southern Great Plains, Key Message 4. Regions are projected to experience some of the greatest impacts. See Figure 1.21. Natural Environment and Ecosystem Services. Climate change threatens many benefits that the natural environment provides to society: safe and reliable water supplies, clean air, protection from flooding and erosion, and the use of natural resources for economic, recreational, and subsistence activities. Valued aspects of regional heritage and quality of life tied to the natural environment, wildlife, and outdoor recreation will change with the climate, and as a result, future generations can expect to experience and interact with natural systems in ways that are much different than today. Without significant reductions in greenhouse gas emissions, extinctions and transformative impacts on some ecosystems cannot be avoided, with varying impacts on the economic, recreational, and subsistence activities they support. Changes affecting the quality, quantity, and availability of water resources, driven in part by climate change, impact people and the environment. Chapter 3, Water, Key Message 1. Dependable and safe water supplies for U.S. Caribbean, Hawaii, and U.S.-affiliated Pacific Island communities and ecosystems are threatened by rising temperatures, sea level rise, saltwater intrusion, and increased risks of drought and flooding. Chapter 3, Water, Regional Summary. Chapter 20, U.S. Caribbean, Key Message 1. Chapter 27, Hawaii and Pacific Islands, Key Message 1. In the Midwest, the occurrence of conditions that contribute to harmful algal blooms, which can result in restrictions to water usage for drinking and recreation, is expected to increase. Chapter 3, Water, Regional Summary. Chapter 21, Midwest, Key Message 3. In the Southwest, water supplies for people and nature are decreasing during droughts, due in part to climate change. Intensifying droughts, heavier downpours, and reduced snowpack are combining with other stressors such as groundwater depletion to reduce the future reliability of water supplies in the region, with cascading impacts on energy production and other water-dependent sectors. Chapter 3, Water, Regional Summary. Chapter 4, Energy, State of the Sector. Chapter 25, Southwest, Key Message 5. In the southern Great Plains, current drought and projected increases in drought length and severity threaten the availability of water for agriculture. Figures 1.11 and 1.12. Chapter 23, Southern Great Plains, Key Message 1. Reductions in mountain snowpack and shifts in snowmelt timing are expected to reduce hydropower production in the southwest and the northwest. Chapter 24, Northwest, Key Message 3. Chapter 25, Southwest, Key Message 5. Drought is expected to threaten oil and gas drilling and refining, as well as thermoelectric power plants that rely on a steady supply of water for cooling. Chapter 4, Energy, State of the Sector, Key Message 1. Chapter 22, Northern Great Plains, Key Message 4. Chapter 23, Southern Great Plains, Key Message 2. Chapter 25, Southwest, Key Message 5. Tourism, outdoor recreation, and subsistence activities are threatened by reduced snowpack, increases in wildfire activity, and other stressors affecting ecosystems and natural resources. Figure 1.2d, 1.2k, and 1.13. Chapter 7, Ecosystems, Key Message 3. Increasing wildfire frequency. Chapter 19, Southeast, Case Study, Prescribed Fire. Pest and disease outbreaks. Chapter 21, Midwest, Case Study, Adaptation and Forestry, and other stressors are projected to reduce the ability of U.S. forests to support recreation as well as economic and subsistence activities. Chapter 6, Forests, Key Messages 1 and 2. Chapter 19, Southeast, Key Message 3. Chapter 21, Midwest, Key Message 2. Increases in wildfire smoke events driven by climate change are expected to reduce the amount and quality of time spent in outdoor activities. Chapter 13, Air Quality, Key Message 2. Chapter 24, Northwest, Key Message 4. Projected declines in snowpack in the western United States and shifts to more precipitation falling as rain than snow in the cold season in many parts of the central and eastern United States are expected to adversely impact the winter recreation industry. Chapter 18, Northeast, Key Message 1. Chapter 22, Northern Great Plains, Key Message 3. Chapter 24, Northwest, Key Message 1, Box 24.7. In the Northeast, activities that rely on natural snow and ice cover may not be economically viable by the end of the century without significant reductions in global greenhouse gas emissions. Chapter 18, Northeast, Key Message 1. Diminished snowpack, increased wildfire, pervasive drought, flooding, ocean acidification, and sea level rise directly threaten the viability of agriculture, fisheries, and forestry enterprises on tribal lands across the United States and impact tribal tourism and recreation sectors. Chapter 15, Tribes, Key Message 1. Climate change has already had observable impacts on biodiversity and ecosystems throughout the United States that are expected to continue. Many species are shifting their ranges, figure 1.2h, and changes in the timing of important biological events, such as migration and reproduction, are occurring in response to climate change. Chapter 7, Ecosystems, Key Message 1. Climate change is also aiding the spread of invasive species. Chapter 21, Midwest, Case Study, Adaptation and Forestry. Chapter 22, Northern Great Plains, Case Study, Crow Nation and the Spread of Invasive Species. Recognized as a major driver of biodiversity loss and substantial ecological and economic costs globally. Chapter 7, Ecosystems, Invasive Species. As environmental conditions change further, mismatches between species and the availability of the resources they need to survive are expected to occur. Chapter 7, Ecosystems, Key Message 2. Without significant reductions in global greenhouse gas emissions, extinctions and transformative impacts on some ecosystems cannot be avoided in the long term. Chapter 9, Oceans, Key Message 1. While some new opportunities may emerge from ecosystem changes, economic and recreational opportunities and cultural heritage based around historical use of species or natural resources in many areas are at risk. Chapter 7, Ecosystems, Key Message 3. Chapter 18, Northeast, Key Messages 1 and 2, Box 18.6. Ocean warming and acidification pose high and growing risks for many marine organisms, and the impacts of climate change on ocean ecosystems are expected to lead to reductions in important ecosystem services, such as aquaculture, fishery productivity, and recreational opportunities. Chapter 9, Oceans, Key Message 2. While climate change impacts on ocean ecosystems are widespread, the scope of ecosystem impacts occurring in tropical and polar areas is greater than anywhere else in the world. Ocean warming is already leading to reductions in vulnerable coral reef and sea ice habitats that support the livelihoods of many communities. Chapter 9, Oceans, Key Message 1. Decreasing sea ice extent in the Arctic represents a direct loss of important habitat for marine mammals, causing declines in their populations. Figure 1.2f. Chapter 26, Alaska, Box 26.1. Changes in spring ice melt have affected the ability of coastal communities in Alaska to meet their walrus harvest needs in recent years. Chapter 26, Alaska, Key Message 1. These changes are expected to continue as sea ice declines further. Chapter 2, Climate, Key Message 7. In the tropics, ocean warming has already led to widespread coral reef bleaching and/or outbreaks of coral diseases off the coastlines of Puerto Rico, the U.S. Virgin Islands, Florida, and Hawaii and the U.S.-affiliated Pacific Islands. Chapter 20, U.S. Caribbean, Key Message 2, Chapter 27, Hawaii and Pacific Islands, Key Message 4. By mid-century, widespread coral bleaching is projected to occur annually in Hawaii and the U.S.-affiliated Pacific Islands. Figure 1.14. Bleaching and ocean acidification are expected to result in loss of reef structure, leading to lower fisheries yields and loss of coastal protection and habitat, with impacts on tourism and livelihoods in both regions. Chapter 20, U.S. Caribbean, Key Message 2. Chapter 27, Hawaii and Pacific Islands, Key Message 4. While some targeted response actions are underway, Figure 1.15, many impacts, including losses of unique coral reef and sea ice ecosystems, can only be avoided by significantly reducing global greenhouse gas emissions, particularly carbon dioxide. Chapter 9, Oceans, Key Message 1. Human health and well-being. Higher temperatures, increasing air quality risks, more frequent and intense extreme weather and climate-related events, increases in coastal flooding, disruption of ecosystem services, and other changes increasingly threaten the health and well-being of the American people, particularly populations that are already vulnerable. Future climate change is expected to further disrupt many areas of life, exacerbating existing challenges and revealing new risks to health and prosperity. Rising temperatures pose a number of threats to human health and quality of life. Figure 1.16. Higher temperatures in the summer are linked directly to an increased risk of illness and death, particularly among older adults, pregnant women, and children. Chapter 18, Northeast, Box 18.3. With continued warming, cold-related deaths are projected to decrease, and heat-related deaths are projected to increase. In most regions, the increases in heat-related deaths are expected to outpace the reductions in cold-related deaths. Chapter 14, Human Health, Key Message 1. Rising temperatures are expected to reduce electricity generation capacity while increasing energy demands and costs, which can, in turn, lead to power outages and blackouts. Chapter 4, Energy, Key Message 1. Chapter 11, Urban, Regional Summary, Figure 11.2. These changes strain household budgets, increase people's exposure to heat, and limit delivery of medical and social services. Risks from heat stress are higher for people without access to housing with sufficient insulation or air conditioning. Chapter 11, Urban, Key Message 1. Changes in temperature and precipitation can increase air quality risks from wildfire and ground-level ozone, smog. Projected increases in wildfire activity due to climate change would further degrade air quality, resulting in increased health risks and impacts on quality of life. Chapter 13, Air Quality, Key Message 2. Chapter 14, Human Health, Key Message 1. Unless counteracting efforts to improve air quality are implemented, climate change is expected to worsen ozone pollution across much of the country, with adverse impacts on human health. Figure 1.21, Chapter 13, Air Quality, Key Message 1. Earlier spring arrival, warmer temperatures, changes in precipitation, and higher carbon dioxide concentrations can also increase exposure to airborne pollen allergens. The frequency and severity of allergic illnesses, including asthma and hay fever, are expected to increase as a result of a changing climate. Chapter 13, Air Quality, Key Message 3. Rising air and water temperatures and changes in extreme weather and climate-related events are expected to increase exposure to waterborne and foodborne diseases, affecting food and water safety. The geographic range and distribution of disease-carrying insects and pests are projected to shift as climate changes, which could expose more people in North America to ticks that carry Lyme disease and mosquitoes that transmit viruses such as West Nile, chikungunya, dengue, and Zika. Chapter 14, Human Health, Key Message 1. Chapter 16, International, Key Message 4. Mental health consequences can result from exposure to climate or extreme weather-related events, some of which are projected to intensify as warming continues. Chapter 14, Human Health, Key Message 1. Coastal city flooding, as a result of sea level rise and hurricanes, for example, can result in forced evacuation, with adverse effects on family and community stability as well as mental and physical health. Chapter 11, Urban, Key Message 1. In urban areas, disruptions in food supply or safety related to extreme weather or climate-related events are expected to disproportionately impact those who already experience food insecurity. Chapter 11, Urban, Key Message 3. Indigenous peoples have historical and cultural relationships with ancestral lands, ecosystems, and culturally important species that are threatened by climate change. Chapter 15, Tribes, Key Message 1, Chapter 19, Southeast, Key Message 4, Case Study, Mountain Ramps, Chapter 24, Northwest, Key Message 5. Climate change is expected to compound existing physical health issues in indigenous communities, in part due to the loss of traditional foods and practices, and in some cases, the mental stress from permanent community displacement. Chapter 14, Human Health, Key Message 2. Chapter 15, Tribes, Key Message 2. Throughout the United States, indigenous peoples are considering or actively pursuing relocation as an adaptation strategy in response to climate-related disasters, more frequent flooding, loss of land due to erosion, or as livelihoods are compromised by ecosystem shifts linked to climate change. Chapter 15, Tribes, Key Message 3. In Louisiana, a federal grant is being used to relocate the tribal community of Isle de Jean Charles in response to severe land loss, sea level rise, and coastal flooding. Figure 1.17. Chapter 19, Southeast, Key Message 2, Case Study, A Lesson Learned for Community Resettlement. In Alaska, coastal native communities are already experiencing heightened erosion driven by declining sea ice, rising sea levels, and warmer waters. Figure 1.18. Coastal and river erosion and flooding, in some cases, will require parts of communities, or even entire communities, to relocate to safer terrain. Chapter 26, Alaska, Key Message 2. Combined with other stressors, sea level rise, coastal storms, and the deterioration of coral reef and mangrove ecosystems, put the long-term habitability of coral atolls in the Hawaii and U.S.-affiliated Pacific Islands region at risk, introducing issues of sovereignty, human and national security, and equity. Chapter 27, Hawaii and Pacific Islands, Key Message 6. Box 1.3, Interconnected Impacts of Climate Change. The impacts of climate change and extreme weather on natural and built systems are often considered from the perspective of individual sectors. How does a changing climate impact water resources, the electric grid, or the food system? None of these sectors, however, exists in isolation. The natural, built, and social systems we rely on are all interconnected, and impacts and management choices within one sector may have cascading effects on the others. Chapter 17, Complex Systems, Key Message 1. For example, wildfire trends in the western United States are influenced by rising temperatures and changing precipitation patterns, pest populations, and land management practices. As humans have moved closer to forest lands, increased fire suppression practices have reduced natural fires and led to denser vegetation, resulting in fires that are larger and more damaging when they do occur. Figures 1.5 and 1.2k. Chapter 6, Forests, Key Message 1. Warmer winters have led to increased pest outbreaks and significant tree kills, with varying feedbacks on wildfire. Increased wildfire driven by climate change is projected to increase costs associated with health effects, loss of homes and other property, wildfire response, and fuel management. Failure to anticipate these interconnected impacts can lead to missed opportunities for effectively managing risks within a single sector and may actually increase risks to other sectors. Planning around wildfire risk and other risks affected by climate change entails the challenge of accounting for all of these influences and how they interact with one another. See Chapter 17, Complex Systems, Box 17.4. New to this edition of the NCA, Chapter 17, Complex Systems, highlights several examples of interconnected impacts and documents how a multi-sector perspective and joint management of systems can enhance resilience to a changing climate. It is often difficult or impossible to quantify and predict how all relevant processes and interactions in interconnected systems will respond to climate change. Non-climate influences, such as population changes, add to the challenges of projecting future outcomes. Chapter 17, Complex Systems, Key Message 2. Despite these challenges, there are opportunities to learn from experience to guide future risk management decisions. Valuable lessons can be learned retrospectively. After Superstorm Sandy in 2012, for example, the mayor of New York City initiated a climate change adaptation task force that brought together stakeholders from several sectors, such as water, transportation, energy, and communications, to address the interdependencies among them. Chapter 17, Complex Systems, Box 17.1, Key Message 3. End of Box 1.3. Box 1.4, How Climate Change Around the World Affects the United States. The impacts of changing weather and climate patterns beyond U.S. international borders affect those living in the United States, often in complex ways that can generate both challenges and opportunities. The International Chapter, Chapter 16, new to this edition of the NCA, assesses our current understanding of how global climate change, natural variability, and associated extremes are expected to impact, and in some cases are already impacting, U.S. interests, both within and outside of our borders. Current and projected climate-related impacts on our economy include increased risks to overseas operations of U.S. businesses, disruption of international supply chains, and shifts in the availability and prices of commodities. For example, severe flooding in Thailand in 2011 disrupted the supply chains for U.S. electronics manufacturers. Chapter 16, International, Figure 16.1. U.S. firms are increasingly responding to climate-related risks, including through their financial disclosures and partnerships with environmental groups. Chapter 16, International, Key Message 1. Impacts from climate-related events can also undermine U.S. investments in international development by slowing or reversing social and economic progress in developing countries, weakening foreign markets for U.S. exports, and increasing the need for humanitarian assistance and disaster relief efforts. Predictive tools can help vulnerable countries anticipate natural disasters, such as drought, and manage their impacts. For example, the United States and international partners created the Famine Early Warning Systems Network, FEWS-NET, which helped avoid severe food shortages in Ethiopia during a historic drought in 2015. Chapter 16, International, Key Message 2. Natural variability and changes in climate increase risks to our national security by affecting factors that can exacerbate conflict and displacement outside of U.S. borders, such as food and water insecurity and commodity price shocks. More directly, our national security is impacted by damage to U.S. military assets such as roads, runways, and waterfront infrastructure from extreme weather and climate-related events, figures 1.8 and 1.9. The U.S. military is working to both fully understand these threats and incorporate projected climate changes into long-term planning. For example, the Department of Defense has performed a comprehensive, scenario-driven examination of climate risks from sea level rise to all of its coastal military sites, including atolls in the Pacific Ocean. Chapter 16, International, Key Message 3. Finally, the impacts of climate change are already affecting the ecosystems that span our nation's borders and the communities that rely on them. International frameworks for the management of our shared resources continue to be restructured to incorporate risks from these impacts. For example, a joint commission that implements water treaties between the United States and Mexico is exploring adaptive water management strategies that account for the effects of climate change and natural variability on Colorado River water. Chapter 16, International, Key Message 4. End of Box 1.4. End of Section 2. Section 3 of the 4th National Climate Assessment, Volume 2 by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 1, Overview, Part 3. Reducing the Risks of Climate Change. Climate change is projected to significantly affect human health, the economy, and the environment in the United States, particularly in futures with high greenhouse gas emissions and limited or no adaptation. Recent findings reinforce the fact that without substantial and sustained reductions in greenhouse gas emissions and regional adaptation efforts, there will be substantial and far-reaching changes over the course of the 21st century, with negative consequences for a large majority of sectors, particularly towards the end of the century. The impacts and costs of climate change are already being felt in the United States, and changes in the likelihood or severity of some recent extreme weather events can now be attributed with increasingly higher confidence to human-caused warming. See Climate Science Special Report, Chapter 3. Impacts associated with human health, such as premature deaths due to extreme temperatures and poor air quality, are some of the most substantial. Chapter 13, Air Quality, Key Message 1. Chapter 14, Human Health, Key Messages 1 and 4. Chapter 29, Mitigation, Key Message 2. While many sectors face large economic risks from climate change, other impacts can have significant implications for societal or cultural resources. Further, some impacts will very likely be irreversible for thousands of years, including those to species such as corals, Chapter 9 Oceans, Key Message 1, Chapter 27 Hawaii and Pacific Islands, Key Message 4, or that involve the crossing of thresholds, such as the effects of ice sheet disintegration on accelerated sea level rise, leading to widespread effects on coastal development lasting thousands of years. Chapter 29, Mitigation, Key Message 2. Future impacts and risks from climate change are directly tied to decisions made in the present, both in terms of mitigation to reduce emissions of greenhouse gases or remove carbon dioxide from the atmosphere, and adaptation to reduce risks from today's changed climate conditions and prepare for future impacts. Mitigation and adaptation activities can be considered complementary strategies. Mitigation efforts can reduce future risks, while adaptation actions can minimize the consequences of changes that are already happening as a result of past and present greenhouse gas emissions. Many climate change impacts and economic damages in the United States can be substantially reduced through global-scale reductions in greenhouse gas emissions, complemented by regional and local adaptation efforts. Chapter 29, Mitigation, Key Message 4. Our understanding of the magnitude and timing of risks that can be avoided varies by sector, region, and assumptions about how adaptation measures change the exposure and vulnerability of people, livelihoods, ecosystems, and infrastructure. Acting sooner rather than later generally results in lower costs overall for both adaptation and mitigation efforts and can offer other benefits in the near term. Chapter 29, Mitigation, Key Message 3. Since the third National Climate Assessment, NCA3, in 2014, a growing number of states, cities, and businesses have pursued or expanded upon initiatives aimed at reducing greenhouse gas emissions, and the scale of adaptation implementation across the country has increased. However, these efforts do not yet approach the scale needed to avoid substantial damages to the economy, environment, and human health expected over the coming decades. Chapter 28, Adaptation, Key Message 1. Chapter 29, Mitigation, Key Messages 1 and 2. Mitigation. Many activities within the public and private sectors aim for or have the effect of reducing greenhouse gas emissions, such as the increasing use of natural gas in place of coal or the expansion of wind and solar energy to generate electricity. Fossil fuel combustion accounts for approximately 85% of total U.S. greenhouse gas emissions, with agriculture, land cover change, industrial processes, and methane from fossil fuel extraction and processing, as well as from waste, including landfills, wastewater treatment, and composting, accounting for most of the remainder. A number of efforts exist at the federal level to promote low-carbon energy technologies and to increase soil and forest carbon storage. State, local, and tribal government approaches to mitigating greenhouse gas emissions include comprehensive emissions reduction strategies as well as sector and technology-specific policies. See Figure 1.19. Since NCA 3, private companies have increasingly reported their greenhouse gas emissions, announced emissions reductions targets, implemented actions to achieve those targets, and, in some cases, even put an internal price on carbon. Individuals and other organizations are also making choices every day to reduce their carbon footprints. Market forces and technological change, particularly within the electric power sector, have contributed to a decline in U.S. greenhouse gas emissions over the past decade. In 2016, U.S. emissions were at their lowest level since 1994. Power sector emissions were 25% below 2005 levels in 2016, the largest emissions reduction for a sector of the American economy over this time. This decline was in large part due to increases in natural gas and renewable energy generation, as well as enhanced energy efficiency standards and programs. Chapter 4, Energy, Key Message 2. Given these advances in electricity generation, transmission, and distribution, the largest annual sectoral emissions in the United States now come from transportation. As of the writing of this report, business as usual, as in no new policies, projections of U.S. carbon dioxide and other greenhouse gas emissions show flat or declining trajectories over the next decade, with a central estimate of about 15% to 20% reduction below 2005 levels by 2025. Chapter 29, Mitigation, Key Message 1. Recent studies suggest that some of the indirect effects of mitigation actions could significantly reduce, or possibly even completely offset, the potential costs associated with cutting greenhouse gas emissions. Beyond reduction of climate pollutants, there are many benefits, often immediate, associated with greenhouse gas emissions reductions, such as improving air quality and public health, reducing crop damages from ozone, and increasing energy independence and security through increased reliance on domestic sources of energy. Chapter 13, Air Quality, Key Message 4. Chapter 29, Mitigation, Key Message 4. Adaptation. Many types of adaptation actions exist, including changes to business operations, hardening infrastructure against extreme weather, and adjustments to natural resource management strategies. Achieving the benefits of adaptation can require upfront investments to achieve longer-term savings, engaging with different stakeholder interests and values, and planning under uncertainty. In many sectors, adaptation can reduce the cost of climate impacts by more than half. Chapter 28, Adaptation, Key Message 4. Chapter 29, Mitigation, Key Message 4. At the time of NCA 3's release in 2014, its authors found that risk assessment and planning were underway throughout the United States, but that on-the-ground implementation was limited. Since then, the scale and scope of adaptation implementation has increased, including by federal, state, tribal, and local agencies, as well as business, academic, and nonprofit organizations, Figure 1.20. While the level of implementation is now higher, it is not yet common nor uniform across the United States, and the scale of implementation for some effects and locations is often considered inadequate to deal with the projected scale of climate change risks. Communities have generally focused on actions that address risks from current climate variability and recent extreme events, such as making buildings and other assets incrementally less sensitive to climate impacts. Fewer communities have focused on actions to address the anticipated scale of future change and emergent threats, such as reducing exposure by preventing building in high-risk locations or retreating from at-risk coastal areas. Chapter 28, Adaptation, Key Message 1. Many adaptation initiatives can generate economic and social benefits in excess of their costs in both the near and long term. Chapter 28, Adaptation, Key Message 4. Damages to infrastructure, such as road and rail networks, are particularly sensitive to adaptation assumptions, with proactive measures that account for future climate risks estimated to be capable of reducing damages by large fractions. More than half of damages to coastal property are estimated to be avoidable through adaptation measures such as shoreline protection and beach replenishment. Chapter 29, Mitigation, Key Message 4. Considerable guidance is available on actions whose benefits exceed their costs in some sectors, such as adaptation responses to storms and rising seas in coastal zones, to riverine and extreme precipitation flooding, and for agriculture at the farm level, but less so on other actions, such as those aimed at addressing risks to health, biodiversity, and ecosystems services that may provide significant benefits but are not as well understood. Chapter 28, Adaptation, Key Message 4. Effective adaptation can also enhance social welfare in many ways that can be difficult to quantify, including improving economic opportunity, health, equity, national security, education, social connectivity, and sense of place, while safeguarding cultural resources and enhancing environmental quality. Aggregating these benefits into a single monetary value is not always the best approach, and more fundamentally, communities may value benefits differently. Considering various outcomes separately in risk management processes can facilitate participatory planning processes and allow for a specific focus on equity. Prioritizing adaptation actions for populations that face higher risks from climate change, including low-income and marginalized communities, may prove more equitable and lead, for instance, to improved infrastructure in their communities and increase focus on efforts to promote community resilience that can improve their capacity to prepare for, respond to, and recover from disasters. Chapter 28, Adaptation, Key Message 4. A significant portion of climate risk can be addressed by integrating climate adaptation into existing investments, policies, and practices. Integration of climate adaptation into decision processes has begun in many areas, including financial risk reporting, capital investment planning, engineering standards, military planning, and disaster risk management. A growing number of jurisdictions address climate risk in their land use, hazard mitigation, capital improvement, and transportation plans, and a small number of cities explicitly link their coastal and hazard mitigation plans using analysis of future climate risks. However, over the course of this century, and especially under a higher scenario, RCP 8.5, Reducing the risks of climate change may require more significant changes to policy and regulations at all scales: community planning, economic and financial systems, technology applications, and ecosystems. Chapter 28, Adaptation, Key Message 5. Some sectors are already taking actions that go beyond integrating climate risk into current practices. Faced with substantial climate-induced changes in the future, including new invasive species and shifting ranges for native species, ecosystem managers have already begun to adopt new approaches, such as assisted migration and development of wildlife corridors. Chapter 7, Ecosystems, Key Message 2. Many millions of Americans live in coastal areas threatened by sea level rise. In all but the very lowest sea level rise projections, retreat will become an unavoidable option in some areas along the U.S. coastline. Chapter 8, Coastal, Key Message 1. The federal government has granted funds for the relocation of some communities, including the Biloxi Chickamauga Choctaw tribe from Isle de Jean Charles in Louisiana. Figure 1.17. However, the potential need for millions of people and billions of dollars of coastal infrastructure to be relocated in the future creates challenging legal, financial, and equity issues that have not yet been addressed. Chapter 28, Adaptation, Key Message 5. In some areas, lack of historical or current data to inform policy decisions can be a limitation to assessments of vulnerabilities and/or effective adaptation planning. For this National Climate Assessment, this was particularly the case for some aspects of the Alaska, U.S. Caribbean, and Hawaii and U.S. affiliated Pacific Islands regions. In many instances, relying on indigenous knowledges is among the only current means of reconstructing what has happened in the past. To help communities across the United States learn from one another in their efforts to build resilience to a changing climate, this report highlights common climate-related risks and possible response actions across all regions and sectors. What has happened since the last National Climate Assessment? Our understanding of and experience with climate science, impacts, risks, and adaptation in the United States have grown significantly since the third National Climate Assessment, NCA3, advancing our knowledge of key processes in the Earth system, how human and natural forces are changing them, what the implications are for society, and how we can respond. Key scientific advances. Detection and attribution. Significant advances have been made in the attribution of the human influence for individual climate and weather extreme events. See Climate Science Special Report, Chapters 3, 6, 7, and 8. Extreme events and atmospheric circulation. How climate change may affect specific types of extreme events in the United States, and the extent to which atmospheric circulation in the mid-latitudes is changing or is projected to change, possibly in ways not captured by current climate models, are important areas of research where scientific understanding has advanced. See Climate Science Special Report, Chapters 5, 6, 7, and 9. Localized information. As computing resources have grown, projections of future climate from global models are now being conducted at finer scales, with resolution on the order of 15 miles, providing more realistic characterization of intense weather systems, including hurricanes. For the first time in the NCA process, sea level rise projections incorporate geographic variation based on factors such as local land subsidence, ocean currents, and changes in Earth's gravitational field. See Climate Science Special Report, Chapters 9 and 12. Ocean and coastal waters. Ocean acidification, warming, and oxygen loss are all increasing and scientific understanding of the severity of their impacts is growing. Both oxygen loss and acidification may be magnified in some U.S. coastal waters relative to the global average, raising the risk of serious ecological and economic consequences. See Climate Science Special Report, Chapters 2 and 13. Rapid changes for ice on Earth. New observations from many different sources confirm that ice loss across the globe is continuing and, in many cases, accelerating. Since NCA 3, Antarctica and Greenland have continued to lose ice mass, with mounting evidence that mass loss is accelerating. Observations continue to show declines in the volume of mountain glaciers around the world. Annual September minimum sea ice extent in the Arctic Ocean has decreased at a rate of 11% to 16% per decade since the early 1980s, with accelerating ice loss since 2000. The annual sea ice extent minimum for 2016 was the second lowest on record. The sea ice minimums in 2014 and 2015 were also among the lowest on record. See Climate Science Special Report, Chapters 1, 11, and 12. Potential surprises. Both large-scale shifts in the climate system, sometimes called tipping points, and compound extremes have the potential to generate outcomes that are difficult to anticipate and may have high consequences. The more the climate changes, the greater the potential for these surprises. See Climate Science Special Report, Chapter 15. Extreme events. Climate change is altering the characteristics of many extreme weather and climate-related events. Some extreme events have already become more frequent, intense, widespread, or of longer duration, and many are expected to continue to increase or worsen, presenting substantial challenges for built, agricultural, and natural systems. Some storm types, such as hurricanes, tornadoes, and winter storms, are also exhibiting changes that have been linked to climate change, although the current state of the science does not yet permit detailed understanding. See Climate Science Special Report Executive Summary. Individual extreme weather and climate-related events, even those that have not been clearly attributed to climate change by scientific analyses, reveal risks to society and vulnerabilities that mirror those we expect in a warmer world. Non-climate stressors, such as land use changes and shifting demographics, can also amplify the damages associated with extreme events. The National Oceanic and Atmospheric Administration estimates that the United States has experienced $44 billion weather and climate disasters since 2015 through April 6, 2018, incurring costs of nearly $400 billion. Hurricanes. The 2017 Atlantic hurricane season alone is estimated to have caused more than $250 billion in damages and over 250 deaths throughout the U.S. Caribbean, Southeast, and Southern Great Plains. More than 30 inches of rain fell during Hurricane Harvey, affecting 6.9 million people. Hurricane Maria's high winds caused widespread devastation to Puerto Rico's transportation, agriculture, communication, and energy infrastructure. Extreme rainfall of up to 37 inches caused widespread flooding and mudslides across the island. The interruption to commerce and standard living conditions will be sustained for a long period while much of Puerto Rico's infrastructure is rebuilt. Hurricane Irma destroyed 25% of buildings in the Florida Keys. Floods. In August 2016, a historic flood, resulting from 20 to 30 inches of rainfall over several days, devastated a large area of southern Louisiana, causing over $10 billion in damages and 13 deaths. More than 30,000 people were rescued from floodwaters that damaged or destroyed more than 50,000 homes, 100,000 vehicles, and 20,000 businesses. In June 2016, torrential rainfall caused destructive flooding throughout many West Virginia towns, damaging thousands of homes and businesses and causing considerable loss of life. More than 1,500 roads and bridges were damaged or destroyed. The 2015-2016 El Niño poured 11 days of record-setting rainfall on Hawaii, causing severe urban flooding. Drought. In 2015, drought conditions caused about $5 billion in damages across the Southwest and Northwest, as well as parts of the northern Great Plains. California experienced the most severe drought conditions. Hundreds of thousands of acres of farmland remained fallow, and excess groundwater pumping was required to irrigate existing agricultural interests. 2 years later, in 2017, extreme drought caused $2.5 billion in agricultural damages across the northern Great Plains. Field crops, including wheat, were severely damaged, and the lack of feed for cattle forced ranchers to sell off livestock. Wildfires. During the summer of 2015, over 10.1 million acres, an area larger than the entire state of Maryland, burned across the United States, surpassing 2006 for the highest annual total U.S. acreage burned since record-keeping began in 1960. These wildfire conditions were exacerbated by the preceding drought conditions in several states. The most extensive wildfires occurred in Alaska, where 5 million acres burned within the state. In Montana, wildfires burned in excess of 1 million acres. The costliest wildfires occurred in California, where more than 2,500 structures were destroyed by the Valley and Butte fires. Insured losses alone exceeded $1 billion. In October 2017, a historic firestorm damaged or destroyed more than 15,000 homes, businesses, and other structures across California. See Figure 1.5. The Tubbs, Atlas, Nuns, and Redwood Valley fires caused a total of 44 deaths, and their combined destruction represents the costliest wildfire event on record. Tornadoes. In March 2017, a severe tornado outbreak caused damage across much of the Midwest and into the Northeast. Nearly 1 million customers lost power in Michigan alone due to sustained high winds, which affected several states from Illinois to New York. Heat waves. Honolulu experienced 24 days of record-setting heat during the 2015-2016 El Niño event. As a result, the local energy utility issued emergency public service announcements to curtail escalating air conditioning use that threatened the electrical grid. New aspects of this report. Hundreds of states, counties, cities, businesses, universities, and other entities are implementing actions that build resilience to climate-related impacts and risks, while also aiming to reduce greenhouse gas emissions. Many of these actions have been informed by new climate-related tools and products developed through the U.S. Global Change Research Program, USGCRP, since NCA 3, see Appendix 3, Scenario Products and Data Tools. We briefly highlight a few of them here. In addition, several structural changes have been introduced to the report, and new methods used in response to stakeholder needs for more localized information and to address key gaps identified in NCA 3. The third National Climate Assessment remains a valuable and relevant resource. This report expands upon our knowledge and experience as presented 4 years ago. Climate Science Special Report. Early in the development of NCA 4, experts and administration officials recognized that conducting a comprehensive physical science assessment, Volume 1, in advance of an impacts assessment, Volume 2, would allow one to inform the other. The Climate Science Special Report, released in November 2017, is Volume 1 of NCA 4 and represents the most thorough and up-to-date assessment of climate science in the United States and underpins the findings of this report. Its findings are summarized in Chapter 2, Our Changing Climate. See the Key Scientific Advances section in this box and Box 2.3 in Chapter 2 for more detail. Scenario products. As described in more detail in Appendix 3, Data Tools and Scenario Products, federal interagency groups developed a suite of high-resolution scenario products that span a range of plausible future changes in key environmental variables through at least 2100. These USGCRP scenario products help ensure consistency across the report and improve the ability to synthesize across chapters. Where possible, authors have used these scenario products to frame uncertainty in future climate as it relates to the risks that are the focus of their chapters. In addition, the Indicators Interagency Working Group has developed an indicators platform that uses observations or calculations to monitor conditions or trends in the Earth system, just as businesses might use the unemployment index as an indicator of economic conditions. See Figure 1.2. Localized information. With the increased focus on local and regional information in NCA 4, U.S. GCRP agencies developed two additional products that not only inform this assessment, but can serve as valuable decision support tools. The first are the State Climate Summaries, a peer-reviewed collection of climate change information covering all 10 NCA 4 regions at the state level. In addition to standard data on observed and projected climate change, each state climate summary contains state-specific changes and their related impacts, as well as a suite of complementary graphics. The second product is the U.S. Climate Resilience Toolkit, which offers data-driven tools, information, and subject matter expertise from across the federal government in one easy-to-use location, so Americans are better able to understand the climate-related risks and opportunities impacting their communities and can make more informed decisions on how to respond. In particular, the case studies showcase examples of climate change impacts and accompanying response actions that complement those presented in Figure 1.1 and allow communities to learn how to build resilience from one another. New chapters. In response to public feedback on NCA 3 and input solicited in the early stages of this assessment, a number of significant structural changes have been made. Most fundamentally, the balance of the report's focus has shifted from national-level chapters to regional chapters in response to a growing desire for more localized information on impacts. Building on this theme, the Great Plains chapter has been split into northern and southern chapters, chapters 22 and 23, along the Kansas-Nebraska border. In addition, the U.S. Caribbean is now featured as a separate region in this report, chapter 20, focusing on the unique impacts, risks, and response capabilities in Puerto Rico and the U.S. Virgin Islands. Public input also requested greater international context in the report, which has been addressed through two new additions. A new chapter focuses on topics including the effects of climate change on U.S. trade and businesses, national security, and U.S. humanitarian assistance and disaster relief, Chapter 16. A new international appendix, Appendix 4, presents a number of illustrative examples of how other countries have conducted national climate assessments, putting our own effort into a global context. Given recent scientific advances, some emerging topics warranted a more visible platform in NCA 4. A new chapter on air quality, Chapter 13, examines how traditional air pollutants are affected by climate change. A new chapter on sector interactions, multiple stressors, and complex systems, Chapter 17, evaluates climate-related risks to interconnected human and natural systems that are increasingly vulnerable to cascading impacts and highlights advances in analyzing how these systems will interact with and respond to a changing environment. See Box 1.3. Integrating economics. This report, to a much greater degree than previous national climate assessments, includes broader and more systematic quantification of climate change impacts in economic terms. While this is an emerging body of literature that is not yet reflected in each of the 10 NCA regions, it represents a valuable advancement in our understanding of the financial costs and benefits of climate change impacts. Figure 1.21 provides an illustration of the type of economic information that is integrated throughout this report. It shows the financial damages avoided under a lower scenario, RCP 4.5, versus a higher scenario, RCP 8.5. End of Section 3. Section 4 of the 4th National Climate Assessment, Volume 2, by USG CRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 2, Our Changing Climate. Key Message 1. Observed changes in global climate. Global climate is changing rapidly compared to the pace of natural variations in climate that have occurred throughout Earth's history. Global average temperature has increased by about 1.8 degrees Fahrenheit from 1901 to 2016, and observational evidence does not support any credible natural explanations for this amount of warming. Instead, the evidence consistently points to human activities, especially emissions of greenhouse or heat-trapping gases, as the dominant cause. Key Message 2. Future changes in global climate. Earth's climate will continue to change over the century and beyond. Past mid-century, how much the climate changes will depend primarily on global emissions of greenhouse gases and on the response of Earth's climate system to human-induced warming. With significant reductions in emissions, global temperature increase could be limited to 3.6 degrees Fahrenheit, 2 degrees Celsius, or less compared to pre-industrial temperatures. Without significant reductions, annual average global temperatures could increase by 9 degrees Fahrenheit, 5 degrees Celsius, or more by the end of this century compared to pre-industrial temperatures. Key Message 3. Warming and acidifying oceans. The world's oceans have absorbed 93% of the excess heat from human-induced warming since the mid-20th century and are currently absorbing more than a quarter of the carbon dioxide emitted to the atmosphere annually from human activities, making the oceans warmer and more acidic. Increasing sea surface temperatures, rising sea levels, and changing patterns of precipitation, winds, nutrients, and ocean circulation are contributing to overall declining oxygen concentrations in many locations. Key Message 4. Rising global sea levels. Global average sea level has risen by about 7 to 8 inches about 16 to 21 centimeters, since 1900, with almost half this rise occurring since 1993, as oceans have warmed and land-based ice has melted. Relative to the year 2000, sea level is very likely to rise 1 to 4 feet, 0.3 to 1.3 meters, by the end of the century. Emerging science regarding Antarctic ice sheet stability suggests that, for higher scenarios, a rise exceeding 8 feet, 2.4 meters, by 2100 is physically possible, although the probability of such an extreme outcome cannot currently be assessed. Key Message 5: Increasing U.S. temperatures. Annual average temperature over the contiguous United States has increased by 1.2 degrees Fahrenheit, 0.7 degrees Celsius, over the last few decades, and by 1.8 degrees Fahrenheit, 1 degree Celsius, relative to the beginning of the last century. Additional increases in annual average temperature of about 2.5 degrees Fahrenheit, 1.4 degrees Celsius, are expected over the next few decades, regardless of future emissions, and increases ranging from 3 degrees Fahrenheit to 12 degrees Fahrenheit, 1.6 to 6.6 degrees Celsius, are expected by the end of century, depending on whether the world follows a higher or lower future scenario, with proportionally greater changes in high temperature extremes. Key Message 6: Changing U.S. precipitation. Annual precipitation since the beginning of the last century has increased across most of the northern and eastern United States and decreased across much of the southern and western United States. Over the coming century, significant increases are projected in winter and spring over the northern Great Plains, the upper Midwest, and the Northeast. Observed increases in the frequency and intensity of heavy precipitation events in most parts of the United States are projected to continue. Surface soil moisture over most of the United States is likely to decrease, accompanied by large declines in snowpack in the western United States and shifts to more winter precipitation falling as rain rather than snow. Key Message 7: Rapid Arctic change. In the Arctic, annual average temperatures have increased more than twice as fast as the global average, accompanied by thawing permafrost and loss of sea ice and glacier mass. Arctic-wide glacial and sea ice loss is expected to continue. By mid-century, it is very likely that the Arctic will be nearly free of sea ice in late summer. Permafrost is expected to continue to thaw over the coming century as well, and the carbon dioxide and methane released from thawing permafrost has the potential to amplify human-induced warming, possibly significantly. Key Message 8: Changes in severe storms. Human-induced change is affecting atmospheric dynamics and contributing to the poleward expansion of the tropics and the northward shift in northern hemisphere winter storm tracks since 1950. Increases in greenhouse gases and decreases in air pollution have contributed to increases in Atlantic hurricane activity since 1970. In the future, Atlantic and eastern North Pacific hurricane rainfall and intensity are projected to increase, as are the frequency and severity of landfalling atmospheric rivers on the West Coast. Key Message 9: Increases in coastal flooding. Regional changes in sea level rise and coastal flooding are not evenly distributed across the United States. Ocean circulation changes, sinking land, and Antarctic ice melt will result in greater than average sea level rise for the Northeast and western Gulf of Mexico under lower scenarios, and most of the U.S. coastline other than Alaska under higher scenarios. Since the 1960s, Sea level rise has already increased the frequency of high tide flooding by a factor of 5 to 10 for several U.S. coastal communities. The frequency, depth, and extent of tidal flooding are expected to continue to increase in the future, as is the more severe flooding associated with coastal storms such as hurricanes and nor'easters. Key Message 10: Long-term changes. The climate changes resulting from human-caused emissions of carbon dioxide will persist for decades to millennia. Self-reinforcing cycles within the climate system have the potential to accelerate human-induced change and even shift Earth's climate system into new states that are very different from those experienced in the recent past. Future changes outside the range projected by climate models cannot be ruled out, and due to their systematic tendency to underestimate temperature change during past warm periods, models may be more likely to underestimate than to overestimate long-term future change. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/climate. End of section 4. Section 5 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 3, Water. Key Message 1: Changes in water quantity and quality. Significant changes in water quantity and quality are evident across the country. These changes, which are expected to persist, present an ongoing risk to coupled human and natural systems and related ecosystem services. Variable precipitation and rising temperature are intensifying droughts, increasing heavy downpours, and reducing snowpack. Reduced snow-to-rain ratios are leading to significant differences between the timing of water supply and demand. Groundwater depletion is exacerbating drought risk. Surface water quality is declining as water temperature increases and more frequent high-intensity rainfall events mobilize pollutants such as sediments and nutrients. Key Message 2: Deteriorating water infrastructure at risk. Deteriorating water infrastructure compounds the climate risk faced by society. Extreme precipitation events are projected to increase in a warming climate and may lead to more severe floods and greater risk of infrastructure failure in some regions. Infrastructure design, operation, financing principles, and regulatory standards typically do not account for a changing climate. Current risk management does not typically consider the impact of compound extremes, co-occurrence of multiple events, and the risk of cascading infrastructure failure. Key Message 3: Water management in a changing future. Water management strategies designed in view of an evolving future we can only partially anticipate will help prepare the nation for water and climate-related risks of the future. Current water management and planning principles typically do not address risk that changes over time, leaving society exposed to more risk than anticipated. While there are examples of promising approaches to manage climate risk, the gap between research and implementation, especially in view of regulatory and institutional constraints, remains a challenge. Ensuring a reliable supply of clean fresh water to individuals, communities, and ecosystems, together with effective management of floods and droughts, is the foundation of human and ecological health. The water sector is also central to the economy and contributes significantly to the resilience of many other sectors, including agriculture, energy, urban environments, and industry. Water systems face considerable risk, even without anticipated future climate changes. Limited surface water storage, as well as a limited ability to make use of long-term drought forecasts and to trade water across uses and basins, has led to a significant depletion of aquifers in many regions of the United States. Across the nation, much of the critical water and wastewater infrastructure is nearing the end of its useful life. To date, no comprehensive assessment exists of the climate-related vulnerability of U.S. water infrastructure, including dams, levees, aqueducts, sewers, and water and wastewater distribution and treatment systems, the potential resulting damages, or the cost of reconstruction and recovery. Paleoclimate information, reconstructions of past climate derived from ice cores or tree rings, shows that over the last 500 years, North America has experienced pronounced wet-dry regime shifts that sometimes persisted for decades. Because such protracted exposures to extreme floods or droughts in different parts of the country are extraordinary compared to events experienced in the 20th century, they are not yet incorporated in water management principles and practice. Anticipated future climate change will exacerbate this risk in many regions. A central challenge to water planning and management is learning to plan for plausible future climate conditions that are wider in range than those experienced in the 20th century. Doing so requires approaches that evaluate plans over many possible futures instead of just one, incorporate real-time monitoring and forecast products to better manage extremes when they occur, and update policies and engineering principles with the best available geoscience-based understanding of planetary change. While this represents a break from historical practice, recent examples of adaptation responses undertaken by large water management agencies, including major metropolitan water utilities and the U.S. Corps of Engineers, are promising. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/water. End of section 5. Section 6 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 4, Energy Supply, Delivery, and Demand. Key Message 1. Nationwide Impacts on Energy. The nation's energy system is already affected by extreme weather events, and due to climate change, it is projected to be increasingly threatened by more frequent and longer-lasting power outages affecting critical energy infrastructure and creating fuel availability and demand imbalances. The reliability, security, and resilience of the energy system underpin virtually every sector of the U.S. economy. Cascading impacts on other critical sectors could affect economic and national security. Key Message 2. Changes in energy system affect vulnerabilities. Changes in energy technologies, markets, and policies are affecting the energy system's vulnerabilities to climate change and extreme weather. Some of these changes increase reliability and resilience, while others create additional vulnerabilities. Changes include the following. Natural gas is increasingly used as fuel for power plants. Renewable resources are becoming increasingly cost competitive with an expanding market share, and a resilient energy supply is increasingly important as telecommunications, transportation, and other critical systems are more interconnected than ever. Key Message 3: Improving Energy System Resilience. Actions are being taken to enhance energy security, reliability, and resilience with respect to the effects of climate change and extreme weather. This progress occurs through improved data collection, modeling, and analysis to support resilience planning, private and public-private partnerships supporting coordinated action, and both development and deployment of new innovative energy technologies for adapting energy assets to extreme weather hazards. Although barriers exist, opportunities remain to accelerate the pace, scale, and scope of investments in energy systems resilience. The nation's economic security is increasingly dependent on an affordable and reliable supply of energy. Every sector of the economy depends on energy, from manufacturing to agriculture, banking, healthcare, telecommunications, and transportation. Increasingly, climate change and extreme weather events are affecting the energy system, threatening more frequent and longer-lasting power outages and fuel shortages. Such events can have cascading impacts on other critical sectors, potentially affecting the nation's economic and national security. At the same time, the energy sector is undergoing substantial policy, market, and technology-driven changes that are projected to affect these vulnerabilities. The impacts of extreme weather and climate change on energy systems will differ across the United States. Low-lying energy facilities and systems located along inland waters or near the coasts are at elevated risk of flooding from more intense precipitation, rising sea levels, and more intense hurricanes. Increases in the severity and frequency of extreme precipitation are projected to affect inland energy infrastructure in every region. Rising temperatures and extreme heat events are projected to reduce the generation capacity of thermoelectric power plants and decrease the efficiency of the transmission grid. Rising temperatures are projected to also drive greater use of air conditioning and increase electricity demand, likely resulting in increases in electricity costs. The increase in annual electricity demand across the country for cooling is offset only marginally by the relatively small decline in electricity demand for heating. Extreme cold events, including ice and snow events, can damage power lines and impact fuel supplies. Severe drought, along with changes in evaporation, reductions in mountain snowpack, and shifting mountain snowmelt timing, is projected to reduce hydropower production and threaten oil and gas drilling and refining, as well as thermoelectric power plants that rely on surface water for cooling. Drier conditions are projected to increase the risk of wildfires and damage to energy production and generation assets and the power grid. At the same time, the nature of the energy system itself is changing. Low carbon-emitting natural gas generation has displaced coal generation due to the rising production of low-cost, unconventional natural gas, in part supported by federal investment in research and development. In the last 10 years, the share of generation from natural gas increased from 20% to over 30%, while coal has declined from nearly 50% to around 30%. Over this same time, generation from wind and solar has grown from less than 1% to over 5%, due to a combination of technological progress, dramatic cost reductions, and federal and state policies. It is possible to address the challenges of a changing climate and energy system, and both industry and governments at the local, state, regional, federal, and tribal levels are taking actions to improve the resilience of the nation's energy system. These actions include planning and operational measures that seek to anticipate climate impacts and prevent or respond to damages more effectively, as well as hardening measures to protect assets from damage during extreme events. Resilience actions can have co-benefits, such as developing and deploying new innovative energy technologies that increase resilience and reduce emissions. While steps are being taken, an escalation of the pace, scale, and scope of efforts is needed to ensure the safe and reliable provision of energy and to establish a climate-ready energy system to address present and future risks. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/energy. End of section 6. Section 7 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 5. Land Cover and Land Use Change. Key Message 1. Land cover changes influence weather and climate. Changes in land cover continue to impact local to global scale weather and climate by altering the flow of energy, water, and greenhouse gases between the land and the atmosphere. Reforestation can foster localized cooling, while in urban areas, continued warming is expected to exacerbate urban heat island effects. Key Message 2. Climate impacts on land and ecosystems. Climate change affects land use and ecosystems. Climate change is expected to directly and indirectly impact land use and cover by altering disturbance patterns, species distributions, and the suitability of land for specific uses. The composition of the natural and human landscapes and how society uses the land affects the ability of the nation's ecosystems to provide essential goods and services. Climate can affect and be affected by changes in land cover, the physical features that cover the land, such as trees or pavement, and land use, human management and activities on land, such as mining or recreation. A forest, for instance, would likely include tree cover but could also include areas of recent tree removals currently covered by open grass areas. Land cover and use are inherently coupled. Changes in land use practices can change land cover, and land cover enables specific land uses. Understanding how land cover, use, condition, and management vary in space and time is challenging. Changes in land cover can occur in response to both human and climate drivers. For example, demand for new settlements often results in the permanent loss of natural and working lands, which can result in localized changes in weather patterns, temperature, and precipitation. Aggregated over large areas, these changes have the potential to influence Earth's climate by altering regional and global circulation patterns, changing the albedo, reflectivity, of Earth's surface, and changing the amount of carbon dioxide, CO2, in the atmosphere. Conversely, climate change can also influence land cover, resulting in a loss of forest cover from climate-related increases in disturbances, the expansion of woody vegetation into grasslands, and the loss of beaches due to coastal erosion amplified by rises in sea level. Land use is also changed by both human and climate drivers. Land use decisions are traditionally based on short-term economic factors. Land use changes are increasingly being influenced by distant forces due to the globalization of many markets. Land use can also change due to local, state, and national policies, such as programs designed to remove cultivation from highly erodible land to mitigate degradation, legislation to address sea level rise in local comprehensive plans, or policies that reduce the rate of timber harvest on federal lands. Technological innovation has also influenced land use change. With the expansion of cultivated lands from the development of irrigation technologies and, more recently, decreases in demand for agricultural land due to increases in crop productivity. The recent expansion of oil and gas extraction activities throughout large areas of the United States demonstrates how policy, economics, and technology can collectively influence and change land use and land cover. Decisions about land use, cover, and management can help determine society's ability to mitigate and adapt to climate change. For a full chapter, including references and traceable accounts, see https://nca2018.global.change.gov/chapter/land-changes. End of section 7. Section 8 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 6, Forests. Key Message 1. Ecological Disturbances and Forest Health. It is very likely that more frequent extreme weather events will increase the frequency and magnitude of severe ecological disturbances, driving rapid, months to years, and often persistent changes in forest structure and function across large landscapes. It is also likely that other changes, resulting from gradual climate change and less severe disturbances, will alter forest productivity and health, and the distribution and abundance of species at longer timescales, decades to centuries. Key Message 2. Ecosystem Services. It is very likely that climate change will decrease the ability of many forest ecosystems to provide important ecosystem services to society. Tree growth and carbon storage are expected to decrease in most locations as a result of higher temperatures, more frequent drought, and increased disturbances. The onset and magnitude of climate change effects on water resources in forest ecosystems will vary, but are already occurring in some regions. Key Message 3. Adaptation. Forest management activities that increase the resilience of U.S. forests to climate change are being implemented, with a broad range of adaptation options for different resources, including applications in planning. The future pace of adaptation will depend on how effectively social, organizational, and economic conditions support implementation. Forests on public and private lands provide benefits to the natural environment, as well as economic benefits and ecosystem services to people in the United States and globally. The ability of U.S. forests to continue to provide goods and services is threatened by climate change and associated increases in extreme events and disturbances. For example, severe drought and insect outbreaks have killed hundreds of millions of trees across the United States over the past 20 years, and wildfires have burned at least 3.7 million acres annually in all but 3 years from 2000 to 2016. Recent insect-caused mortality appears to be outside the historical context and is likely related to climate change. However, it is unclear if the apparent climate-related increase in fire-caused tree mortality is outside the range of what has been observed over centuries of wildfire occurrence. A warmer climate will decrease tree growth in most forests that are water limited, for example, low elevation ponderosa pine forests, but will likely increase growth in forests that are energy limited, for example, subalpine forests, where long-lasting snowpack and cold temperatures limit the growing season. Drought and extreme high temperatures can cause heat-related stress in vegetation and, in turn, reduce forest productivity and increase mortality. The rate of climate warming is likely to influence forest health, that is, the extent to which ecosystem processes are functioning within their range of historic variation, and competition between trees, which will affect the distributions of some species. Large-scale disturbances, over thousands to hundreds of thousands of acres, that cause rapid change, over days to years, and more gradual climate change effects, over decades, will alter the ability of forests to provide ecosystem services, although alterations will vary greatly depending on the tree species and local biophysical conditions. For example, whereas crown fires, forest fires that spread from treetop to treetop, will cause extensive areas of tree mortality in dense, dry forests in the western United States that have not experienced wildfire for several decades, increased fire frequency is expected to facilitate the persistence of sprouting hardwood species, such as quaking aspen in western mountains and fire-tolerant pine and hardwood species in the eastern United States. See regional chapters for more detail on variation across the United States. Drought, heavy rainfall, altered snowpack, and changing forest conditions are increasing the frequency of low summer stream flow, winter and spring flooding, and low water quality in some locations, with potential negative impacts on aquatic resources and on water supplies for human communities. From 1990 to 2015, U.S. forests sequestered 742 teragrams (Tg) of carbon dioxide (CO2) per year, offsetting approximately 11% of the nation's CO2 emissions. U.S. forests are projected to continue to store carbon, but at declining rates, as affected by both land use and lower CO2 uptake as forests get older. However, carbon accumulation in surface soils at depths of 0 to 4 inches can mitigate the declining carbon sink of U.S. forests if reforestation is routinely implemented at large spatial scales. Implementation of climate-informed resource planning and management on forest lands has progressed significantly over the past decade. The ability of society and resource management to continue to adapt to climate change will be determined primarily by socioeconomic factors and organizational capacity. A viable forest-based workforce can facilitate timely actions that minimize negative effects of climate change. Ensuring the continuing health of forest ecosystems and, where desired and feasible, keeping forest land in forest cover are key challenges for society. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/forests. Section 9 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 7, ecosystems, ecosystem services, and biodiversity. Key Message 1. Impacts on species and populations. Climate change continues to impact species and populations in significant and observable ways. Terrestrial, freshwater, and marine organisms are responding to climate change by altering individual characteristics, the timing of biological events, and their geographic ranges. Local and global extinctions may occur when climate change outpaces the capacity of species to adapt. Key Message 2. Impacts on ecosystems. Climate change is altering ecosystem productivity, exacerbating the spread of invasive species, and changing how species interact with each other and with their environment. These changes are reconfiguring ecosystems in unprecedented ways. Key Message 3. Ecosystem services at risk. The resources and services that people depend on for their livelihoods, sustenance, protection, and well-being are jeopardized by the impacts of climate change on ecosystems. Fundamental changes in agricultural and fisheries production, the supply of clean water, protection from extreme events, and culturally valuable resources are occurring. Key Message 4. Challenges for natural resource management. Traditional natural resource management strategies are increasingly challenged by the impacts of climate change. Adaptation strategies that are flexible, consider interacting impacts of climate and other stressors, and are coordinated across landscape scales are progressing from theory to application. Significant challenges remain to comprehensively incorporate climate adaptation planning into mainstream natural resource management, as well as to evaluate the effectiveness of implemented actions. Biodiversity, the variety of life on Earth, provides vital services that support and improve human health and well-being. Ecosystems, which are composed of living things that interact with the physical environment, provide numerous essential benefits to people. These benefits, termed ecosystem services, encompass four primary functions: provisioning materials such as food and fiber, regulating critical parts of the environment such as water quality and erosion control, providing cultural services such as recreational opportunities and aesthetic value, and providing supporting services such as nutrient cycling. Climate change poses many threats and potential disruptions to ecosystems and biodiversity, as well as to the ecosystem services on which people depend. Building on the findings of the third National Climate Assessment, NCA 3, this chapter provides additional evidence that climate change is significantly impacting ecosystems and biodiversity in the United States. Mounting evidence also demonstrates that climate change is increasingly compromising the ecosystem services that sustain human communities, economies, and well-being. Both human and natural systems respond to change, but their ability to respond and thrive under new conditions is determined by their adaptive capacity, which may be inadequate to keep pace with rapid change. Our understanding of climate change impacts and the responses of biodiversity and ecosystems has improved since NCA 3. The expected consequences of climate change will vary by region, species, and ecosystem type. Management responses are evolving as new tools and approaches are developed and implemented. However, they may not be able to overcome the negative impacts of climate change. Although efforts have been made since NCA 3 to incorporate climate adaptation strategies into natural resource management, significant work remains to comprehensively implement climate-informed planning. This chapter presents additional evidence for climate change impacts to biodiversity, ecosystems, and ecosystem services, reflecting increased confidence in the findings reported in NCA 3. The chapter also illustrates the complex and interrelated nature of climate change impacts to biodiversity, ecosystems, and the services they provide. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/ecosystems. End of section 9. Section 10 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 8, Coastal Effects. Key Message 1. Coastal economies and property are already at risk. America's trillion-dollar coastal property market and public infrastructure are threatened by the ongoing increase in the frequency, depth, and extent of tidal flooding due to sea level rise, with cascading impacts to the larger economy. Higher storm surges due to sea level rise and the increased probability of heavy precipitation events exacerbate the risk. Under a higher scenario, RCP 8.5, many coastal communities will be transformed by the latter part of this century, and even under lower scenarios, RCP 4.5 or RCP 2.6, many individuals and communities will suffer financial impacts as chronic high tide flooding leads to higher costs and lower property values. Actions to plan for and adapt to more frequent, widespread, and severe coastal flooding would decrease direct losses and cascading economic impacts. Key Message 2. Coastal environments are already at risk. Fisheries, tourism, human health, and public safety depend on healthy coastal ecosystems that are being transformed, degraded, or lost due in part to climate change impacts, particularly sea level rise and higher numbers of extreme weather events. Restoring and conserving coastal ecosystems and adopting natural and nature-based infrastructure solutions can enhance community and ecosystem resilience to climate change, help to ensure their health and vitality, and decrease both direct and indirect impacts of climate change. Key Message 3. Social challenges intensified. As the pace and extent of coastal flooding and erosion accelerate, climate change impacts along our coasts are exacerbating pre-existing social inequities as communities face difficult questions about determining who will pay for current impacts and future adaptation and mitigation strategies, and if, how, or when to relocate. In response to actual or projected climate change losses and damages, coastal communities will be among the first in the nation to test existing climate-relevant legal frameworks and policies against these impacts, and thus will establish precedents that will affect both coastal and non-coastal regions. The Coasts chapter of the 3rd National Climate Assessment, published in 2014, focused on coastal lifelines at risk, economic disruption, uneven social vulnerability, and vulnerable ecosystems. This Coastal Effects chapter of the 4th National Climate Assessment updates those themes with a focus on integrating the socioeconomic and environmental impacts and consequences of a changing climate. Specifically, the chapter builds on the threat of rising sea levels, exacerbating tidal and storm surge flooding, the state of coastal ecosystems, and the treatment of social vulnerability by introducing the implications for social equity. U.S. coasts are dynamic environments and economically vibrant places to live and work. As of 2013, coastal shoreline counties were home to 133.2 million people, or 42% of the population. The coasts are economic engines that support jobs in defense, fishing, transportation, and tourism industries, contribute substantially to the U.S. gross domestic product, and serve as hubs of commerce, with seaports connecting the country with global trading partners. Coasts are home to diverse ecosystems such as beaches, intertidal zones, reefs, seagrasses, salt marshes, estuaries, and deltas that support a range of important services, including fisheries, recreation, and coastal storm protection. U.S. coasts span 3 oceans, as well as the Gulf of Mexico, the Great Lakes, and Pacific and Caribbean islands. The social, economic, and environmental systems along the coasts are being affected by climate change. Threats from sea level rise, SLR, are exacerbated by dynamic processes such as high tide and storm surge flooding. Chapter 19, Southeast, Key Message 2. Erosion, Chapter 26, Alaska, Key Message 2. Waves and their effects, saltwater intrusion into coastal aquifers, and elevated groundwater tables. Chapter 27, Hawaii and Pacific Islands, Key Message 1. Chapter 3, Water, Key Message 1. Local rainfall, Chapter 3, Water, Key Message 1. River runoff, Chapter 3, Water, Key Message 1. Increasing water and surface air temperatures, Chapter 9, Oceans, Key Message 3. And ocean acidification. See Chapter 2, Climate, Key Message 3, and Chapter 9, Oceans, Key Messages 1, 2, and 3, for more information on ocean acidification, hypoxia, and ocean warming. Although storms, floods, and erosion have always been hazards, in combination with rising sea levels, they now threaten approximately $1 trillion in national wealth held in coastal real estate and the continued viability of coastal communities that depend on coastal water, land, and other resources for economic health and cultural integrity. Chapter 15, Tribes, Key Messages 1 and 2. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/coastal. End of section 10. Section 11 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 9, Oceans and Marine Resources. Key Message 1. Ocean Ecosystems. The nation's valuable ocean ecosystems are being disrupted by increasing global temperatures through the loss of iconic and highly valued habitats and changes in species composition and food web structure. Ecosystem disruption will intensify as ocean warming, acidification, deoxygenation, and other aspects of climate change increase. In the absence of significant reductions in carbon emissions, transformative impacts on ocean ecosystems cannot be avoided. Key Message 2. Marine Fisheries. Marine fisheries and fishing communities are at high risk from climate-driven changes in the distribution, timing, and productivity of fishery-related species. Ocean warming, acidification, and deoxygenation are projected to increase these changes in fishery-related species, reduce catches in some areas, and challenge effective management of marine fisheries and protected species. Fisheries management that incorporates climate knowledge can help reduce impacts, promote resilience, and increase the value of marine resources in the face of changing ocean conditions. Key Message 3: Extreme Events. Marine ecosystems and the coastal communities that depend on them are at risk of significant impacts from extreme events with combinations of very high temperatures, very low oxygen levels, or very acidified conditions. These unusual events are projected to become more common and more severe in the future, and they expose vulnerabilities that can motivate change, including technological innovations to detect, forecast, and mitigate adverse conditions. Americans rely on ocean ecosystems for food, jobs, recreation, energy, and other vital services. Increased atmospheric carbon dioxide levels change ocean conditions through three main factors: warming seas, ocean acidification, and deoxygenation. These factors are transforming ocean ecosystems, and these transformations are already impacting the U.S. economy and coastal communities, cultures, and businesses. While climate-driven ecosystem changes are pervasive in the ocean, the most apparent impacts are occurring in tropical and polar ecosystems, where ocean warming is causing the loss of two vulnerable habitats, coral reef and sea ice ecosystems. The extent of sea ice in the Arctic is decreasing, which represents a direct loss of important habitat for animals like polar bears and ringed seals that use it for hunting, shelter, migration, and reproduction, causing their abundances to decline. Chapter 26, Alaska, Key Message 1. Warming has led to mass bleaching and/or outbreaks of coral diseases off the coastlines of Puerto Rico, the U.S. Virgin Islands, Florida, Hawaii, and the U.S.-affiliated Pacific Islands. Chapter 20, U.S. Caribbean, Key Message 2, Chapter 27, Hawaii and Pacific Islands, Key Message 4, that threaten reef ecosystems and the people who depend on them. The loss of recreational benefits alone from coral reefs in the United States is expected to reach $140 billion, discounted at 3% in 2015 dollars, by 2100. Reducing greenhouse gas emissions, for example under RCP 4.5, see the Scenario Products section of Appendix 3 for more on scenarios, could reduce these cumulative losses by as much as $5.4 billion, but will not avoid many ecological and economic impacts. Ocean warming, acidification, and deoxygenation are leading to changes in productivity, recruitment, survivorship, and, in some cases, active movements of species to track their preferred temperature conditions, with most moving northward or into deeper water with warming oceans. These changes are impacting the distribution and availability of many commercially and recreationally valuable fish and invertebrates. The effects of ocean warming, acidification, and deoxygenation on marine species will interact with fishery management decisions, from seasonal and spatial closures to annual quota setting, allocations, and fish stock rebuilding plans. Accounting for these factors is the cornerstone of climate-ready fishery management. Even without directly accounting for climate effects, precautionary fishery management and better incentives can increase economic benefits and improve resilience. Short-term changes in weather or ocean circulation can combine with long-term climate trends to produce periods of very unusual ocean conditions that can have significant impacts on coastal communities. Two such events have been particularly well documented: the 2012 marine heat wave in the northwestern Atlantic Ocean, and the sequence of warm ocean events between 2014 and 2016 in the northeastern Pacific Ocean, including a large, persistent area of very warm water referred to as the blob. Ecosystems within these regions experienced very warm conditions, more than 3.6 degrees Fahrenheit, 2 degrees Celsius, above the normal range, that persisted for several months or more. Extreme events in the oceans, other than those related to temperature, including ocean acidification and low oxygen events, can lead to significant disruptions to ecosystems and people, but they can also motivate preparedness and adaptation. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/oceans. End of section 11. Section 12 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 10, Agriculture and Rural Communities. Key Message 1. Reduced agricultural productivity. Food and forage production will decline in regions experiencing increased frequency and duration of drought. Shifting precipitation patterns, when associated with high temperatures, will intensify wildfires that reduce forage on rangelands, accelerate the depletion of water supplies for irrigation, and expand the distribution and incidence of pests and diseases for crops and livestock. Modern breeding approaches and the use of novel genes from crop-wild relatives are being employed to develop higher-yielding, stress-tolerant crops. Key Message 2. Degradation of soil and water resources. The degradation of critical soil and water resources will expand as extreme precipitation events increase across our agricultural landscape. Sustainable crop production is threatened by excessive runoff, leaching, and flooding, which results in soil erosion, degraded water quality in lakes and streams, and damage to rural community infrastructure. Management practices to restore soil structure and the hydrologic function of landscapes are essential for improving resilience to these challenges. Key Message 3. Health challenges to rural populations and livestock. Challenges to human and livestock health are growing due to the increased frequency and intensity of high-temperature extremes. Extreme heat conditions contribute to heat exhaustion, heat stroke, and heart attacks in humans. Heat stress in livestock results in large economic losses for producers. Expanded health services in rural areas, heat-tolerant livestock, and improved design of confined animal housing are all important advances to minimize these challenges. Key Message 4. Vulnerability and adaptive capacity of rural communities. Residents in rural communities often have limited capacity to respond to climate change impacts due to poverty and limitations in community resources. Communication, transportation, water, and sanitary infrastructure are vulnerable to disruption from climate stressors. Achieving social resilience to these challenges would require increases in local capacity to make adaptive improvements in shared community resources. In 2015, U.S. agricultural producers contributed $136.7 billion to the economy and accounted for 2.6 million jobs. About half of the revenue comes from livestock production. Other agriculture-related sectors in the food supply chain contributed an additional $855 billion of gross domestic product and accounted for 21 million jobs. In 2013, about 46 million people, or 15% of the U.S. population, lived in rural counties covering 72% of the nation's land area. From 2010 to 2015, a historic number of rural counties experienced population declines, and recent demographic trends point to relatively slow employment and population growth in rural areas, as well as high rates of poverty. Rural communities, where livelihoods are more tightly interconnected with agriculture, are particularly vulnerable to the agricultural volatility related to climate. Climate change has the potential to adversely impact agricultural productivity at local, regional, and continental scales through alterations in rainfall patterns, more frequent occurrences of climate extremes, including high temperatures or drought, and altered patterns of pest pressure. Risks associated with climate change depend on the rate and severity of the change and the ability of producers to adapt to changes. These adaptations include altering what is produced, modifying the inputs used for production, adopting new technologies, and adjusting management strategies. U.S. agricultural production relies heavily on the nation's land, water, and other natural resources, and these resources are affected directly by agricultural practices and by climate. Climate change is expected to increase the frequency of extreme precipitation events in many regions of the United States. Because increased precipitation extremes elevate the risk of surface runoff, soil erosion, and the loss of soil carbon, additional protective measures are needed to safeguard the progress that has been made in reducing soil erosion and water quality degradation through the implementation of grassed waterways, cover crops, conservation tillage, and waterway protection strips. Climate change impacts, such as changes in extreme weather conditions, have a complex influence on human and livestock health. The consequences of climate change on the incidence of drought also impact the frequency and intensity of wildfires, and this holds implications for agriculture and rural communities. Rural populations are the stewards of most of the nation's forests, watersheds, rangelands, agricultural land, and fisheries. Much of the rural economy is closely tied to the natural environment. Rural residents and the lands they manage have the potential to make important economic and conservation contributions to climate change mitigation and adaptation, but their capacity to adapt is impacted by a host of demographic and economic concerns. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/agriculture-rural. End of section 12. Section 13 of the 4th National Climate Assessment, Volume 2 by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 11. Built Environment, Urban Systems, and Cities. Key Message 1. Impacts on Urban Quality of Life. The opportunities and resources in urban areas are critically important to the health and well-being of people who work, live, and visit there. Climate change can exacerbate existing challenges to urban quality of life, including social inequality, aging and deteriorating infrastructure, and stressed ecosystems. Many cities are engaging in creative problem-solving to improve quality of life while simultaneously addressing climate change impacts. Key Message 2. Forward-looking design for urban infrastructure. Damages from extreme weather events demonstrate current urban infrastructure vulnerabilities. With its long service life, urban infrastructure must be able to endure a future climate that is different from the past. Forward-looking design informs investment in reliable infrastructure that can withstand ongoing and future climate risks. Key Message 3: Impacts on urban goods and services. Interdependent networks of infrastructure, ecosystems, and social systems provide essential urban goods and services. Damage to such networks from current weather extremes and future climate will adversely affect urban life. Coordinated local, state, and federal efforts can address these interconnected vulnerabilities. Key Message 4: Urban response to climate change. Cities across the United States are leading efforts to respond to climate change. Urban adaptation and mitigation actions can affect current and projected impacts of climate change and provide near-term benefits. Challenges to implementing these plans remain. Cities can build on local knowledge and risk management approaches, integrate social equity concerns, and join multi-city networks to begin to address these challenges. Urban areas, where the vast majority of Americans live, are engines of economic growth and contain land valued at trillions of dollars. Cities around the United States face a number of challenges to prosperity, such as social inequality, aging and deteriorating infrastructure, and stressed ecosystems. These social, infrastructure, and environmental challenges affect urban exposure and susceptibility to climate change effects. Urban areas are already experiencing the effects of climate change. Cities differ across regions in the acute and chronic climate stressors they are exposed to and how these stressors interact with local geographic characteristics. Cities are already subject to higher surface temperatures because of the urban heat island effect, which is projected to get stronger. Recent extreme weather events reveal the vulnerability of the built environment. Infrastructure such as residential and commercial buildings, transportation, communications, energy, water systems, parks, streets, and landscaping, and its importance to how people live, study, recreate, and work. Heat waves and heavy rainfalls are expected to increase in frequency and intensity. The way city residents respond to such incidents depends on their understanding of risk, their way of life, access to resources, and the communities to which they belong. Infrastructure designed for historical climate trends is vulnerable to future weather extremes and climate change. Investing in forward-looking design can help ensure that infrastructure performs acceptably under changing climate conditions. Urban areas are linked to local, regional, and global systems. Situations where multiple climate stressors simultaneously affect multiple city sectors, either directly or through system connections, are expected to become more common. When climate stressors affect one sector, cascading effects on other sectors increase risks to residents' health and well-being. Cities across the nation are taking action in response to climate change. U.S. cities are at the forefront of reducing greenhouse gas emissions, and many have begun adaptation planning. These actions build urban resilience to climate change. For full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/built-environment. End of section 13. Section 14 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 12. Transportation. Key Message 1. Transportation at risk. A reliable, safe, and efficient U.S. transportation system is at risk from increases in heavy precipitation, coastal flooding, heat, wildfires, and other extreme events, as well as changes to average temperature. Throughout this century, climate change will continue to pose a risk to U.S. transportation infrastructure with regional differences. Key Message 2. Impacts to urban and rural transportation. Extreme events that increasingly impact the transportation network are inducing societal and economic consequences, some of which disproportionately affect vulnerable populations. In the absence of intervention, future changes in climate will lead to increasing transportation challenges, particularly because of system complexity, aging infrastructure, and dependency across sectors. Key Message 3. Vulnerability assessments. Engineers, planners, and researchers in the transportation field are showing increasing interest and sophistication in understanding the risks that climate hazards pose to transportation assets and services. Transportation practitioner efforts demonstrate the connection between advanced assessment and the implementation of adaptive measures, though many communities still face challenges and barriers to action. Transportation is the backbone of economic activity, connecting manufacturers with supply chains, consumers with products and tourism, and people with their workplaces, homes, and communities across both urban and rural landscapes. However, the ability of the transportation sector to perform reliably, safely, and efficiently is undermined by a changing climate. Heavy precipitation, coastal flooding, heat, wildfires, freeze-thaw cycles, and changes in average precipitation and temperature impact individual assets across all modes. These impacts threaten the performance of the entire network, with critical ramifications for economic vitality and mobility, particularly for vulnerable populations and urban infrastructure. Sea level rise is progressively making coastal roads and bridges more vulnerable and less functional. Many coastal cities across the United States have already experienced an increase in high tide flooding that reduces the functionality of low elevation roadways, rail, and bridges, often causing costly congestion and damage to infrastructure. Inland transportation infrastructure is highly vulnerable to intense rainfall and flooding. In some regions, the increasing frequency and intensity of heavy precipitation events reduce transportation system efficiency and increase accident risk. High temperatures can stress bridge integrity and have caused more frequent and extended delays to passenger and freight rail systems and air traffic. Transportation is not only vulnerable to impacts of climate change, but also contributes significantly to the causes of climate change. In 2016, the transportation sector became the top contributor to U.S. greenhouse gas emissions. The transportation system is rapidly growing and evolving in response to market demand and innovation. This growth could make climate mitigation and adaptation progressively more challenging to implement and more important to achieve. However, transportation practitioners are increasingly invested in addressing climate risks, as evidenced in more numerous and diverse assessments of transportation sector vulnerabilities across the United States. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov /chapter/transportation. End of section 14. Section 15 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 13, Air Quality. Key Message 1. Increasing Risks from Air Pollution. More than 100 million people in the United States live in communities where air pollution exceeds health-based air quality standards. Unless counteracting efforts to improve air quality are implemented, climate change will worsen existing air pollution levels. This worsened air pollution would increase the incidence of adverse respiratory and cardiovascular health effects, including premature death. Increased air pollution would also have other environmental consequences, including reduced visibility and damage to agricultural crops and forests. Key Message 2. Increasing impacts of wildfires. Wildfire smoke degrades air quality, increasing the health risks to tens of millions of people in the United States. More frequent and severe wildfires, due to climate change, would further diminish air quality, increase incidences of respiratory illness from exposure to wildfire smoke, impair visibility, and disrupt outdoor recreational activities. Key Message 3. Increases in airborne allergy exposure. The frequency and severity of allergic illnesses, including asthma and hay fever, are likely to increase as a result of a changing climate. Earlier spring arrival, warmer temperatures, changes in precipitation, and higher carbon dioxide concentrations can increase exposure to airborne pollen allergens. Key Message 4. Co-benefits of greenhouse gas mitigation. Many emission sources of greenhouse gases also emit air pollutants that harm human health. Controlling these common emission sources would both mitigate climate change and have immediate benefits for air quality and human health. Because methane is both a greenhouse gas and an ozone precursor, reductions of methane emissions have the potential to simultaneously mitigate climate change and improve air quality. Unless offset by additional emissions reductions of ozone precursor emissions, there is high confidence that climate change will increase ozone levels over most of the United States, particularly over already polluted areas, thereby worsening the detrimental health and environmental effects due to ozone. The climate penalty results from changes in local weather conditions, including temperature and atmospheric circulation patterns, as well as changes in ozone precursor emissions that are influenced by meteorology. Climate change has already had an influence on ozone concentrations over the United States, offsetting some of the expected ozone benefit from reduced precursor emissions. The magnitude of the climate penalty over the United States could be reduced by mitigating climate change. Climatic changes, including warmer springs, longer summer dry seasons, and drier soils and vegetation, have already lengthened the wildfire season and increased the frequency of large wildfires. Exposure to wildfire smoke increases the risk of respiratory disease, resulting in adverse impacts to human health. Longer fire seasons and increases in the number of large fires would impair both human health and visibility. Climate change, specifically rising temperatures and increased carbon dioxide (CO2) concentrations, can influence plant-based allergens, hay fever, and asthma in 3 ways: by increasing the duration of the pollen season, by increasing the amount of pollen produced by plants, and by altering the degree of allergic reactions to the pollen. The energy sector, which includes energy production, conversion, and use, accounts for 84% of greenhouse gas (GHG) emissions in the United States, as well as 80% of emissions of nitrogen oxides (NOx) and 96% of sulfur dioxide, the major precursor of sulfate aerosol. In addition to reducing future warming, reductions in GHG emissions often result in co-benefits, other positive effects such as improved air quality, and possibly some negative effects, disbenefits, Chapter 29 Mitigation. Specifically, mitigating GHG emissions can lower emissions of particulate matter, PM, ozone and PM precursors, and other hazardous pollutants, reducing the risks to human health from air pollution. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/air-quality. End of section 15. Section 16 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 14, Human Health. Key Message 1. Climate change affects the health of all Americans. The health and well-being of Americans are already affected by climate change, with the adverse health consequences projected to worsen with additional climate change. Climate change affects human health by altering exposures to heat waves, floods, droughts, and other extreme events, vector, food, and waterborne infectious diseases, changes in the quality and safety of air, food, and water, and stresses to mental health and well-being. Key Message 2. Exposure and resilience vary across populations and communities. People and communities are differentially exposed to hazards and disproportionately affected by climate-related health risks. Populations experiencing greater health risks include children, older adults, low-income communities, and some communities of color. Key Message 3. Adaptation reduces risks and improves health. Proactive adaptation policies and programs reduce the risks and impacts from climate-sensitive health outcomes and from disruptions in healthcare services. Additional benefits to health arise from explicitly accounting for climate change risks in infrastructure planning and urban design. Key Message 4. Reducing greenhouse gas emissions results in health and economic benefits. Reducing greenhouse gas emissions would benefit the health of Americans in the near and long term. By the end of this century, thousands of American lives could be saved and hundreds of billions of dollars in health-related economic benefits gained each year under a pathway of lower greenhouse gas emissions. Climate-related changes in weather patterns and associated changes in air, water, food, and the environment are affecting the health and well-being of the American people, causing injuries, illnesses, and death. Increasing temperatures, increases in the frequency and intensity of heat waves since the 1960s, changes in precipitation patterns, especially increases in heavy precipitation, and sea level rise can affect our health through multiple pathways. Changes in weather and climate can degrade air and water quality, affect the geographic range, seasonality, and intensity of transmission of infectious diseases through food, water, and disease-carrying vectors, such as mosquitoes and ticks, and increase stresses that affect mental health and well-being. Changing weather patterns also interact with demographic and socioeconomic factors, as well as underlying health trends, to influence the extent of the consequences of climate change for individuals and communities. While all Americans are at risk of experiencing adverse climate-related health outcomes, some populations are disproportionately vulnerable. The risks of climate change for human health are expected to increase in the future, with the extent of the resulting impacts dependent on the effectiveness of adaptation efforts and on the magnitude and pattern of future climate change. Individuals, communities, public health departments, health-related organizations and facilities, and others are taking action to reduce health vulnerability to current climate change and to increase resilience to the risks projected in coming decades. The health benefits of reducing greenhouse gas emissions could result in economic benefits of hundreds of billions of dollars each year by the end of the century. Annual health impacts and health-related costs are projected to be approximately 50% lower under a lower scenario, RCP 4.5, compared to a higher scenario, RCP 8.5. These estimates would be even larger if they included the benefits of health outcomes that are difficult to quantify, such as avoided mental health impacts or long-term physical health impacts. For full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/health. End of section 16. Section 17 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 15. Tribes and Indigenous Peoples. Key Message 1. Indigenous Livelihoods and Economies at Risk. Climate change threatens indigenous peoples' livelihoods and economies, including agriculture, hunting and gathering, fishing, forestry, energy, recreation, and tourism enterprises. Indigenous peoples' economies rely on, but face institutional barriers to, their self-determined management of water, land, other natural resources, and infrastructure that will be impacted increasingly by changes in climate. Key Message 2. Physical, mental, and indigenous values-based health at risk. Indigenous health is based on interconnected social and ecological systems that are being disrupted by a changing climate. As these changes continue, the health of individuals and communities will be uniquely challenged by climate impacts to lands, waters, foods, and other plant and animal species. These impacts threaten sites, practices, and relationships with cultural, spiritual, or ceremonial importance that are foundational to indigenous peoples' cultural heritages, identities, and physical and mental health. Key Message 3. Adaptation, disaster management, displacement, and community-led relocations. Many indigenous peoples have been proactively identifying and addressing climate impacts. However, institutional barriers exist in the United States that severely limit their adaptive capacities. These barriers include limited access to traditional territory and resources, and the limitations of existing policies, programs, and funding mechanisms in accounting for the unique conditions of indigenous communities. Successful adaptation in indigenous contexts relies on use of indigenous knowledge, resilient and robust social systems and protocols, a commitment to principles of self-determination, and proactive efforts on the part of federal, state, and local governments to alleviate institutional barriers. Indigenous peoples in the United States are diverse and distinct political and cultural groups and populations. Though they may be affected by climate change in ways that are similar to others in the United States, Indigenous peoples can also be affected uniquely and disproportionately. Many Indigenous peoples have lived in particular areas for hundreds, if not thousands of years. Indigenous peoples' histories and shared experience engender distinct knowledge about climate change impacts and strategies for adaptation. Indigenous peoples' traditional knowledge systems can play a role in advancing understanding of climate change and in developing more comprehensive climate adaptation strategies. Observed and projected changes of increased wildfire, diminished snowpack, pervasive drought, flooding, ocean acidification, and sea level rise threaten the viability of Indigenous peoples' traditional subsistence and commercial activities that include agriculture, hunting and gathering, fisheries, forestry, energy, recreation, and tourism enterprises. Despite institutional barriers to tribal self-determination stemming from federal trust authority over tribal trust lands, a number of tribes have adaptation plans that include a focus on subsistence and commercial economic activities. Some tribes are also pursuing climate mitigation actions through the development of renewable energy on tribal lands. Climate impacts to lands, waters, foods, and other plant and animal species threaten cultural heritage sites and practices that sustain intra- and intergenerational relationships built on sharing traditional knowledges, food, and ceremonial or cultural objects. This weakens place-based cultural identities, may worsen historical trauma still experienced by many Indigenous peoples in the United States, and adversely affects mental health and Indigenous values-based understandings of health. Throughout the United States, climate-related disasters are causing Indigenous communities to consider or actively pursue relocation as an adaptation strategy. Challenges to Indigenous actions to address disaster management and recovery, displacement, and relocation in the face of climate change include economic, social, political, and legal considerations that severely constrain their abilities to respond to rapid ecological shifts and complicate action towards safe and self-determined futures for these communities. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/tribes. End of section 17. Section 18 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 16. Climate Effects on U.S. International Interests. Key Message 1. Economics and Trade. The impacts of climate change, variability, and extreme events outside the United States are affecting and are virtually certain to increasingly affect U.S. trade and economy, including import and export prices and businesses with overseas operations and supply chains. Key Message 2. International Development and Humanitarian Assistance. The impacts of climate change, variability, and extreme events can slow or reverse social and economic progress in developing countries, thus undermining international aid and investments made by the United States and increasing the need for humanitarian assistance and disaster relief. The United States provides technical and financial support to help developing countries better anticipate and address the impacts of climate change, variability, and extreme events. Key Message 3: Climate and National Security. Climate change, variability, and extreme events, in conjunction with other factors, can exacerbate conflict, which has implications for U.S. national security. Climate impacts already affect U.S. military infrastructure, and the U.S. military is incorporating climate risks in its planning. Key Message 4: Transboundary Resources. Shared resources along U.S. land and maritime borders provide direct benefits to Americans and are vulnerable to impacts from a changing climate, variability, and extremes. Multinational frameworks that manage shared resources are increasingly incorporating climate risk in their transboundary decision-making processes. U.S. international interests, such as economics and trade, international development and humanitarian assistance, national security, and transboundary resources, are affected by impacts from climate change, variability, and extreme events. Long-term changes in climate could lead to large-scale shifts in the global availability and prices of a wide array of agricultural, energy, and other goods, with corresponding impacts on the U.S. economy. Some U.S.-led businesses are already working to reduce their exposure to risks posed by a changing climate. U.S. investments in international development are sensitive to climate-related impacts and will likely be undermined by more frequent and intense extreme events, such as droughts, floods, and tropical cyclones. These events can impede development efforts and result in greater demand for U.S. humanitarian assistance and disaster relief. In response, the U.S. government has funded adaptation programs that seek to reduce vulnerability to climate impacts in critical sectors. Climate change, variability, and extreme events increase risks to national security through direct impacts on U.S. military infrastructure and, more broadly, through the relationship between climate-related stress on societies and conflict. Direct linkages between climate and conflict are unclear, but climate variability has been shown to affect conflict through intermediate processes, including resource competition, commodity price shocks, and food insecurity. The U.S. military is working to fully understand these threats and to incorporate projected climate changes into long-term planning. The impacts of changing weather and climate patterns across U.S. international borders affect those living in the United States. The changes pose new challenges for the management of shared and transboundary resources. Many bilateral agreements and public-private partnerships are incorporating climate risk and adaptation management into their near and long-term strategies. U.S. cooperation with international and other national scientific organizations improves access to global information and strategic partnerships, which better positions the nation to observe, understand, assess, and respond to the impacts associated with climate change, variability, and extremes on national interests both within and outside of U.S. borders. For full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/international-interests. End of section 18. Section 19 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 17. Sector Interactions, Multiple Stressors, and Complex Systems. Key Message 1. Interactions among sectors. The sectors and systems exposed to climate, for example, energy, water, and agriculture, interact with and depend on one another and other systems less directly exposed to climate, such as the financial sector. In addition, these interacting systems are not only exposed to climate-related stressors, such as floods, droughts, and heat waves, they are also subject to a range of non-climate factors, from population movements to economic fluctuations to urban expansion. These interactions can lead to complex behaviors and outcomes that are difficult to predict. It is not possible to fully understand the implications of climate change on the United States without considering the interactions among sectors and their consequences. Key Message 2. Multi-Sector Risk Assessment. Climate change risk assessment benefits from a multi-sector perspective, encompassing interactions among sectors and both climate and non-climate stressors. Because such interactions and their consequences can be challenging to identify in advance, effectively assessing multi-sector risks requires tools and approaches that integrate diverse evidence and that consider a wide range of possible outcomes. Key Message 3. Management of Interacting Systems. The joint management of interacting systems can enhance the resilience of communities, industries, and ecosystems to climate-related stressors. For example, during drought events, river operations can be managed to balance water demand for drinking water, navigation, and electricity production. Such integrated approaches can help avoid missed opportunities or unanticipated trade-offs associated with implementation of management responses to climate-related stressors. Key Message 4. Advancing Knowledge. Predicting the responses of complex interdependent systems will depend on developing meaningful models of multiple diverse systems, including human systems, and methods for characterizing uncertainty. The world we live in is a web of natural, built, and social systems, from global and regional climate to the electric grid, to water management systems such as dams, rivers, and canals, to managed and unmanaged forests, and to financial and economic systems. Climate affects many of these systems individually, but they also affect one another, and often in ways that are hard to predict. In addition, while climate-related risks such as heat waves, floods, and droughts have an important influence on these interconnected systems, these systems are also subject to a range of other factors, such as population growth, economic forces, technological change, and deteriorating infrastructure. A key factor in assessing risk in this context is that it is hard to quantify and predict all the ways in which climate-related stressors might lead to severe or widespread consequences for natural, built, and social systems. A multi-sector perspective can help identify such critical risks ahead of time, but uncertainties will always remain regarding exactly how consequences will materialize in the future. Therefore, effectively assessing multi-sector risks requires different tools and approaches than would be applied to understand a single sector by itself. In interacting systems, management responses within one system influence how other systems respond. Failure to anticipate interdependencies can lead to missed opportunities for managing the risks of climate change. It can also lead to management responses that increase risks to other parts of the system. Despite the challenge of managing system interactions, there are opportunities to learn from experience to guide future risk management decisions. There is a large gap in the multi-sector and multi-scale tools and frameworks that are available to describe how different human systems interact with one another and with the Earth system, and how those interactions affect the total system response to the many stressors they are subject to, including climate-related stressors. Characterizing the nature of such interactions and building the capacity to model them are important research challenges. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/complex-systems. End of section 19. Section 20 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 18, Northeast. Key Message 1. Changing seasons affect rural ecosystems, environments, and economies. The seasonality of the Northeast is central to the region's sense of place and is an important driver of rural economies. Less distinct seasons with milder winter and earlier spring conditions are already altering ecosystems and environments in ways that adversely impact tourism, farming, and forestry. The region's rural industries and livelihoods are at risk from further changes to forests, wildlife, snowpack, and stream flow. Key Message 2. Changing coastal and ocean habitats, ecosystem services, and livelihoods. The Northeast's coast and ocean support commerce, tourism, and recreation that are important to the region's economy and way of life. Warmer ocean temperatures, sea level rise, and ocean acidification threaten these services. The adaptive capacity of marine ecosystems and coastal communities will influence ecological and socio-economic outcomes as climate risks increase. Key Message 3. Maintaining urban areas and communities and their interconnectedness. The Northeast's urban centers and their interconnections are regional and national hubs for cultural and economic activity. Major negative impacts on critical infrastructure, urban economies, and nationally significant historic sites are already occurring and will become more common with a changing climate. Key Message 4. Threats to human health. Changing climate threatens the health and well-being of people in the Northeast through more extreme weather, warmer temperatures, degradation of air and water quality, and sea level rise. These environmental changes are expected to lead to health-related impacts and costs, including additional deaths, emergency room visits, and hospitalizations, and a lower quality of life. Health impacts are expected to vary by location, age, current health, and other characteristics of individuals and communities. Key Message 5. Adaptation to climate change is underway. Communities in the Northeast are proactively planning and implementing actions to reduce risks posed by climate change. Using decision support tools, to develop and apply adaptation strategies informs both the value of adopting solutions and the remaining challenges. Experience since the last assessment provides a foundation to advance future adaptation efforts. The distinct seasonality of the Northeast's climate supports a diverse natural landscape adapted to the extremes of cold, snowy winters and warm to hot, humid summers. This natural landscape provides the economic and cultural foundation for many rural communities, which are largely supported by a diverse range of agricultural, tourism, and natural resource-dependent industries. See Chapter 10, Ag and Rural, Key Message 4. The recent dominant trend in precipitation throughout the Northeast has been towards increases in rainfall intensity, with increases in intensity exceeding those in other regions of the contiguous United States. Further increases in rainfall intensity are expected, with increases in total precipitation expected during the winter and spring, but with little change in the summer. Monthly precipitation in the Northeast is projected to be about 1 inch greater for December through April by the end of century, 2070 through 2100, under the higher scenario, RCP 8.5. Ocean and coastal ecosystems are being affected by large changes in a variety of climate-related environmental conditions. These ecosystems support fishing and aquaculture, tourism and recreation, and coastal communities. Observed and projected increases in temperature, acidification, storm frequency and intensity, and sea levels are of particular concern for coastal and ocean ecosystems, as well as local communities and their interconnected social and economic systems. Increasing temperatures and changing seasonality on the Northeast continental shelf have affected marine organisms and the ecosystem in various ways. The warming trend experienced in the Northeast continental shelf has been associated with many fish and invertebrate species moving northward and to greater depths. Because of the diversity of the Northeast's coastal landscape, the impacts from storms and sea level rise will vary at different locations along the coast. Northeastern cities, with their abundance of concrete and asphalt and a relative lack of vegetation, tend to have higher temperatures than surrounding regions due to the urban heat island effect. During extreme heat events, nighttime temperatures in the region's big cities are generally several degrees higher than surrounding regions, leading to higher risk of heat-related death. Urban areas are at risk for large numbers of evacuated and displaced populations and damaged infrastructure due to both extreme precipitation events and recurrent flooding, potentially requiring significant emergency response efforts and consideration of a long-term commitment to rebuilding and adaptation and/or support for relocation where needed. Much of the infrastructure in the Northeast, including drainage and sewer systems, flood and storm protection assets, transportation systems, and power supply, is nearing the end of its planned life expectancy. Climate-related disruptions will only exacerbate existing issues with aging infrastructure. Sea level rise has amplified storm impacts in the Northeast, Key Message 2, contributing to higher surges that extend farther inland, as demonstrated in New York City in the aftermath of Superstorm Sandy in 2012. Service and resource supply infrastructure in the Northeast is at increasing risk of disruption, resulting in lower quality of life, economic declines, and increased social inequality. Loss of public services affects the capacity of communities to function as administrative and economic centers and triggers disruptions of interconnected supply chains. Chapter 16 International, Key Message 1. Increases in annual average temperatures across the Northeast range from less than 1 degree Fahrenheit (0.6 degrees centigrade) in West Virginia to about 3 degrees Fahrenheit (1.7 degrees centigrade) or more in New England since 1901. Although the relative risk of death on very hot days is lower today than it was a few decades ago, heat-related illness and death remain significant public health problems in the Northeast. For example, a study in New York City estimated that in 2013 there were 133 excess deaths due to extreme heat. These projected increases in temperature are expected to lead to substantially more premature deaths, hospital admissions, and emergency department visits across the Northeast. For example, in the Northeast, we can expect approximately 650 additional premature deaths per year from extreme heat by the year 2050 under either a lower RCP 4.5 or higher RCP 8.5 scenario, and from 960 under RCP 4.5 to 2,300 under RCP 8.5 more premature deaths per year by 2090. Communities, towns, cities, counties, states, and tribes across the Northeast are engaged in efforts to build resilience to environmental challenges and adapt to a changing climate. Developing and implementing climate adaptation strategies in daily practice often occur in collaboration with state and federal agencies. Advances in rural towns, cities, and suburban areas include low-cost adjustments of existing building codes and standards. In coastal areas, partnerships among local communities and federal and state agencies leverage federal adaptation tools and decision support frameworks. Increasingly, cities and towns across the Northeast are developing or implementing plans for adaptation and resilience in the face of changing climate. The approaches are designed to maintain and enhance the everyday lives of residents and promote economic development. In some cities, adaptation planning has been used to respond to present and future challenges in the built environment. Regional efforts have recommended changes in design standards when building, replacing, or retrofitting infrastructure to account for a changing climate. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Northeast. End of section 20. Section 21 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 19, Southeast. Key Message 1. Urban Infrastructure and Health Risks. Many southeastern cities are particularly vulnerable to climate change compared to cities in other regions, with expected impacts to infrastructure and human health. The vibrancy and viability of these metropolitan areas, including the people and critical regional resources located in them, are increasingly at risk due to heat, flooding, and vector-borne disease brought about by a changing climate. Many of these urban areas are rapidly growing and offer opportunities to adopt effective adaptation efforts to prevent future negative impacts of climate change. Key Message 2. Increasing flood risks in coastal and low-lying regions. The Southeast's coastal plain and inland low-lying regions support a rapidly growing population, a tourism economy, critical industries, and important cultural resources that are highly vulnerable to climate change impacts. The combined effects of changing extreme rainfall events and sea level rise are already increasing flood frequencies, which impacts property values and infrastructure viability, particularly in coastal cities. Without significant adaptation measures, these regions are projected to experience daily high tide flooding by the end of the century. Key Message 3: Natural ecosystems will be transformed. The Southeast's diverse natural systems, which provide many benefits to society, will be transformed by climate change. Changing winter temperature extremes, wildfire patterns, sea levels, hurricanes, floods, droughts, and warming ocean temperatures are expected to redistribute species and greatly modify ecosystems. As a result, the ecological resources that people depend on for livelihood, protection, and well-being are increasingly at risk, and future generations can expect to experience and interact with natural systems that are much different than those we see today. Key Message 4: Economic and health risks for rural communities. Rural communities are integral to the Southeast's cultural heritage and to the strong agricultural and forest products industries across the region. More frequent extreme heat episodes and changing seasonal climates are projected to increase exposure-linked health impacts and economic vulnerabilities in the agricultural, timber, and manufacturing sectors. By the end of the century, over 1/2 billion labor hours could be lost from extreme heat-related impacts. Such changes would negatively impact the region's labor-intensive agricultural industry and compound existing social stresses in rural areas related to limited local community capabilities and associated with rural demography, occupations, earnings, literacy, and poverty incidents. Reduction of existing stresses can increase resilience. The Southeast includes vast expanses of coastal and inland low-lying areas, the southern portion of the Appalachian Mountains, numerous high-growth metropolitan areas, and large rural expanses. These beaches and bayous, fields and forests, and cities and small towns are all at risk from a changing climate. While some climate change impacts, such as sea level rise and extreme downpours, are being acutely felt now, others, like increasing exposure to dangerous high temperatures, humidity, and new local diseases, are expected to become more significant in the coming decades. While all regional residents and communities are potentially at risk for some impacts, some communities or populations are at greater risk due to their locations, services available to them, and economic situations. Observed warming since the mid-20th century has been uneven in the Southeast region, with average daily minimum temperatures increasing 3 times faster than average daily maximum temperatures. The number of extreme rainfall events is increasing. Climate model simulations of future conditions project increases in both temperature and extreme precipitation. Trends toward a more urbanized and denser Southeast are expected to continue, creating new climate vulnerabilities. Cities across the Southeast are experiencing more and longer summer heat waves. Vector-borne diseases pose a greater risk in cities than in rural areas because of higher population densities and other human factors, and the major urban centers in the Southeast are already impacted by poor air quality during warmer months. Increasing precipitation and extreme weather events will likely impact roads, freight rail, and passenger rail, which will likely have cascading effects across the region. Infrastructure related to drinking water and wastewater treatment also has the potential to be compromised by climate-related events. Increases in extreme rainfall events and high-tide coastal floods due to future climate change will impact the quality of life of permanent residents as well as tourists visiting the low-lying and coastal regions of the Southeast. Sea level rise is contributing to increased coastal flooding in the Southeast, and high tide flooding already poses daily risks to businesses, neighborhoods, infrastructure, transportation, and ecosystems in the region. There have been numerous instances of intense rainfall events that have had devastating impacts on inland communities in recent years. The ecological resources that people depend on for livelihoods, protection, and well-being are increasingly at risk from the impacts of climate change. Sea level rise will result in the rapid conversion of coastal, terrestrial, and freshwater ecosystems to tidal saline habitats. Reductions in the frequency and intensity of cold winter temperature extremes are already allowing tropical and subtropical species to move northward and replace more temperate species. Warmer winter temperatures are also expected to facilitate the northward movement of problematic invasive species, which could transform natural systems north of their current distribution. In the future, rising temperatures and increases in the duration and intensity of drought are expected to increase wildfire occurrence and also reduce the effectiveness of prescribed fire practices. Many in rural communities are maintaining connections to traditional livelihoods and relying on natural resources that are inherently vulnerable to climate changes. Climate trends and possible climate futures show patterns that are already impacting and are projected to further impact rural sectors, from agriculture and forestry to human health and labor productivity. Future temperature increases are projected to pose challenges to human health. Increases in temperatures, water stress, freeze-free days, drought, and wildfire risks, together with changing conditions for invasive species and the movement of diseases, create a number of potential risks for existing agricultural systems. Rural communities tend to be more vulnerable to these changes due to factors such as demography, occupations, earnings, literacy, and poverty incidence. In fact, a recent economic study using a higher scenario, RCP 8.5, suggests that the southern and midwestern populations are likely to suffer the largest losses from future climate changes in the United States. Climate change tends to compound existing vulnerabilities and exacerbate existing inequities. Already poor regions, including those found in the Southeast, are expected to continue incurring greater losses than elsewhere in the United States. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/southeast. End of section 21. Section 22 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 20, U.S. Caribbean. Key Message 1. Fresh water. Fresh water is critical to life throughout the Caribbean. Increasing global carbon emissions are projected to reduce average rainfall in this region by the end of the century, constraining freshwater availability, while extreme rainfall events, which can increase freshwater flooding impacts, are expected to increase in intensity. Saltwater intrusion associated with sea level rise will reduce the quantity and quality of fresh water in coastal aquifers. Increasing variability in rainfall events and increasing temperatures will likely alter the distribution of ecological life zones and exacerbate existing problems in water management, planning, and infrastructure capacity. Key Message 2: Marine Resources. Marine ecological systems provide key ecosystem services such as commercial and recreational fisheries and coastal protection. These systems are threatened by changes in ocean surface temperature, ocean acidification, sea level rise, and changes in the frequency and intensity of storm events. Degradation of coral and other marine habitats can result in changes in the distribution of species that use these habitats and the loss of live coral cover, sponges, and other key species. These changes will likely disrupt valuable ecosystem services, producing subsequent effects on Caribbean island economies. Key Message 3: Coastal Systems. Coasts are a central feature of Caribbean island communities. Coastal zones dominate island economies and are home to critical infrastructure, public and private property, cultural heritage, and natural ecological systems. Sea level rise, combined with stronger wave action and higher storm surges, will worsen coastal flooding and increase coastal erosion, likely leading to diminished beach area, loss of storm surge barriers, decreased tourism, and negative effects on livelihoods and well-being. Adaptive planning and nature-based strategies, combined with active community participation and traditional knowledge, are beginning to be deployed to reduce the risks of a changing climate. Key Message 4: Rising temperatures. Natural and social systems adapt to the temperatures under which they evolve and operate. Changes to average and extreme temperatures have direct and indirect effects on organisms and strong interactions with hydrological cycles, resulting in a variety of impacts. Continued increases in average temperatures will likely lead to decreases in agricultural productivity, changes in habitats and wildlife distributions, and risks to human health, especially in vulnerable populations. As maximum and minimum temperatures increase, there are likely to be fewer cool nights and more frequent hot days, which will likely affect the quality of life in the U.S. Caribbean. Key Message 5: Disaster Risk Response to Extreme Events. Extreme events pose significant risks to life, property, and economy in the Caribbean, and some extreme events, such as flooding and droughts, are projected to increase in frequency and intensity. Increasing hurricane intensity and associated rainfall rates will likely affect human health and well-being, economic development, conservation, and agricultural productivity. Increased resilience will depend on collaboration and integrated planning, preparation, and responses across the region. Key Message 6: Increasing adaptive capacity through regional collaboration. Shared knowledge, collaborative research and monitoring, and sustainable institutional adaptive capacity can help support and speed up disaster recovery, reduce loss of life, enhance food security, and improve economic opportunity in the U.S. Caribbean. Increased regional cooperation and stronger partnerships in the Caribbean can expand the region's collective ability to achieve effective actions that build climate change resilience, reduce vulnerability to extreme events, and assist in recovery efforts. Historically, the U.S. Caribbean region has experienced relatively stable seasonal rainfall patterns, moderate annual temperature fluctuations, and a variety of extreme weather events, such as tropical storms, hurricanes, and drought. However, the Caribbean climate is changing and is projected to be increasingly variable as levels of greenhouse gases in the atmosphere increase. The high percentage of coastal area relative to the total island land area in the U.S. Caribbean means that a large proportion of the region's people, infrastructure, and economic activity are vulnerable to sea level rise, more frequent intense rainfall events and associated coastal flooding, and saltwater intrusion. High levels of exposure and sensitivity to risk in the U.S. Caribbean region are compounded by a low level of adaptive capacity, due in part to the high costs of mitigation and adaptation measures relative to the region's gross domestic product, particularly when compared to the continental U.S. coastal areas. The limited geographic and economic scale of Caribbean islands means that disruptions from extreme climate-related events, such as droughts and hurricanes, can devastate large portions of local economies and cause widespread damage to crops, water supplies, infrastructure, and other critical resources and services. The U.S. Caribbean territories of Puerto Rico and the U.S. Virgin Islands, USVI, have distinct differences in topography, language, population size, governance, natural and human resources, and economic capacity. However, both are highly dependent on natural and built coastal assets. Service-related industries account for more than 60% of the USVI economy. Beaches, affected by sea level rise and erosion, are among the main tourist attractions. In Puerto Rico, critical infrastructure, for example, drinking water pipelines and pump stations, sanitary pipelines and pump stations, wastewater treatment plants, and power plants, is vulnerable to the effects of sea level rise, storm surge, and flooding. In the USVI, infrastructure and historical buildings in the inundation zone for sea level rise include the power plants on both St. Thomas and St. Croix. Schools, housing communities, the towns of Charlotte-Amalie, Christiansted, and Frederiksted, and pipelines for water and sewage. Climate change will likely result in water shortages due to an overall decrease in annual rainfall, a reduction in ecosystem services, and increased risks for agriculture, human health, wildlife, and socioeconomic development in the U.S. Caribbean. These shortages would result from some locations within the Caribbean experiencing longer dry seasons and shorter but wetter, wet seasons in the future. Extended dry seasons are projected to increase fire likelihood. Excessive rainfall, coupled with poor construction practices, unpaved roads, and steep slopes, can exacerbate erosion rates and have adverse effects on reservoir capacity, water quality, and nearshore marine habitats. Ocean warming poses a significant threat to the survival of corals and will likely also cause shifts in associated habitats that compose the coral reef ecosystem. Severe, repeated, or prolonged periods of high temperatures leading to extended coral bleaching can result in colony death. ocean acidification also is likely to diminish the structural integrity of coral habitats. Studies show that major shifts in fisheries distribution and changes to the structure and composition of marine habitats adversely affect food security, shoreline protection, and economies throughout the Caribbean. In Puerto Rico, the annual number of days with temperatures above 90 degrees Fahrenheit has increased over the last 4.5 decades. During that period, stroke and cardiovascular disease, which are influenced by such elevated temperatures, became the primary causes of death. Increases in average temperature and in extreme heat events will likely have detrimental effects on agricultural operations throughout the U.S. Caribbean region. Many farmers in the tropics, including the U.S. Caribbean, are considered smallholding, limited resource farmers and often lack the resources and/or capital to adapt to changing conditions. Most Caribbean countries and territories share the need to assess risks, enable actions across scales, and assess changes in ecosystems to inform decision-making on habitat protection under a changing climate. U.S. Caribbean islands have the potential to improve adaptation and mitigation actions by fostering stronger collaborations with Caribbean initiatives on climate change and disaster risk reduction. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Caribbean. End of section 22. Section 23 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 21, Midwest. Key Message 1: Agriculture. The Midwest is a major producer of a wide range of food and animal feed for national consumption and international trade. Increases in warm season absolute humidity and precipitation have eroded soils, created favorable conditions for pests and pathogens, and degraded the quality of stored grain. Projected changes in precipitation, coupled with rising extreme temperatures before mid-century, will reduce Midwest agricultural productivity to levels of the 1980s without major technological advances. Key Message 2: Forestry. Midwest forests provide numerous economic and ecological benefits, yet threats from a changing climate are interacting with existing stressors, such as invasive species and pests, to increase tree mortality and reduce forest productivity. Without adaptive actions, these interactions will result in the loss of economically and culturally important tree species such as paper birch and black ash, and are expected to lead to the conversion of some forests to other forest types, or even to non-forested ecosystems by the end of the century. Land managers are beginning to manage risk in forests by increasing diversity and selecting for tree species adapted to a range of projected conditions. Key Message 3: Biodiversity and Ecosystems. The ecosystems of the Midwest support a diverse array of native species and provide people with essential services such as water purification, flood control, resource provision, crop pollination, and recreational opportunities. Species and ecosystems, including the important freshwater resources of the Great Lakes, are typically most at risk when climate stressors, like temperature increases, interact with land use change, habitat loss, pollution, nutrient inputs, and non-native invasive species. Restoration of natural systems, increases in the use of green infrastructure, and targeted conservation efforts, especially of wetland systems, can help protect people and nature from climate change impacts. Key Message 4: Human Health. Climate change is expected to worsen existing health conditions and introduce new health threats by increasing the frequency and intensity of poor air quality days, extreme high temperature events, and heavy rainfalls, extending pollen seasons, and modifying the distribution of disease-carrying pests and insects. By mid-century, the region is projected to experience substantial, yet avoidable, loss of life, worsened health conditions, and economic impacts estimated in the billions of dollars as a result of these changes. Improved basic health services and increased public health measures, including surveillance and monitoring, can prevent or reduce these impacts. Key Message 5: Transportation and Infrastructure. Stormwater management systems, transportation networks, and other critical infrastructure are already experiencing impacts from changing precipitation patterns and elevated flood risks. Green infrastructure is reducing some of the negative impacts by using plants and open space to absorb stormwater. The annual cost of adapting urban stormwater systems to more frequent and severe storms is projected to exceed $500 million for the Midwest by the end of the century. Key Message 6: Community Vulnerability and Adaptation. At-risk communities in the Midwest are becoming more vulnerable to climate change impacts such as flooding, drought, and increases in urban heat islands. Tribal nations are especially vulnerable because of their reliance on threatened natural resources for their cultural, subsistence, and economic needs. Integrating climate adaptation into planning processes offers an opportunity to better manage climate risks now. Developing knowledge for decision-making in cooperation with vulnerable communities and tribal nations will help to build adaptive capacity and increase resilience. The Midwest is home to over 60 million people, and its active economy represents 18% of the U.S. gross domestic product. The region is probably best known for agricultural production. Increases in growing season temperature in the Midwest are projected to be the largest contributing factor to declines in the productivity of U.S. agriculture. Increases in humidity in spring through mid-century are expected to increase rainfall, which will increase the potential for soil erosion and further reduce planting season workdays due to waterlogged soil. Forests are a defining characteristic of many landscapes within the Midwest, covering more than 91 million acres. However, a changing climate, including an increased frequency of late growing season drought conditions, is worsening the effects of invasive species, insect pests, and plant diseases as trees experience periodic moisture stress. Impacts from human activities, such as logging, fire suppression, and agricultural expansion, have lowered the diversity of the Midwest's forests from the pre-Euro-American settlement period. Natural resource managers are taking steps to address these issues by increasing the diversity of trees and introducing species suitable for a changing climate. The Great Lakes play a central role in the Midwest and provide an abundant freshwater resource for water supplies, industry, shipping, fishing, and recreation, as well as a rich and diverse ecosystem. These important ecosystems are under stress from pollution, nutrient and sediment inputs from agricultural systems, and invasive species. Lake surface temperatures are increasing. Lake ice cover is declining. The seasonal stratification of temperatures in the lakes is occurring earlier in the year, and summer evaporation rates are increasing. Increasing storm impacts and declines in coastal water quality can put coastal communities at risk. While several coastal communities have expressed willingness to integrate climate action into planning efforts, access to useful climate information and limited human and financial resources constrain municipal action. Land conversion, and a wide range of other stressors, has already greatly reduced biodiversity in many of the region's prairies, wetlands, forests, and freshwater systems. Species are already responding to changes that have occurred over the last several decades, and rapid climate change over the next century is expected to cause or further amplify stress in many species and ecological systems in the Midwest. The loss of species and the degradation of ecosystems have the potential to reduce or eliminate essential ecological services such as flood control, water purification, and crop pollination, thus reducing the potential for society to successfully adapt to ongoing changes. However, understanding these relationships also highlights important climate adaptation strategies. For example, restoring systems like wetlands and forested floodplains and implementing agricultural best management strategies that increase vegetative cover crops and riparian buffers, can help reduce flooding risks and protect water quality. Midwestern populations are already experiencing adverse health impacts from climate change, and these impacts are expected to worsen in the future. In the absence of mitigation, ground-level ozone concentrations are projected to increase across most of the Midwest, resulting in an additional 200 to 550 premature deaths in the region per year by 2050. Exposure to high temperatures impacts workers' health, safety, and productivity. Currently, days over 100 degrees Fahrenheit in Chicago are rare. However, they could become increasingly more common by late century in both the lower and higher scenarios, RCP 4.5 and RCP 8.5. The Midwest also has vibrant manufacturing, retail, recreation/tourism, and service sectors. The region's highways, railroads, airports, and navigable rivers are major modes for commerce activity. Increasing precipitation, especially heavy rain events, has increased the overall flood risk, causing disruptions to transportation and damage to property and infrastructure. Increasing use of green infrastructure, including nature-based approaches such as wetland restoration and innovations like permeable pavements, and better engineering practices, are beginning to address these issues. Citizens and stakeholders value their health and the well-being of their communities, all of which are at risk from increased flooding, increased heat, and lower air and water quality under a changing climate. To better prevent and respond to these impacts, scholars and practitioners highlight the need to engage in risk-driven approaches that not only focus on assessing vulnerabilities, but also include effective planning and implementation of adaptation options. For full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Midwest. End of section 23. Section 24 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 22, Northern Great Plains. Key Message 1. Water. Water is the lifeblood of the Northern Great Plains, and effective water management is critical to the region's people, crops and livestock, ecosystems, and energy industry. Even small changes in annual precipitation can have large effects downstream. When coupled with the variability from extreme events, these changes make managing these resources a challenge. Future changes in precipitation patterns, warmer temperatures, and the potential for more extreme rainfall events are very likely to exacerbate these challenges. Key Message 2. Agriculture. Agriculture is an integral component of the economy, the history, and the culture of the Northern Great Plains. Recently, agriculture has benefited from longer growing seasons and other recent climatic changes. Some additional production and conservation benefits are expected in the next 2 to 3 decades as land managers employ innovative adaptation strategies, but rising temperatures and changes in extreme weather events are very likely to have negative impacts on parts of the region. Adaptation to extremes and to longer-term persistent climate changes will likely require transformative changes in agricultural management, including regional shifts of agricultural practices and enterprises. Key Message 3. Recreation and tourism. Ecosystems across the Northern Great Plains provide recreational opportunities and other valuable goods and services that are at risk in a changing climate. Rising temperatures have already resulted in shorter snow seasons, lower summer stream flows, and higher stream temperatures, and have negatively affected high elevation ecosystems and riparian areas, with important consequences for local economies that depend on winter or river-based recreational activities. Climate-induced land use changes in agriculture can have cascading effects on closely entwined natural ecosystems, such as wetlands, and the diverse species and recreational amenities they support. Federal, tribal, state, and private organizations are undertaking preparedness and adaptation activities, such as scenario planning, transboundary collaboration, and development of market-based tools. Key Message 4. Energy. Fossil fuel and renewable energy production and distribution infrastructure is expanding within the Northern Great Plains. Climate change and extreme weather events put this infrastructure at risk, as well as the supply of energy it contributes to support individuals, communities, and the U.S. economy as a whole. The energy sector is also a significant source of greenhouse gases and volatile organic compounds that contribute to climate change and ground-level ozone pollution. Key Message 5. Indigenous peoples. Indigenous peoples of the Northern Great Plains are at high risk from a variety of climate change impacts, especially those resulting from hydrological changes, including changes in snowpack, seasonality and timing of precipitation events, and extreme flooding and droughts, as well as melting glaciers and reduction in stream flows. These changes are already resulting in harmful impacts to tribal economies, livelihoods, and sacred waters and plants used for ceremonies, medicine, and subsistence. At the same time, many tribes have been very proactive in adaptation and strategic climate change planning. In the Northern Great Plains, The timing and quantity of both precipitation and runoff have important consequences for water supplies, agricultural activities, and energy production. Overall, climate projections suggest that the number of heavy precipitation events with greater than 1 inch per day of rainfall, is projected to increase. Moving forward, the magnitude of year-to-year variability overshadows the small projected average decrease in stream flow. Changes in extreme events are likely to overwhelm average changes in both the eastern and western regions of the northern Great Plains. Major flooding across the basin in 2011 was followed by severe drought in 2012, representing new and unprecedented variability that is likely to become more common in a warmer world. The northern Great Plains region plays a critical role in national food security. Among other anticipated changes, projected warmer and generally wetter conditions with elevated atmospheric carbon dioxide concentrations are expected to increase the abundance and competitive ability of weeds and invasive species, increase livestock production and efficiency of production, and result in longer growing seasons at mid and high latitudes. Net primary productivity, including crop yields and forage production, is also likely to increase, although an increasing number of extreme temperature events during critical pollination and grain fill periods is likely to reduce crop yields. Ecosystems across the northern Great Plains provide recreational opportunities and other valuable goods and services that are ingrained in the region's cultures. Higher temperatures, reduced snow cover, and more variable precipitation will make it increasingly challenging to manage the region's valuable wetlands, rivers, and snow-dependent ecosystems. In the mountains of western Wyoming and western Montana, the fraction of total water in precipitation that falls as snow is expected to decline by 25% to 40% by 2100 under a higher scenario, RCP 8.5, which would negatively affect the region's winter recreation industry. At lower elevation areas of the northern Great Plains, climate-induced land use changes in agriculture can have cascading effects on closely entwined natural ecosystems, such as wetlands, and the diverse species and recreational opportunities they support. Energy resources in the northern Great Plains include abundant crude oil, natural gas, coal, wind, and stored water, and, to a lesser extent, corn-based ethanol, solar energy, and uranium. The infrastructure associated with the extraction, distribution, and energy produced from these resources is vulnerable to the impacts of climate change. Railroads and pipelines are vulnerable to damage or disruption from increasing heavy precipitation events and associated flooding and erosion. Declining water availability in the summer would likely increase costs for oil production operations, which require freshwater resources. These cost increases will either lead to lower production or be passed on to consumers. Finally, higher maximum temperatures, longer and more severe heat waves, and higher overnight lows are expected to increase electricity demand for cooling in the summer, further stressing the power grid. Indigenous peoples in the region are observing changes to climate, many of which are impacting livelihoods, as well as traditional subsistence and wild foods, wildlife, plants and water for ceremonies, medicines, and health and well-being. Because some tribes and indigenous peoples are among those in the region with the highest rates of poverty and unemployment, and because many are still directly reliant on natural resources, they are among the most at risk to climate change. For a full chapter, including references and traceable accounts, see https://ncA2018.globalchange.gov/chapter/northern-great-plains. End of section 24. Section 25 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 23, Southern Great Plains. Key Message 1: Food, Energy, and Water Resources. Quality of life in the region will be compromised as increasing population, the migration of individuals from rural to urban locations, and a changing climate redistribute demand at the intersection of food consumption, energy production, and water resources. A growing number of adaptation strategies, improved climate services, and early warning decision support systems will more effectively manage the complex regional, national, and transnational issues associated with food, energy, and water. Key Message 2: Infrastructure. The built environment is vulnerable to increasing temperature, extreme precipitation, and continued sea level rise, particularly as infrastructure ages and populations shift to urban centers. Along the Texas Gulf Coast, relative sea level rise of twice the global average will put coastal infrastructure at risk. Regional adaptation efforts that harden or relocate critical infrastructure will reduce the risk of climate change impacts. Key Message 3: Ecosystems and ecosystem services. Terrestrial and aquatic ecosystems are being directly and indirectly altered by climate change. Some species can adapt to extreme droughts, unprecedented floods, and wildfires from a changing climate, while others cannot, resulting in significant impacts to both services and people living in these ecosystems. Landscape-scale ecological services will increase the resilience of the most vulnerable species. Key Message 4: Human Health. Health threats, including heat illness and diseases transmitted through food, water, and insects, will increase as temperature rises. Weather conditions supporting these health threats are projected to be of longer duration or occur at times of the year when these threats are not normally experienced. Extreme weather events, with resultant physical injury and population displacement, are also a threat. These threats are likely to increase in frequency and distribution, and are likely to create significant economic burdens. Vulnerability and adaptation assessments, comprehensive response plans, seasonal health forecasts, and early warning systems can be useful adaptation strategies. Key Message 5: Indigenous peoples. Tribal and indigenous communities are particularly vulnerable to climate change due to water resource constraints, extreme weather events, higher temperature, and other likely public health issues. Efforts to build community resilience can be hindered by economic, political, and infrastructure limitations, but traditional knowledge and intertribal organizations provide opportunities to adapt to the potential challenges of climate change. The southern Great Plains experiences weather that is dramatic and consequential, from hurricanes and flooding to heat waves and drought. Its 34 million people, their infrastructure, and economies are often stressed, greatly impacting socioeconomic systems. The quality of life for the region's residents is dependent upon resources and natural systems for the sustainable provision of our basic needs: food, energy, and water. Extreme weather and climate events have redistributed demands for consumption, production, and supply across the region. Adaptation strategies that integrate climate services and early warning systems are improving our abilities to develop sustainable infrastructure and increase agricultural production, yet include the flexibility needed to embrace any changing demand patterns. Regional adaptation efforts that harden or relocate critical infrastructure will reduce the risk of climate change impacts. Redesigns of coastal infrastructure and the use of green/gray methodologies are improving future coastal resilience. Energy industry reinvention is ensuring operations and reliability during extreme climatic events. Increasingly robust considerations of economic resilience allow us to anticipate risk, evaluate how that risk can affect our needs, and build a responsive, adaptive capacity. With climate change, terrestrial and aquatic ecosystems and species within them have winners and losers. Those that can adapt are increasers, while others cannot, resulting in impacts to traditional services and the livelihoods of the people who depend on those resources. The warming of coastal bay waters has been documented since at least the 1980s, and those increases in water temperature directly affect water quality, leading to hypoxia, harmful algal blooms, and fish kills, thus lowering the productivity and diversity of estuaries. Natural wetlands, like the playa lakes in the high plains, which have served for centuries as important habitat for migrating waterfowl, are virtually non-existent during drought. Direct human health threats follow a similar pattern of species within our natural ecosystems. Extreme weather results in both direct and indirect impacts to people. Physical injury and population displacement are anticipated to result with climate change. Heat illness and diseases transmitted through food, water, and insects increase human risk as temperature rises. Acute awareness of these future impacts allows us to plan for the most vulnerable and adapt through response plans, health forecasting, and early warning strategies, including those that span transboundary contexts and systems. The impacts of climate change in general become more acute when considering tribal and indigenous communities. Resilience to climate change will be hindered by economic, political, and infrastructure limitations for these groups. At the same time, connectivity of the tribes and indigenous communities offers opportunities for teaching adaptively through their cultural means of applying traditional knowledge and intertribal organization. These well-honed connections of adapting through the centuries may help all of us learn how to offset the impacts and potential challenges of climate change. The role of climate change in altering the frequency of the types of severe weather most typically associated with the southern Great Plains, such as severe local storms, hailstorms, and tornadoes, remains difficult to quantify. Indirect approaches suggest a possible increase in the circumstances conducive to such severe weather, including an increase in the instances of larger hail sizes in the region by 2040. But changes are unlikely to be uniform across the region, and additional research is needed. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/southern-great-plains. End of section 25. Section 26 of the 4th National Climate Assessment, Volume 2 by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 24, Northwest. Key Message 1. Natural Resource Economy. Climate change is already affecting the Northwest's diverse natural resources, which support sustainable livelihoods, provide a robust foundation for rural, tribal, and indigenous communities, and strengthen local economies. Climate change is expected to continue affecting the natural resource sector, but the economic consequences will depend on future market dynamics, management actions, and adaptation efforts. Proactive management can increase the resilience of many natural resources and their associated economies. Key Message 2. Natural World and Cultural Heritage. Climate change and extreme events are already endangering the well-being of a wide range of wildlife, fish, and plants, which are intimately tied to tribal subsistence culture and popular outdoor recreation activities. Climate change is projected to continue to have adverse impacts on the regional environment, with implications for the values, identity, heritage, cultures, and quality of life of the region's diverse population. Adaptation and informed management, especially culturally appropriate strategies, will likely increase the resilience of the region's natural capital. Key Message 3. Infrastructure. Existing water, transportation, and energy infrastructure already face challenges from flooding, landslides, drought, wildfire, and heat waves. Climate change is projected to increase the risks from many of these extreme events, potentially compromising the reliability of water supplies, hydropower, and transportation across the region. Isolated communities, and those with systems that lack redundancy, are the most vulnerable. Adaptation strategies that address more than one sector or are coupled with social and environmental co-benefits can increase resilience. Key Message 4. Health. Organizations and volunteers that make up the Northwest's social safety net are already stretched thin with current demands. Healthcare and social systems will likely be further challenged with the increasing frequency of acute events, or when cascading events occur. In addition to an increased likelihood of hazards and epidemics, disruptions in local economies and food systems are projected to result in more chronic health risks. The potential health co-benefits of future climate mitigation investments could help to counterbalance these risks. Key Message 5. Frontline communities. Communities on the front lines of climate change experience the first, and often the worst, effects. Frontline communities in the Northwest include tribes and indigenous peoples, those most dependent on natural resources for their livelihoods, and the economically disadvantaged. These communities generally prioritize basic needs, such as shelter, food, and transportation, frequently lack economic and political capital, and have fewer resources to prepare for and cope with climate disruptions. The social and cultural cohesion inherent in many of these communities provides a foundation for building community capacity and increasing resilience. Residents of the Northwest list the inherent qualities of the natural environment among the top reasons to live in the region. The region is known for clean air, abundant water, low-cost hydroelectric power, vast forests, extensive farmlands, and outdoor recreation that includes hiking, boating, fishing, hunting, and skiing. Climate change, including gradual changes to the climate and in extreme climatic events, is already affecting these valued aspects of the region, including the natural resource sector, cultural identity and quality of life, built infrastructure systems, and the health of Northwest residents. The communities on the front lines of climate change, tribes and indigenous peoples, those most dependent on natural resources for their livelihoods, and the economically disadvantaged, are experiencing the first and often the worst effects. In the third National Climate Assessment, the key messages for the Northwest focused on projected climate impacts to the region. These impacts, many of which are now better understood in the scientific literature, remain the primary climate concerns over the coming decades. In this updated assessment, the key messages explore how climate change could affect the interrelationships between the environment and the people of the Northwest. The extreme weather events of 2015 provide an excellent opportunity to explore projected changes in baseline climate conditions for the Northwest. The vast array of climate impacts that occurred over this record-breaking warm and dry year, coupled with the impacts of a multi-year drought, provide an enlightening glimpse into what may be more commonplace under a warmer future climate. Record low snowpack led to water scarcity and large wildfires that negatively affected farmers, hydropower, drinking water, air quality, salmon, and recreation. Warmer than normal ocean temperatures led to shifts in the marine ecosystem, challenges for salmon, and a large, harmful algal bloom that adversely affected the region's fisheries and shellfish harvests. Strong climate variability is likely to persist for the Northwest, owing in part to the year-to-year and decade-to-decade climate variability associated with the Pacific Ocean. Periods of prolonged drought are projected to be interspersed with years featuring heavy rainfall, driven by powerful atmospheric rivers, and strong El Niño winters associated with storm surge, large waves, and coastal erosion. Continued changes in the ocean environment, such as warmer waters, altered chemistry, sea level rise, and shifts in the marine ecosystems, are also expected. These changes would affect the Northwest's natural resource economy, cultural heritage, built infrastructure, and recreation, as well as the health and welfare of Northwest residents. The Northwest has an abundance of examples and case studies that highlight climate adaptation in progress and in practice, including creating resilient agro-ecosystems that reduce climate-related risks while meeting economic, conservation, and adaptation goals, using green or hybrid green and gray infrastructure solutions that combine nature-based solutions with more traditional engineering approaches, and building social cohesion and strengthening social networks in frontline communities to assist in meeting basic needs while also increasing resilience to future climate stressors. Many of the case studies in this chapter demonstrate the importance of co-producing adaptation efforts with scientists, resource managers, communities, and decision makers as the region prepares for climate change impacts across multiple sectors and resources. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Northwest. End of section 26. Section 27 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 25, Southwest. Key Message 1. Water Resources. Water for people and nature in the Southwest has declined during droughts, due in part to human-caused climate change. Intensifying droughts and occasional large floods, combined with critical water demands from a growing population, deteriorating infrastructure, and groundwater depletion, suggest the need for flexible water management techniques that address changing risks over time, balancing declining supplies with greater demands. Key Message 2. Ecosystems and ecosystem services. The integrity of Southwest forests and other ecosystems, and their ability to provide natural habitat, clean water, and economic livelihoods, have declined as a result of recent droughts and wildfire, due in part to human-caused climate change. Greenhouse gas emissions reductions, fire management, and other actions can help reduce future vulnerabilities of ecosystems and human well-being. Key Message 3. The Coast. Many coastal resources in the Southwest have been affected by sea level rise, ocean warming, and reduced ocean oxygen, all impacts of human-caused climate change, and ocean acidification resulting from human emissions of carbon dioxide. Homes and other coastal infrastructure, marine flora and fauna, and people who depend on coastal resources face increased risks under continued climate change. Key Message 4. Indigenous peoples. Traditional foods, natural resource-based livelihoods, cultural resources, and spiritual well-being of indigenous peoples in the Southwest are increasingly affected by drought, wildfire, and changing ocean conditions. Because future changes would further disrupt the ecosystems on which indigenous peoples depend, tribes are implementing adaptation measures and emissions reduction actions. Key Message 5. Energy. The ability of hydropower and fossil fuel electricity generation to meet growing energy use in the Southwest is decreasing as a result of drought and rising temperatures. Many renewable energy sources offer increased electricity reliability, lower water intensity of energy generation, reduced greenhouse gas emissions, and new economic opportunities. Key Message 6. Food. Food production in the Southwest is vulnerable to water shortages. Increased drought, heat waves, and reduction of winter chill hours can harm crops and livestock, exacerbate competition for water among agriculture, energy generation, and municipal uses, and increase future food insecurity. Key Message 7. Human health. Heat-associated deaths and illnesses, vulnerabilities to chronic disease, and other health risks to people in the Southwest result from increases in extreme heat, poor air quality, and conditions that foster pathogen growth and spread. Improving public health systems, community infrastructure, and personal health can reduce serious health risks under future climate change. The Southwest region encompasses diverse ecosystems, cultures, and economies, reflecting a broad range of climate conditions, including the hottest and driest climate in the United States. Water for people and nature in the Southwest region has declined during droughts, due in part to human-caused climate change. Higher temperatures intensified the recent severe drought in California and are amplifying drought in the Colorado River Basin. Since 2000, Lake Mead on the Colorado River has fallen 130 feet, 40 meters, and lost 60% of its volume, a result of the ongoing Colorado River Basin drought and continued water withdrawals by cities and agriculture. The reduction of water volume in both Lake Powell and Lake Mead increases the risk of water shortages across much of the Southwest. Local water utilities, the governments of 7 U.S. states, and the federal governments of the United States and Mexico have voluntarily developed and implemented solutions to minimize the possibility of water shortages for cities, farms, and ecosystems. In response to the recent California drought, the state implemented a water conservation plan in 2014 that set allocations for water utilities and major users and banned wasteful practices. As a result, the people of the state reduced water use 25% from 2014 to 2017. Exposure to hotter temperatures and heat waves already leads to heat-associated deaths in Arizona and California. Mortality risk during a heat wave is amplified on days with high levels of ground-level ozone or particulate air pollution. Given the proportion of the U.S. population in the Southwest region, a disproportionate number of West Nile virus, plague, hantavirus pulmonary syndrome, and valley fever cases occur in the region. Analyses estimated that the area burned by wildfire across the western United States from 1984 to 2015 was twice what would have burned had climate change not occurred. Wildfires around Los Angeles from 1990 to 2009 caused $3.1 billion in damages, unadjusted for inflation. Tree death in mid-elevation conifer forests doubled from 1955 to 2007, due, in part, to climate change, allowing naturally ignited fires to burn in wilderness areas and preemptively setting low-severity prescribed burns in areas of unnatural fuel accumulations can reduce the risk of high-severity fires under climate change. Reducing greenhouse gas emissions globally can also reduce ecological vulnerabilities. At the Golden Gate Bridge in San Francisco, sea level rose 9 inches, 22 centimeters, between 1854 and 2016. Climate change caused most of this rise by melting of land ice and thermal expansion of ocean water. Local governments on the California coast are using projections of sea level rise to develop plans to reduce future risks. Ocean water acidity off the coast of California increased 25% to 40%, decreases of 0.1 to 0.15 pH units, from the pre-industrial era, circa 1750, to 2014, due to increasing concentrations of atmospheric carbon dioxide from human activities. The marine heat wave along the Pacific coast from 2014 to 2016 occurred due to a combination of natural factors and climate change. The event led to the mass stranding of sick and starving birds and sea lions, and shifts of red crabs and tuna into the region. The ecosystem disruptions contributed to closures of commercially important fisheries. Agricultural irrigation accounts for approximately 3/4 of water use in the Southwest region, which grows half of the fruits, vegetables, and nuts, and most of the wine grapes, strawberries, and lettuce for the United States. Increasing heat stress during specific phases of the plant life cycle can increase crop failures. Drought and increasing heat intensify the arid conditions of reservations, where the United States restricted some tribal nations in the Southwest region to the driest portions of their traditional homelands. In response to climate change, indigenous peoples in the region are developing new adaptation and mitigation actions. The severe drought in California, intensified by climate change, reduced hydroelectric generation 2/3 from 2011 to 2015. The efficiency of all water-cooled electric power plants that burn fuel depends on the temperature of the external cooling water, so climate change could reduce energy efficiency up to 15% across the Southwest by 2050. Solar, wind, and other renewable energy sources, except biofuels, emit less carbon and require less water than fossil fuel energy. Economic conditions and technological innovations have lowered renewable energy costs and increased renewable energy generation in the Southwest. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Southwest. End of section 27. Section 28 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 26, Alaska. Key Message 1. Marine Ecosystems. Alaska's marine fish and wildlife habitats, species distributions, and food webs, all of which are important to Alaska's residents, are increasingly affected by retreating and thinning Arctic summer sea ice, increasing temperatures, and ocean acidification. Continued warming will accelerate related ecosystem alterations in ways that are difficult to predict, making adaptation more challenging. Key Message 2. Terrestrial processes. Alaska residents, communities, and their infrastructure continue to be affected by permafrost thaw, coastal and river erosion, increasing wildfire, and glacier melt. These changes are expected to continue into the future with increasing temperatures, which would directly impact how and where many Alaskans will live. Key Message 3. Human health. A warming climate brings a wide range of human health threats to Alaskans, including increased injuries, smoke inhalation, damage to vital water and sanitation systems, decreased food and water security, and new infectious diseases. The threats are greatest for rural residents, especially those who face increased risk of storm damage and flooding, loss of vital food sources, disrupted traditional practices, or relocation. Implementing adaptation strategies would reduce the physical, social, and psychological harm likely to occur under a warming climate. Key Message 4: Indigenous Peoples. The subsistence activities, culture, health, and infrastructure of Alaska's indigenous peoples and communities are subject to a variety of impacts, many of which are expected to increase in the future. Flexible, community-driven adaptation strategies would lessen these impacts by ensuring that climate risks are considered in the full context of the existing socio-cultural systems. Key Message 5: Economic Costs. Climate warming is causing damage to infrastructure that will be costly to repair or replace, especially in remote Alaska. It is also reducing heating costs throughout the state. These effects are very likely to grow with continued warming. Timely repair and maintenance of infrastructure can reduce the damages and avoid some of these added costs. Key Message 6: Adaptation. Proactive adaptation in Alaska would reduce both short and long-term costs associated with climate change, generate social and economic opportunity, and improve livelihood security. Direct engagement and partnership with communities is a vital element of adaptation in Alaska. Alaska is the largest state in the nation, almost one-fifth the size of the combined lower 48 United States, and is rich in natural capital resources. Alaska is often identified as being on the front lines of climate change, since it is warming faster than any other state and faces a myriad of issues associated with a changing climate. The cost of infrastructure damage from a warming climate is projected to be very large, potentially ranging from $110 to $270 million per year, assuming timely repair and maintenance. Although climate change does and will continue to dramatically transform the climate and environment of the Arctic, proactive adaptation in Alaska has the potential to reduce costs associated with these impacts. This includes the dissemination of several tools, such as guidebooks to support adaptation planning, some of which focus on indigenous communities. While many opportunities exist with a changing climate, economic prospects are not well captured in the literature at this time. As the climate continues to warm, there is likely to be a nearly sea ice-free Arctic during the summer by mid-century. Ocean acidification is an emerging global problem that will intensify with continued carbon dioxide (CO2) emissions and negatively affects organisms. Climate change will likely affect management actions and economic drivers, including fisheries, in complex ways. The use of multiple alternative models to appropriately characterize uncertainty in future fisheries biomass trajectories and harvests could help manage these challenges. As temperature and precipitation increase across the Alaska landscape, physical and biological changes are also occurring throughout Alaska's terrestrial ecosystems. Degradation of permafrost is expected to continue, with associated impacts to infrastructure, river and stream discharge, water quality, and fish and wildlife habitat. Longer sea ice-free seasons, higher ground temperatures, and relative sea level rise are expected to exacerbate flooding and accelerate erosion in many regions, leading to the loss of terrestrial habitat in the future, and in some cases, requiring entire communities or portions of communities to relocate to safer terrain. The influence of climate change on human health in Alaska can be traced to three sources: direct exposures, indirect effects, and social or psychological disruption. Each of these will have different manifestations for Alaskans when compared to residents elsewhere in the United States. Climate change exerts indirect effects on human health in Alaska through changes to water, air, and soil, and through ecosystem changes affecting disease ecology and food security, especially in rural communities. Alaska's rural communities are predominantly inhabited by indigenous peoples who may be disproportionately vulnerable to socioeconomic and environmental change. However, they also have rich cultural traditions of resilience and adaptation. The impacts of climate change will likely affect all aspects of Alaska Native societies, from nutrition, infrastructure, economics, and health consequences, to language, education, and the communities themselves. The profound and diverse climate-driven changes in Alaska's physical environment and ecosystems generate economic impacts through their effects on environmental services. These services include positive benefits directly from ecosystems, for example, food, water, and other resources, as well as services provided directly from the physical environment, for example, temperature moderation, stable ground for supporting infrastructure, and smooth surface for overland transportation. Some of these effects are relatively assured, and in some cases are already occurring. Other impacts are highly uncertain due to their dependence on the structure of global and regional economies and future human alterations to the environment decades into the future, but they could be large. In Alaska, a range of adaptations to changing climate and related environmental conditions are underway, and others have been proposed as potential actions, including measures to reduce vulnerability and risk, as well as more systematic institutional transformation. For a full chapter, including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Alaska. End of section 28. Section 29 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 27, Hawaii and U.S.-affiliated Pacific Islands. Key Message 1. Threats to water supplies. Dependable and safe water supplies for Pacific Island communities and ecosystems are threatened by rising temperatures, changing rainfall patterns, sea level rise, and increased risk of extreme drought and flooding. Islands are already experiencing saltwater contamination due to sea level rise, which is expected to catastrophically impact food and water security, especially on low-lying atolls. Resilience to future threats relies on active monitoring and management of watersheds and freshwater systems. Key Message 2. Terrestrial ecosystems, ecosystem services, and biodiversity. Pacific Island ecosystems are notable for the high percentage of species found only in the region, and their biodiversity is both an important cultural resource for island people and a source of economic revenue through tourism. Terrestrial habitats and the goods and services they provide are threatened by rising temperatures, changes in rainfall, increased storminess, and land use change. These changes promote the spread of invasive species and reduce the ability of habitats to support protected species and sustain human communities. Some species are expected to become extinct, and others to decline to the point of requiring protection and costly management. Key Message 3: Coastal Communities and Systems. The majority of Pacific Island communities are confined to a narrow band of land within a few feet of sea level. Sea level rise is now beginning to threaten critical assets such as ecosystems, cultural sites and practices, economies, housing and energy, transportation, and other forms of infrastructure. By 2100, increases of 1 to 4 feet in global sea level are very likely, with even higher levels than the global average in the U.S.-affiliated Pacific Islands. This would threaten the food and freshwater supply of Pacific Island populations and jeopardize their continued sustainability and resilience. As sea level rise is projected to accelerate strongly after mid-century, adaptation strategies that are implemented sooner can better prepare communities and infrastructure for the most severe impacts. Key Message 4: Oceans and Marine Resources. Fisheries, coral reefs, and the livelihoods they support are threatened by higher ocean temperatures and ocean acidification. Widespread coral reef bleaching and mortality have been occurring more frequently, and by mid-century, these events are projected to occur annually, especially if current trends in emissions continue. Bleaching and acidification will result in loss of reef structure, leading to lower fisheries yields and loss of coastal protection and habitat. Declines in oceanic fishery productivity of up to 15% and 50% of current levels are projected by mid-century and 2100, respectively, under the higher scenario, RCP 8.5. Key Message 5: Indigenous Communities and Knowledge. Indigenous peoples of the Pacific are threatened by rising sea levels, diminishing freshwater availability, and shifting ecosystem services. These changes imperil communities' health, well-being, and modern livelihoods, as well as their familial relationships with lands, territories, and resources. Built on observations of climatic changes over time, the transmission and protection of traditional knowledge and practices, especially via the central role played by Indigenous women, are intergenerational, place-based, localized, and vital for ongoing adaptation and survival. Key Message 6: Cumulative Impacts and Adaptation. Climate change impacts in the Pacific Islands are expected to amplify existing risks and lead to compounding economic, environmental, social, and cultural costs. In some locations, climate change impacts on ecological and social systems are projected to result in severe disruptions to livelihoods that increase the risk of human conflict or compel the need for migration. Early interventions, already occurring in some places across the region, can prevent costly and lengthy rebuilding of communities and livelihoods, and minimize displacement and relocation. The U.S. Pacific Islands are culturally and environmentally diverse, treasured by the 1.9 million people who call them home. Pacific Islands are particularly vulnerable to climate change impacts due to their exposure and isolation, small size, low elevation in the case of atolls, and concentration of infrastructure and economy along the coasts. A prevalent cause of year-to-year changes in climate patterns around the globe and in the Pacific Islands region is the El Niño Southern Oscillation, ENSO. The El Niño and La Niña phases of ENSO can dramatically affect precipitation, air and ocean temperature, sea surface height, storminess, wave size, and trade winds. It is unknown exactly how the timing and intensity of ENSO will continue to change in the coming decades, but recent climate model results suggest a doubling in frequency of both El Niño and La Niña extremes in this century as compared to the 20th century under scenarios with more warming, including the higher scenario, RCP 8.5. On islands, all natural sources of freshwater come from rainfall received within their limited land areas. Severe droughts are common, making water shortage one of the most important climate-related risks in the region. As temperature continues to rise and cloud cover decreases in some areas, evaporation is expected to increase, causing both reduced water supply and higher water demand. Stream flow in Hawaii has declined over approximately the past 100 years, consistent with observed decreases in rainfall. The impacts of sea level rise in the Pacific include coastal erosion, episodic flooding, permanent inundation, heightened exposure to marine hazards, and saltwater intrusion to surface water and groundwater systems. Sea level rise will disproportionately affect the tropical Pacific and potentially exceed the global average. Invasive species, landscape change, habitat alteration, and reduced resilience have resulted in extinctions and diminished ecosystem function. Inundation of atolls in the coming decades is projected to impact existing on-island ecosystems. Wildlife that relies on coastal habitats will likely also be severely impacted. In Hawaii, coral reefs contribute an estimated $477 million to the local economy every year, under projected warming of approximately 0.5 degrees Fahrenheit per decade. All nearshore coral reefs in the Hawaii and Pacific Islands region will experience annual bleaching before 2050. An ecosystem-based approach to international management of open ocean fisheries in the Pacific that incorporates climate-informed catch limits is expected to produce more realistic future harvest levels and enhance ecosystem resilience. Indigenous communities of the Pacific derive their sense of identity from the islands. Emerging issues for indigenous communities of the Pacific include the resilience of marine managed areas and climate-induced human migration from their traditional lands. The rich body of traditional knowledge is place-based and localized, and is useful in adaptation planning because it builds on intergenerational sharing of observations. Documenting the kinds of governance structures or decision-making hierarchies created for management of these lands and waters is also important as a learning tool that can be shared with other island communities. Across the region, groups are coming together to minimize damage and disruption from coastal flooding and inundation, as well as other climate-related impacts. Social cohesion is already strong in many communities, making it possible to work together to take action. Early intervention can lower economic, environmental, social, and cultural costs, and reduce or prevent conflict and displacement from ancestral land and resources. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/Hawaii-Pacific. End of section 29. Section 30 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 28. Reducing Risks Through Adaptation Actions. Key Message 1. Adaptation implementation is increasing. Adaptation planning and implementation activities are occurring across the United States in the public, private, and nonprofit sectors. Since the 3rd National Climate Assessment, implementation has increased, but is not yet commonplace. Key Message 2. Climate change outpaces adaptation planning. Successful adaptation has been hindered by the assumption that climate conditions are and will be similar to those in the past. Incorporating information on current and future climate conditions into design guidelines, standards, policies, and practices would reduce risk and adverse impacts. Key Message 3. Adaptation entails iterative risk management. Adaptation entails a continuing risk management process. It does not have an endpoint. With this approach, individuals and organizations of all types assess risks and vulnerabilities from climate and other drivers of change, such as economic, environmental, and societal, take actions to reduce those risks, and learn over time. Key Message 4. Benefits of proactive adaptation exceed costs. Proactive adaptation initiatives, including changes to policies, business operations, capital investments, and other steps, yield benefits in excess of their costs in the near term as well as over the long term. Evaluating adaptation strategies involves consideration of equity, justice, cultural heritage, the environment, health, and national security. Key Message 5. New approaches can further reduce risk. Integrating climate considerations into existing organizational and sectoral policies and practices provides adaptation benefits. Further reduction of the risks from climate change can be achieved by new approaches that create conditions for altering regulatory and policy environments, cultural and community resources, economic and financial systems, technology applications, and ecosystems. Across the United States, many regions and sectors are already experiencing the direct effects of climate change. For these communities, climate impacts, from extreme storms made worse by sea level rise, to longer lasting and more extreme heat waves, to increased numbers of wildfires and floods, are an immediate threat, not a far-off possibility. Because these impacts are expected to increase over time, communities throughout the United States face the challenge not only of reducing greenhouse gas emissions, but also of adapting to current and future climate change to help mitigate climate risks. Adaptation takes place at many levels, national and regional, but mainly local, as governments, businesses, communities, and individuals respond to today's altered climate conditions and prepare for future change based on the specific climate impacts relevant to their geography and vulnerability. Adaptation has 5 general stages: awareness, assessment, planning, implementation, and monitoring and evaluation. These phases naturally build on one another, though they are often not executed sequentially, and the terminology may vary. The third National Climate Assessment, released in 2014, found the first 3 phases underway throughout the United States, but limited in terms of on-the-ground implementation. Since then, the scale and scope of adaptation implementation have increased, but in general, adaptation implementation is not yet commonplace. One important aspect of adaptation is the ability to anticipate future climate impacts and plan accordingly. Public and private sector decision-makers have traditionally made plans assuming that the current and future climate in their location will resemble that of the recent past. This assumption is no longer reliably true. Increasingly, planners, builders, engineers, architects, contractors, developers, and other individuals are recognizing the need to take current and projected climate conditions into account in their decisions about the location and design of buildings and infrastructure, engineering standards, insurance rates, property values, land use plans, disaster response preparations, supply chains, and cropland and forest management. In anticipating and planning for climate change, decision-makers practice a form of risk assessment known as iterative risk management. Iterative risk management emphasizes that the process of anticipating and responding to climate change does not constitute a single set of judgments at any point in time. Rather, it is an ongoing cycle of assessment, action, reassessment, learning, and response. In the adaptation context, public and private sector actors manage climate risk using 3 types of actions: reducing exposure, reducing sensitivity, and increasing adaptive capacity. Climate risk management includes some attributes and tactics that are familiar to most businesses and local governments, since these organizations already commonly manage or design for a variety of weather-related risks, including coastal and inland storms, heat waves, water availability threats, droughts, and floods. However, successful adaptation also requires the often unfamiliar challenge of using information on current and future climate rather than past climate, which can prove difficult for those lacking experience with climate change datasets and concepts. In addition, many professional practices and guidelines, as well as legal requirements, still call for the use of data based on past climate. Finally, factors such as access to resources, culture, governance, and available information can affect not only the risk faced by different populations, but also the best ways to reduce their risks. Achieving the benefits of adaptation can require upfront investments to achieve longer-term savings, engaging with differing stakeholder interests and values, and planning in the face of uncertainty. But adaptation also presents challenges, including difficulties in obtaining the necessary funds, insufficient information and relevant expertise, and jurisdictional mismatches. In general, adaptation can generate significant benefits in excess of its costs. Benefit cost analysis can help guide organizations toward actions that most efficiently reduce risks, in particular, those that, if not addressed, could prove extremely costly in the future. Beyond those attributes explicitly measured by benefit cost analysis, effective adaptation can also enhance social welfare in many ways that can be difficult to quantify and that people will value differently, including improving economic opportunity, health, equity, security, education, social connectivity, and sense of place, as well as safeguarding cultural resources and practices and environmental quality. A significant portion of climate risk can be addressed by mainstreaming, that is, integrating climate adaptation into existing organizational and sectoral investments, policies, and practices, such as planning, budgeting, policy development, and operations and maintenance. Mainstreaming of climate adaptation into existing decision processes has already begun in many areas, such as financial risk reporting, capital investment planning, engineering standards, military planning, and disaster risk management. Further reduction of the risks from climate change, in particular those that arise from futures with high levels of greenhouse gas emissions, calls for new approaches that create conditions for altering regulatory and policy environments, cultural and community resources, economic and financial systems, technology applications, and ecosystems. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/adaptation. End of section 30. Section 31 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Chapter 29, Reducing Risks Through Emissions Mitigation. Key Message 1. Mitigation-related activities within the United States. Mitigation-related activities are taking place across the United States at the federal, state, and local levels, as well as in the private sector. Since the 3rd National Climate Assessment, a growing number of states, cities, and businesses have pursued or deepened initiatives aimed at reducing emissions. Key Message 2. The Risks of Inaction. In the absence of more significant global mitigation efforts, climate change is projected to impose substantial damages on the U.S. economy, human health, and the environment. Under scenarios with high emissions and limited or no adaptation, annual losses in some sectors are estimated to grow to hundreds of billions of dollars by the end of the century. It is very likely that some physical and ecological impacts will be irreversible for thousands of years, while others will be permanent. Key Message 3. Avoided or reduced impacts due to mitigation. Many climate change impacts and associated economic damages in the United States can be substantially reduced over the course of the 21st century through global-scale reductions in greenhouse gas emissions, though the magnitude and timing of avoided risks vary by sector and region. The effect of near-term emissions mitigation on reducing risks is expected to become apparent by mid-century and grow substantially thereafter. Key Message 4: Interactions between mitigation and adaptation. Interactions between mitigation and adaptation are complex and can lead to benefits, but they also have the potential for adverse consequences. Adaptation can complement mitigation to substantially reduce exposure and vulnerability to climate change in some sectors. This complementarity is especially important given that a certain degree of climate change due to past and present emissions is unavoidable. Current and future emissions of greenhouse gases, and thus emission mitigation actions, are crucial for determining future risks and impacts of climate change to society. The scale of risks that can be avoided through mitigation actions is influenced by the magnitude of emissions reductions, the timing of those reductions, and the relative mix of mitigation strategies for emissions of long-lived greenhouse gases, namely carbon dioxide, short-lived greenhouse gases, such as methane, and land-based biologic carbon. Many actions at national, regional, and local scales are underway to reduce greenhouse gas emissions, including efforts in the private sector. Climate change is projected to significantly damage human health, the economy, and the environment in the United States, particularly under a future with high greenhouse gas emissions. A collection of frontier research initiatives is underway to improve understanding and quantification of climate impacts. These studies have been designed across a variety of sectoral and spatial scales and feature the use of internally consistent climate and socioeconomic scenarios. Recent findings from these multi-sector modeling frameworks demonstrate substantial and far-reaching changes over the course of the 21st century, and particularly at the end of the century, with negative consequences for a large majority of sectors, including infrastructure and human health. For sectors where positive effects are observed in some regions or for specific time periods, the effects are typically dwarfed by changes happening overall within the sector or at broader scales. Recent studies also show that many climate change impacts in the United States can be substantially reduced over the course of the 21st century through global-scale reductions in greenhouse gas emissions. While the difference in climate outcomes between scenarios is more modest through the first half of the century, the effect of mitigation in avoiding climate change impacts typically becomes clear by 2050 and increases substantially in magnitude thereafter. Research supports that early and substantial mitigation offers a greater chance of avoiding increasingly adverse impacts. The reduction of climate change risk due to mitigation also depends on assumptions about how adaptation changes the exposure and vulnerability of the population. Physical damages to coastal property and transportation infrastructure are particularly sensitive to adaptation assumptions, with proactive measures estimated to be capable of reducing damages by large fractions. Because society is already committed to a certain amount of future climate change due to past and present emissions, and because mitigation activities cannot avoid all climate-related risks, mitigation and adaptation activities can be considered complementary strategies. However, adaptation can require large upfront costs and long-term commitments for maintenance, and uncertainty exists in some sectors regarding the applicability and effectiveness of adaptation in reducing risk. Interactions between adaptation and mitigation strategies can result in benefits or adverse consequences. While uncertainties still remain, advancements in the modeling of climate and economic impacts, including current understanding of adaptation pathways, are increasingly providing new capabilities to understand and quantify future effects. For a full chapter including references and traceable accounts, see https://nca2018.globalchange.gov/chapter/mitigation. End of section 31. Section 32 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Frequently Asked Questions. Introduction to Climate Change. Question: how do we know Earth is warming? Short answer: many indicators show conclusively that Earth has warmed since the 19th century. In addition to warming shown in the observational record of oceanic and atmospheric temperature, other evidence includes melting glaciers and continental ice sheets, rising global sea level, a longer frost-free season, changes in temperature extremes, and increases in atmospheric humidity, all consistent with long-term warming. Long answer: observations of surface temperature, taken over Earth's land and ocean surfaces since the 19th century, show a clear warming trend. Temperature observations have been taken consistently since the 1880s or earlier at thousands of observing sites around the world. Additionally, instruments on ships, buoys, and floats together provide a more than 100-year record of sea surface temperature, showing that the top 6,500 feet of Earth's ocean is warming in all basins. These observations are consistent with readings from satellite instruments that measure atmospheric and sea surface temperatures from space. Used together, land, ocean, and space-based temperature observations show clear evidence of warming at Earth's surface over climatological timescales. http://www.globalchange.gov/browse/indicators for more indicators of change. See also Chapter 2, Climate. Scientists around the world have been measuring the extent and volume of ice contained in the same glaciers every few years since 1980. These measurements show that, globally, there is a large net volume loss in glacial ice since the 1980s. However, the rate of the ice loss varies by region, and in some cases, yearly glacier advances are observed. See frequently asked question: how does climate change affect mountain glaciers? Ice sheets on Antarctica and Greenland have been losing ice mass consistently since 2002, when advanced satellite measurements of their continental ice mass began. See frequently asked question: is Antarctica losing ice? What about Greenland? Arctic sea ice coverage has been monitored using satellite imagery since the late 1970s, showing consistent and large declines in September, the time of year when the minimum coverage occurs. There are additional observational lines of evidence for warming. For example, the area of land in the northern hemisphere covered by snow each spring is now smaller on average than it was in the 1960s. Tide gauges and satellites show that global sea level is rising, both as a result of the addition of water to the ocean from melting glaciers and from the expansion of seawater as it warms. Chapter 2 Climate, Chapter 8 Coastal. Lastly, as air warms, its capacity to hold water vapor increases, and measurements show that atmospheric humidity is increasing around the globe, consistent with a warming climate. See Chapter 3 Water. See also Chapter 1 Overview, Figure 1.2, for more indicators of a warming world. Question: what makes recent climate change different from warming in the past? Short answer: increases in global temperature since the 1950s are unusual for two reasons. First, current changes are primarily the result of human activities rather than natural physical processes. Second, temperature changes are occurring much faster than they did in the past. Long answer: our planet's climate has changed before. Sedimentary rocks and fossils show clear evidence for a series of long cold periods, called ice ages, followed by warm periods. Common archaeological and geological processes for dating past events show that these cycles of cooling and warming occurred about once every 100,000 years, for at least the last million years. Before major land use changes and industrialization, changes in global temperature were caused by natural factors, including regular changes in Earth's orbit around the Sun, volcanic eruptions, and changes in energy from the Sun. Major warming and cooling events were driven by natural variations of Earth's orbit that altered the amount of sunlight reaching Earth's Arctic and Antarctic regions, resulting in the retreat and advance of massive ice sheets. Additionally, quiescent or active periods of volcanic eruptions also could contribute to warming or cooling events, respectively. Natural factors are still affecting the planet's climate today. See Figure A5.5. Yet, since the beginning of the Industrial Revolution, human use of coal, oil, and gas has rapidly changed the composition of the atmosphere. Figure A5.1. Land use changes, such as deforestation, cement production, and animal production for food, have also contributed to the increase in levels of greenhouse gases in the atmosphere. Unlike past changes in climate, today's warming is driven primarily by human activity rather than by natural physical processes. See Figure A5.5. See also Chapter 2, Climate. Current warming is also happening much faster than it did in the past. Scientific records from ice cores, tree rings, soil boreholes, and other natural thermometers, often called proxy climate data, show that the recent increase in temperature is unusually rapid compared to past changes. See Figures A5.2 and A5.4. After an ice age, Earth typically took thousands of years to warm up again. The observed rate of warming over the last 50 years is about 8 times faster than the average rate of warming from a glacial maximum to a warm interglacial period. Question: what's the difference between global warming and climate change? Short answer: Though some people use the terms global warming and climate change interchangeably, their meanings are slightly different. Global warming refers only to Earth's rising surface temperature, while climate change includes temperature changes and a multitude of effects that result from warming, including melting glaciers, increased humidity, heavier rainstorms, and changes in the patterns of some climate-related extreme events. Long answer. By itself, the phrase global warming refers to increases in Earth's annual average surface temperature. Today, however, when people use the phrase, they usually mean the recent warming that is due in large part to the rapid increase of greenhouse gases, GHGs, in the atmosphere from human activities such as deforestation and the burning of fossil fuels for energy. Thus, global warming has become a form of shorthand for a complex scientific process. The entire globe is not warming uniformly. Some areas may cool, such as the North Atlantic Ocean, while some may warm faster than the global average, such as the Arctic. The term climate change refers to the full range of consequences or impacts that occur as atmospheric levels of GHGs rise and different parts of the Earth system respond to a higher average surface temperature. For instance, observed long-term trends, such as increases in the frequency of drought and heavy precipitation events, are not technically warming trends, but they are related to current warming and are processes of climate change. Chapter 2, Climate. End of section 32. Section 33 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Frequently asked questions. Climate science. Question: what are greenhouse gases, and what is the greenhouse effect? Short answer: greenhouse gases, GHGs, are gases that absorb and emit thermal, heat, infrared radiation. Carbon dioxide, methane, nitrous oxide, ozone, and water vapor are the most prevalent GHGs in Earth's atmosphere. These gases absorb heat emitted by Earth's surface and re-emit that heat into Earth's atmosphere, making it much warmer than it would be otherwise, a process known as the greenhouse effect. Long answer: most of Earth's atmosphere is made up of nitrogen, N2, and oxygen, O2, neither of which is considered a greenhouse gas. Other gases, known as greenhouse gases, GHGs, behave very differently from O2 and N2 when it comes to infrared radiation emitted from Earth. GHGs, such as water vapor, carbon dioxide, CO2, and methane, CH4, have a more complex molecular structure, made up of 3 or more atoms, as opposed to the symmetrical 2-atom molecules of O2 and N2, that absorbs some of the energy emitted from Earth's surface and then re-radiates that energy in all directions, including back down towards the surface. This ultimately traps energy in the lower atmosphere in the form of heat, figure A5.3. This greenhouse effect makes the average temperature of Earth nearly 60 degrees Fahrenheit warmer than it would be in the absence of these GHGs. even a tiny amount of these gases can have a huge effect on the amount of heat trapped in the lower atmosphere, just like a tiny amount of anthrax can have a huge effect on human health. Many GHGs, including CO2, CH4, water vapor, and nitrous oxide, N2O, occur naturally in the atmosphere. However, atmospheric concentrations of these GHGs have been rising over the last few centuries as a result of human activities. In addition, human activities have added new, entirely human-made GHGs to the atmosphere, including chlorofluorocarbons, CFCs, hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and sulfur hexafluoride, SF6. As the global population has increased, so have GHG emissions. This, in turn, makes the greenhouse effect stronger, resulting in higher average temperature around the globe. Chapter 2, Climate. Question: why are scientists confident that human activities are the primary cause of recent climate change? Short answer: many independent lines of evidence support the finding that human activities are the dominant cause of recent, since 1950, climate change. These lines of evidence include changes seen in the observational records that are consistent with our understanding, based on physics, of how the climate system should change due to human influences. Other evidence comes from climate modeling studies that closely reproduce the observed temperature record. Long answer. The Climate Science Special Report concludes, quote, "Human activities, especially emissions of greenhouse gases, are the dominant cause of the observed warming since the mid-20th century." End quote. The Earth's climate only warms or cools significantly in response to changes that affect the balance of incoming and outgoing energy. Over long time scales, tens to hundreds of thousands of years, orbital cycles produce long periods of warming and cooling. Over shorter time scales, two factors could generally force changes in Earth's temperature to a measurable degree. One, changes in the amount of energy put out by the sun, and two, changes in the concentrations of greenhouse gases, GHGs, in Earth's atmosphere. Recent measurements of the sun's energy show no trend over the last 50 years. Additionally, observations show that the lower atmosphere, troposphere, has warmed, while the upper atmosphere, stratosphere, has cooled. If the observed warming had been due to an increase in energy from the sun, then all layers of Earth's atmosphere would have warmed, which is not what scientists observe. Thus, we can eliminate changes in the energy received from the sun as a major factor in the warming observed since about 1950. This leaves the possibility that changes in GHG concentrations in the atmosphere are the primary cause of recent warming. Atmospheric carbon dioxide, CO2, levels have increased from approximately 270 parts per million, ppm, during pre-industrial times to the current 408 parts per million observed in 2018. See https://www.esrl.noaa.gov/gmd/ccgg/trends/ levels that exceed any observed over the past 800,000 years. Figure A5.4. In addition, atmospheric concentrations of other GHGs, including methane and nitrous oxide, have increased over the same period. This increase in GHG concentrations has coincided with the observed increase in global temperature. Scientists use methods that provide chemical fingerprints of the source of these increased emissions and have shown that the 40% increase in atmospheric CO2 levels since the Industrial Revolution is due mainly to human activities, primarily the combustion of fossil fuels, and not due to natural carbon cycle processes. Other evidence attributing human activities as the dominant driver of observed warming comes from climate modeling studies. Computer simulations of Earth's climate based on historical data of observed changes in natural and human influences accurately reproduce the observed temperature record over the last 120 years. These results show that without human influences, such as the observed increases in GHG emissions, Earth's surface would have cooled slightly over the past half-century. The only way to closely replicate the observed warming is to include both natural and human-forcing changes in climate models, figure A5.5. Thus, the observational record and modeling studies both point to human factors being the main cause for the recent warming. Chapter 2, Climate. Question: what role does water vapor play in climate change? Short answer: water vapor is the most abundant greenhouse gas, GHG, in the atmosphere and plays an important role in Earth's climate, significantly increasing Earth's temperature. However, unlike other GHGs, water vapor can condense and precipitate, so water vapor has a short lifespan in the atmosphere. Air temperature, and not emissions, controls the amount of water vapor in the lower atmosphere. For this reason, water vapor is considered a feedback agent and not a driver of climate change. Long answer: water vapor is the primary GHG in the atmosphere, and its contribution to Earth's greenhouse effect is about 2 or 3 times that of carbon dioxide, CO2. Human activities directly add water vapor to the atmosphere, primarily through increasing evaporation from irrigation, power plant cooling, and combustion of fossil fuels. Other GHGs, such as CO2, are not condensable at atmospheric temperatures and pressures, so they will continue to build up in the atmosphere as long as their emissions continue. The amount of water vapor in the lower atmosphere, troposphere, is mainly controlled by the air temperature and proximity to a water source, such as an ocean or large lake, rather than by emissions from human activities. Fluctuations in air temperature change the amount of water vapor that the air can hold, with warmer air capable of holding more moisture. Increases in water vapor levels in the lower atmosphere are considered a positive feedback, or self-reinforcing cycle, in the climate system, as increasing concentrations of other GHGs, for example carbon dioxide, methane, and nitrous oxide, warm the atmosphere. Atmospheric water vapor concentrations increase, thereby amplifying the warming effect. Figure A5.6. If atmospheric concentrations of CO2 and other GHGs decreased, air temperature would drop, decreasing the ability of the atmosphere to hold water vapor, further decreasing temperature. Question: how are El Niño and climate variability related to climate change? Short answer: El Niño and other forms of natural climate variability are not caused by humans, but their frequency, duration, extent, or intensity might be affected by greenhouse gas emissions from human activities. Natural climate variability produces short-term regional changes in temperature and weather patterns, whereas human-caused climate change is a persistent, long-term phenomenon. Long answer. Climate variability refers to the natural changes in climate that fall within the observed range of extremes for a particular region, as measured by temperature, precipitation, and frequency of events. Drivers of climate variability include the El Niño Southern Oscillation, or ENSO, and other phenomena. ENSO is a quasi-periodic warming or cooling of the sea surface temperatures in the tropical eastern Pacific and is often referred to by its phase of El Niño, warm phase, or La Niña, cool phase. These different ENSO phases can have varying ecosystem and economic effects, especially in certain fishing communities, while also influencing weather worldwide. Figure A5.7. In the United States, El Niño conditions generally correspond with warmer than average sea surface and air temperatures along the west coast, wetter conditions in the southwest, cooler temperatures in the southeast, and warmer conditions in the northeast. In contrast, the La Niña phase of ENSO corresponds to cooler temperature in the U.S. Northwest and drier and warmer conditions in the southeast, along with increased upwelling along the west coast. Evidence from paleoclimate records suggests that there have been changes in the frequency and intensity of ENSO events in the past. Human-caused climate change might also affect the frequency and magnitude of ENSO events and can exacerbate or ameliorate regional ENSO impacts. For example, if there is a strong La Niña event that results in dry conditions in the southwest, those conditions may be exacerbated by additional drying due to climate change. ENSO is a complex phenomenon, but new research is shedding light on the many factors influencing how climate change affects the ENSO cycle. End of section 33. Section 34 of the 4th National Climate Assessment, Volume 2, by USGCRP. This LibriVox recording is in the public domain. Recording by Warren Kati, Gurnee, Illinois. Frequently asked questions. Temperature and climate projections. Question: what methods are used to record global surface temperatures and measure changes in climate? Short answer: global surface temperatures are measured by using data from weather stations over land and by ships and buoys over the ocean. Global surface temperature records date back more than 300 years in some locations, and near global coverage has existed since the late 1800s. Multiple research groups have examined U.S. and global temperature records in great detail, taking into account changes in instruments, the time of observations, station location, and any other potential sources of error. Although there are slight differences among datasets, due to choices in data selection, analysis, and averaging techniques, these differences do not change the clear result that global surface temperature is rising. Long answer: Climate change is best measured by assessing trends over long periods of time, generally greater than 30 years, which means we need global surface temperature records that include data from before the satellite age. Scientists who obtain, digitize, and collate long-term temperature records take great care to ensure that any potentially skewed measurements, such as a change in instrument method or location, or a change in the time of day a recording is made, do not affect the integrity of the dataset. Researchers rigorously examine the data to identify and adjust for any such effects before using it to evaluate long-term climate trends. Different choices in data selection, analysis, and averaging techniques by multiple independent research teams mean that each dataset varies slightly. Even with these variations, however, multiple independently produced results are in very good agreement at both global and regional scales. All global surface temperature datasets indicate that the vast majority of Earth's surface has warmed since 1901. Figure A5.8. Scientists also consider other influences that could impact temperature records, such as whether data from thermometers located in cities are skewed by the urban heat island effect, where heat absorbed by buildings and asphalt makes cities warmer than the surrounding countryside. When determining climate trends, data corrections to these temperature records have adequately accounted for this effect. At the global scale, evidence of global warming over the past 50 years is still observed, even if all of the urban stations are removed from the global temperature record. Studies have also shown that the warming trends of rural and urban areas that are in close proximity essentially match, even though the urban areas may have higher temperatures overall. Question: were there predictions of global cooling in the 1970s? Short answer: no. A review of the scientific literature from the 1970s shows that the broad climate science community did not predict global cooling or an imminent ice age. On the contrary, even then, discussions of human-related warming dominated scientific publications on climate and human influences. Long answer: scientific understanding of what are called the Milankovitch cycles, cyclical changes in Earth's orbit that can explain the onset and ending of ice ages, led a few scientists in the 1970s to contemplate that the current warm interglacial period might be ending soon, leading to a new ice age over the next few centuries. These few speculations were picked up and amplified by the media. But at that time, there were far more scientific articles describing how warming would occur from the increase in atmospheric concentrations of greenhouse gases from human activities, including the burning of fossil fuels. Figure A5.9. The latest information suggests that if Earth's climate was being controlled primarily by natural factors, the next cooling cycle would begin sometime in the next 1,500 years. However, humans have so altered the composition of the atmosphere that the next ice age has likely now been delayed. That delay could potentially be tens of thousands of years. Question: how are temperature and precipitation patterns projected to change in the future? Short answer: our world will continue to warm in the future because of historic emissions of greenhouse gases, GHGs. But the amount of warming will depend largely on the level of future emissions of GHGs and the choices humans make. If humans continue burning fossil fuels at or above our current rate through the end of the century, scientists project Earth will warm about 9 degrees Fahrenheit relative to pre-industrial times, prior to 1750. Precipitation is projected to still be seasonally and regionally variable, but on average, projections show high latitude areas getting wetter and subtropical areas getting drier. The frequency and intensity of very heavy precipitation are expected to increase, increasing the likelihood of flooding. Climate change will not affect all places in the same way or to the same degree, but will vary at regional levels. Long answer. In the coming decades, scientists project that global average temperature will continue to increase. Chapter 2, Climate. Although natural variability will continue to play a significant role in year-to-year changes. Sizable variations from global average changes are possible at the regional level. Even if humans drastically reduce levels of GHG emissions, near-term warming will still occur because there is a lag in the temperature response to changes in atmospheric composition. Figure A5.10. Over the next couple decades, natural variability and the response of Earth's climate system to historic emissions will be the primary determinants of observed warming. After about 2050, however, the rate and amount of emissions of GHGs released by human activities, as well as the response of Earth's climate system to those emissions, will be the primary determining factors in changes in global and regional temperature. Figure A5.13. See also Chapter 2, Climate. Efforts to rapidly and significantly reduce emissions of GHGs can still limit the global temperature increase to 3.6 degrees Fahrenheit, 2 degrees Celsius, by the end of the century relative to pre-industrial levels. Precipitation patterns are also expected to continue to change throughout this century and beyond. The trends observed in recent decades are expected to continue, with more precipitation projected to fall in the form of heavier precipitation events. Such events increase the likelihood of flooding, even in drought-prone areas. As with increases in global average temperature, large-scale shifts toward wetter or drier conditions and the projected increases in heavy precipitation are expected to be greater under higher GHG emissions scenarios, for example, RCP 8.5, versus lower ones, for example, RCP 4.5. Projected warming is also expected to lead to an increase in the fraction of total precipitation falling as rain rather than snow, which reduces snowpack on the margins of areas that now have reliable snowpack accumulation during the cold season. See, for example, Chapter 24, Northwest, Key Message 2. Question: how do computers model Earth's climate? Short answer: global climate models enable scientists to create virtual Earths, where they can analyze causes and effects of past changes in temperature, precipitation, and other climate variables. Today's climate models can accurately reproduce broad features of past and present climate, such as the location and strength of the jet stream, the spatial distribution and seasonal cycle of precipitation, and the natural occurrence of extreme weather events, such as heat and cold waves, droughts and floods, and hurricanes. They can also reproduce historic natural cycles, such as the periodic occurrence of ice ages and interglacial warm periods, as well as the human-caused warming that has occurred over the last 50 years. While uncertainties remain, scientists have confidence in model projections of how climate is likely to change in the future in response to key variables, such as an increase in human-caused emissions of greenhouse gases, in part because of how accurately they can represent past climate changes. Long answer. Climate models are based on equations that represent fundamental laws of nature and the many processes that affect Earth's climate system. By dividing the atmosphere, land, and ocean into smaller spatial units to solve the equations, climate models capture the evolving patterns of atmospheric pressures, winds, temperatures, and precipitation. Over longer time frames, these models simulate wind patterns, high and low pressure systems, ocean currents, ice and snowpack accumulation and melting, soil moisture, extreme weather occurrences, and other environmental characteristics that make up the climate system. Figure A5.11. Some important processes, including cloud formation and atmospheric mixing, are represented by approximate relationships, either because the processes are not fully understood or they are at a scale that a model cannot directly represent. These approximations lead to uncertainties in model simulations of climate. Approximations are not the only uncertainties associated with climate models, as discussed in the frequently asked question, what are key uncertainties when projecting climate change? Question: can scientists project the effects of climate change for local regions? Short answer: yes, though there are limitations. With advances in computing power, the future effects of climate change can be projected more accurately for local communities. Local high-resolution, downscaled climate modeling can be used to produce data at a scale of 1 to 20 miles. These downscaled projections show climate-related impacts at the local level and can be an important tool for community planners and decision makers. Long answer. One significant research focus recently has been to develop models of climate impacts on a relatively small geographic scale. Most global climate projections use grid units that may be too coarse to properly represent mountains, coastlines, and other important features of a local landscape. Recently, two different approaches have been used by scientists to project local climate conditions. The first is a statistical approach that uses local observations in conjunction with global models to project future changes. The local observations required for this approach are available only for limited regions and for a few climate variables, mainly temperature and precipitation. Figure A5.12. The second method is a so-called dynamical approach that uses an additional high-resolution computer model, similar to a weather prediction model, to account for complex topography and varying land cover that can impact climate on the local level. High-resolution dynamical models are complete enough to simulate numerous climate variables, temperature, precipitation, winds, humidity, surface sunlight, etc., and do not require the local observations required for the statistical approach. However, these models require an immense amount of computing power. today's most powerful supercomputers enable climate scientists to examine the effects of climate change in ways that were impossible just 5 years ago. Over the next decade, computer speeds are predicted to increase 100-fold or more, improving climate projections and models on both the global and local levels. It should also be noted that both statistical and dynamical approaches have biases and errors that, when combined with uncertainties from global model simulations, can reduce the level of confidence in these more localized projections. See Hayhoe et al. 2017 for more details. Question: what are key uncertainties when projecting climate change? Short answer: the precise amount of future climate change that will occur over the rest of this century is uncertain, mainly due to uncertainties in emissions, natural variability, and differences in scientific models. Long answer: first, projections of future climate changes are usually based on scenarios, or sets of assumptions, regarding how future emissions may change due to changes in population, energy use, technology, and economics. Society may choose to reduce emissions or continue on a pathway of increasing emissions. The differences in projected future climate under different scenarios are generally small for the next few decades. By the second half of the century, however, human choices, as reflected in these scenarios, become the key determinant of future climate change. Figure A5.13. A second source of uncertainty is natural variability, which affects the climate over timescales from months to decades. These natural variations are largely unpredictable, such as a volcanic eruption, and are superimposed on the warming from increasing greenhouse gases, GHGs. A third source of uncertainty involves limitations in our current scientific knowledge. Climate models differ in the way they represent various processes, for example, cloud properties, ocean circulation, and aerosol effects. Additionally, climate sensitivity, or how much the climate will warm with a given increase in GHGs, often a doubling of GHG from pre-industrial levels, is still a major source of uncertainty. As a result, different models produce small differences in projections of global average change. Scientists often use multiple models to account for the variability and represent this as a range of projected outcomes. Finally, there is always the possibility that there are processes and feedbacks not yet being included in projections of climate in the future. For example, as the Arctic warms, carbon trapped in permafrost may be released into the atmosphere, increasing the initial warming due to human-caused emissions of GHGs, or an ice sheet may collapse, leading to faster than expected sea level rise. However, for a given future scenario, the amount of future climate change can be specified within plausible bounds, with those bounds determined not only from the differences in how climate responds to a doubling of GHG concentrations among models, but also by utilizing information about climate changes in the past. See Hayhoe et al. 2017 for more details. Question: is it getting warmer everywhere at the same rate? Short answer: our world is warming overall, but temperatures are not increasing at the same rate everywhere. The average global temperature is projected to continue increasing throughout the remainder of this century due to greenhouse gas (GHG) emissions from human activities. Generally, high latitudes are expected to continue warming more than lower latitudes. Coastal and island regions are expected to warm less than interior continent regions. Long answer. Temperature changes at a given location are a function of multiple factors, including global and local forces, and both human and natural influences. Though Earth's average temperature is rising, some locations could be cooling due to local factors. In some places, including the U.S. Southeast, temperatures do not show a warming trend over the last century as a whole, although they have been increasing since the 1960s. Chapter 19, Southeast. Possible causes of the observed lack of warming in the Southeast during the 20th century include increased cloud cover and precipitation, increases in the presence of fine particles, called aerosols, in the atmosphere, expanding forests, decreases in the amount of heat conducted from land due to increases in irrigation, and multi-decadal variability in sea surface temperatures in both the North Atlantic and the tropical Pacific Oceans. At smaller geographic scales and time intervals, the relative influence of natural variations in climate compared to the human contribution is larger than at the global scale. A lack of warming or a decrease in temperature at an individual location does not negate the fact that, overall, the planet is warming. Alaska, in contrast to the U.S. Southeast, has been warming twice as fast as the global average since the middle of the 20th century. Chapter 26, Alaska. Statewide average temperatures for 2014 through 2016 were notably warmer as compared to the last few decades, with 2016 being the warmest on record. Daily record high temperatures in the contiguous United States are now occurring twice as often as record low temperatures. In Alaska, starting in the 1990s, record high temperatures occurred 3 times as often as record lows, and in 2015, an astounding 9 times as often. Chapter 26, Alaska. Because Earth's climate system still has more energy entering than leaving, global warming has not yet equilibrated to the load of increased GHGs that have already accumulated in the atmosphere. For example, the oceans are still warming over many layers from surface to depth. Some GHGs have long lifetimes. For example, carbon dioxide can reside in the atmosphere for a century or more. Thus, even if the emissions of GHGs were to be sharply curtailed to bring them back to natural levels, it is estimated that Earth is committed to continued warming of more than 1 degree Fahrenheit by 2100. At the global scale, some future years will be cooler than the preceding year. Some decades could even be cooler than the preceding decade. Figure A5.14. Brief periods of faster temperature increases and also temporary decreases in global temperature can be expected to continue into the future as a result of natural variability and other factors. Nonetheless, each successive decade in the last 30 years has been the warmest in the period of reliable instrumental records, going back to 1850, figure A5.15. In fact, the rate of warming has accelerated in the past several decades, and 17 of the 18 warmest years have occurred since 2001. See frequently asked question, what do scientists mean by the warmest year on record? Based on this historical record and assessed scenarios for the future, it is expected that future global temperatures, averaged over climate timescales of 30 years or more, will be higher than preceding periods as a result of emissions of CO2 and other GHGs from human activities. Chapter 2, Climate. Question: what do scientists mean by the warmest year on record? Short answer: when scientists declare it the warmest year on record, they mean it's the warmest year since modern global surface temperature record keeping began in 1880. Global temperature data from NASA show that 2016 marked the sixth time this century that a new record high annual average temperature was set, along with 2002, 2005, 2010, 2014, and 2015, and that 17 of the 18 warmest years have occurred since 2001. Long answer: the warmest year on record means it is the warmest year in more than 130 years of modern record keeping of global surface temperature. Prior to 1880, observations did not cover a large enough area of Earth's surface to enable an accurate calculation of the global average temperature. To calculate the value in recent times, scientists evaluate data from roughly 6,300 stations around the world on land, ships, and buoys. The year the last National Climate Assessment was published, 2014, was the warmest year on record at the time, but it was surpassed by 2015, which was then surpassed by 2016. Data from NASA shows that 17 of the 18 warmest years have occurred since 2001, and the 6 warmest years on record have occurred this century. Figure A5.16. However, the global surface temperature is affected by natural variability in addition to climate change, so it is not expected that each year will set a new temperature record. Question: how do climate projections differ from weather predictions? Short answer: the range of possible weather conditions at a specific location on any given day can vary considerably. The climate varies far less for that same location because it is a measure of weather conditions averaged over 30 years or more. Because the range of possible climate conditions at a given location is much smaller than the range of possible weather conditions, scientists are able to project climate conditions decades into the future. Long answer: projecting how climate may change decades in the future is a different scientific issue than forecasting weather a few days from now. Weather prediction means determining the exact location, time, and magnitude of specific events. Because the range of possible weather conditions can vary so widely, the weather forecast is extremely sensitive to even the smallest uncertainties or errors in our description of the state of the atmosphere at the start of a forecast. The impact of those uncertainties magnifies over time, which makes it very difficult to predict specific weather events at a given location more than a week or two into the future. Because climate is the average weather at a given location over long periods of time, 3 decades or more, The range of possible climate conditions at a given location is much smaller than the range of possible weather conditions. For example, the daytime high temperature at a given location may vary by 30 degrees Fahrenheit or more over the course of a day, while the annual average temperature over 30 years may vary by no more than a few degrees. Figure A5.17. We can project how climate may change over time in response to natural forces, such as changes in incoming solar radiation, and in response to human activities, such as increasing the abundance of greenhouse gases, GHGs, or decreasing particle pollution. These projections are usually expressed in terms of probabilities, describing a range of possible outcomes, not in the sort of exact, deterministic language of many weather forecasts. The difference between predicting weather and projecting climate is sometimes illustrated with a public health analogy. While it is impossible for us to determine the exact date and time when a particular individual will die, we can easily calculate the average age of death of all Americans for a time period in the past. In this case, weather is like the individual, while climate is like the average. To extend this analogy into the realm of climate change, we can also calculate the average life expectancy of Americans who smoke. We can predict that, on average, smokers will not live as long as non-smokers. Similarly, we can project what the climate will be like if we emit lower levels of GHGs and what it will be like if we emit more. End of section 34.